Hello everyone and welcome to today's session on machine learning full course. Machine learning is growing in importance due to increasingly enormous volumes and variety of data, the access and affordability of computational power, and the availability of high-speed internet. Machine learning and artificial intelligence is definitely one of the most demanded skill in today's scenario. In today's session, we'll learn machine learning right from scratch. So without further ado, let's start with the agenda. First, we'll be talking about what is machine learning and how does it work. After that, we'll be discussing about the different machine learning algorithms like supervised, unsupervised, and reinforcement learning. Then we'll be discussing about some basic concepts of Numpy and Pandas in Python. Then we'll be discussing about data visualization. Post that, we'll be discussing more about linear regression. And then we'll jump to the concepts of deep learning and neural networks. Lastly, we'll be talking about some interview questions related to machine learning which will help you to ace your interviews. So let's begin with the session now. But before we begin with the session, please like and subscribe to our channel and hit the bell icon for more updates from Intellipaat. Now let's begin with the session.
Well guys, the first question we all obviously have to answer is what is machine learning, right? Well guys, let me give you the textbook definition first and we can break it down later. Well, the textbook definition says machine learning is an application of artificial intelligence that provides systems with the ability to actually automatically learn on their own and improve from previous experience without being programmed by a human being. This is the actual textbook definition. But to break it down, in my personal opinion and in the opinion of a lot of data science professionals, machine learning is basically one of the ways that we can go about achieving artificial intelligence, guys. Well, machine learning right now, if you think about it, let's say past few years or right now or probably the next few years from now, it's all about mathematics and the mixture of mathematics and a lot of algorithms mixed together, and these put on some sort of massive steroids, guys, basically. So when you think about it that way, this is where we are right now. But if you're wondering where we're going to go in the future, well, in the future, it is definitely going to be achieving artificial intelligence on the whole. Well, you might be thinking we are almost there, right? So, we have amazing chatbots, we have very good robots which can go into the war, and, we have robots in medical sciences. And we have machines doing so many things faster than us. So why aren't we achieving artificial intelligence yet? Well, guys, I've covered about this in an entire video, which is what is artificial intelligence, which was my last live session. So I suggest you go watch that video after this video to get the answer to just that. But then you will have to know this point, guys. To achieve artificial intelligence, you have to train a machine to think just like a human being. I mean, in a lot of people, in billions of people's of opinions, a human being is the most evolved, most intelligent species out there. So unless the answer of that changes to a machine, which is the most intelligent thing, right? Sure, it might be faster than a human, but is it the most intelligent thing? Is it self-capable? There's a good side and there's a dark side and so much more. But until we go there, we're going to be still stuck with mathematics and statistics and so many of these concepts on steroids, guys. So basically, you might be wondering where machine learning fits in this entire picture of artificial intelligence. Well, as I've already told you, machine learning is one of the ways we can go about to achieve artificial intelligence, guys. But then you can see the other term, deep learning, as well. Again, deep learning is another subset of machine learning itself, which itself is a subset of artificial intelligence, right? So we have three sets going on. Deep learning being the most internal thing, which is a part of machine learning being a part of artificial intelligence, as you can just check out on the screen. Well, consider this very simple scenario, guys. As humans, let us say, we can pretty much go about doing very simple mathematics, multiplication, right? So let us assume y is equal to 2 and y is equal to 4 is the answer that we know. So the data can be x is equal to 1 and x is equal to 2. So what is the rule that you apply on the data to get the answer? If you can figure that out, then you can pretty much know how that answer came by, right? So if you multiply the x value by 2, it's going to become 1 into 2. So we got the first y value, then x is equal to 2. If you multiply this by another 2, we got the second value, which is y is equal to 4. As humans, we have been trained for a lot of years to do just this. But then now think about the machine's perspective. The machine doesn't know how you can get y is equal to 2, right? There is millions of ways you can bring the value of y to 2, but it doesn't know how to go about doing it. But then you can say that, hey, look, you're going to tell your machine that this is the data that you're going to get and this is the answer that I want. So how are you going to do it? You're going to teach this machine how it is supposed to take that data and come up with the rule and give you the answer. It is as simple as that. So if your machine, let's say you apply machine learning, and at the end of it, if you're right, if you've done it well, then pretty much your machine will tell you that, hey, the rule I applied is y is equal to x into 2 to convert the data into the answer that you required. And this is exactly what happens in machine learning, guys. So basically, to learn the rules which governs an entire phenomenon, machines have to go through this entire process, what we call as learning. And after this, basically, they will try out different rules, different learning procedures, and this will basically govern of how the machines want to perform. Do they want to perform well? Are they performing well? And so much more. And this machine's learning to convert data into the answers that we require. This is why they are basically called as machine learning, guys. And I hope this simplification actually made complete sense to each and every one of our viewers who are very excited, as I can see in the comment section, for the machine learning videos, guys. So again, guys, I want to know your opinion about machine learning, past, present, future, and whatever it is that you want to convey. Please head to the comment section. Let us keep it very interactive, and it's going to be an amazing session, guys. So on that note, the next part of simplification is pretty much the terminology. In case you're a student of machine learning, or if you've ever heard of machine learning in your life, there is a very good chance your friend, your colleague, your superior, someone would go about talking about these terminologies as well. So let me tell you the 3 good terminologies that you should know in case you're interested in machine learning. That's it. So basically, first one is data set, guys. A data set is basically a set of a lot of data. So what does this lot of data mean? Well, at this particular point of time, it might be data examples in the form of a list, or it can be an ordered collections. And this will basically contain features or data or more data, let's say. So this data will contain certain information which is required to solve a problem. This is as simple as a data set can go, guys. And the next thing is features. Well, what are features? Features of a mobile phone, features of a television, we sort of use these to describe the object, right? So you might look at the brand new mobile phone which is launched in the market, and you can talk about all the features of it. So features are description of that product. Again, here as well, features are pretty much the important pieces of information in the data that help us understand, how we can go about solving a problem. Instead of analyzing a product, we're analyzing a problem here. And a data set will have a lot of features, and these features can be used to train your model as well, guys. So train your model. So what does the model mean? Well, the model basically, when you talk about a machine learning model, this model is basically what you can call after the output of the entire process of it being trained, it being learned, and it being ready to use. So that's as simple as it is. So your machine learning model, your machine learning algorithm has learned something, and it can give you a valid output, a correct output. It might be the wrong output sometimes as well, but it gives you an output which you can use, and this is the product of training. This particular phenomenon, after your model is trained, we call this the after the algorithm is trained, we call this the model, guys. And there might be other terms as well, something like losses, something people can talk about fitting, underfitting, overfitting, and so many other phenomenon. People talk about generalization, people talk about normalization, hyperparameters, how you can go about tuning these hyperparameters, and so much more, guys. So I suggest you do not be overwhelmed by the terms in case you do not know what they mean. And that is one of the reasons why, actually having a process of structured learning in machine learning, having to master machine learning, being certified in machine learning adds so much value to your resume, guys. So on that note, what is the exact process of how, machine learning works? Well, guys, we're going to work from the top down, right? So the first process you see, data collection, is step number 1, and then step number 2, 3, 4, 5 as we go down. First step is to pretty much go about with data collection, guys. Well, data collection is pretty much the process where we collect the data through which the algorithm will actually learn. Data can come from your neighbors, the data can come from any data sets, the data can come from Twitter, Facebook, WhatsApp. I mean, you can pick up data from any part of this world, and you can go about collecting it, storing it, processing it in a structured way, guys. So this is data collection. The second thing is data preparation. So all this data you have, right? So it might not be in a very usable, friendly way for a machine to go about using, because a machine is, again, a dumb coded machine by an intelligent human is how I would put it. So you need to prepare this data, you need to format this data, bring it to a point where we can engineer the data into the optimal format that we can go about using, guys. This brings us to the third step. The third step is actually training the process where the machine learning algorithm actually learns. This is the process where the training happens. And then the next process is evaluation. Evaluation is basically where we test the model to see how well it performs, and then at the end of the evaluation we actually tune this model. Now we know where the model stands, so let us tune it to make sure it performs better. If it can do 80%, let us tune it to make sure that we can get 100% out of it, right? When you think about it that way. So next up, we need to discuss the key moments of machine learning, guys. So the first important, the timeline of machine learning started in 1959, guys, because the term machine learning was actually coined by Mr. Arthur Lee Samuel in 1959, guys. So it was, think about it, 1959 is such a long time ago, right? The world was a very different place back then. But then people were sure that, especially Mr. Samuel was sure that the world is going to see machine learning sooner than ever. So he was an American pioneer, and during the 90s, he was very famous for his works in the field of computer gaming and bringing artificial intelligence to the table as well, guys. So him along with other pioneers such as Alan Turing, John McCarthy, and so many more actually came together in conferences, and I've again discussed this in my previous What's Artificial Intelligence video. So they came about and they give us all the terms we see now, guys: artificial intelligence, machine learning, and so much more. And again, fast forwarding all the way from then to 2012, our first machine learning product was Google Brain. Google Brain was basically a deep neural network created by this person called as Jeff Dean at Google, and this person basically created a neural network which could detect patterns in images and videos, guys. And since it was using the resources that the biggest company Google had, it was no match for any of the other small neural network companies to actually compete with, to be honest. But then it was later actually used to detect objects in YouTube videos. And guess what was the first detection made by Google Brain, guys? So Google Brain actually went about detecting an image of a cat in a video, and that's how our machine learning journey started, guys. So on YouTube, we went to go about, the model basically detected a cat successfully. And then from then on, we are doing binary classifications with cats and dogs and whatnot, right? So fast forward to 2014. The amazing people at Facebook created another deep neural network, and they called it DeepFace. DeepFace is basically using deep learning for face recognition, guys. And then Facebook made a claim which the world had never seen before. They claimed saying that we can recognize people with your photos with the same precision as a human being can do. Think about our original terms of artificial intelligence. Achieving AI is basically making a machine think equally good as a human. And that is the same with the Turing test as well. Again, regarding the Turing test, I've covered it in the previous video, guys. So basically, when you think about it, when they claimed it to be this, then it had to be amazing, right? So then again, the same thing happened in the same year actually by DeepMind. Well, the people at Google again said, hey, if you can go about recognizing images, we can go about playing video games against the best professionals in the world. This had already been done by IBM Watson, but then people at DeepMind took it to another level, because in 2016, it managed to beat the world champion at this game called Go. But what is famous in that is Go is considered to be one of the world's most difficult board games, guys. So on that note, we come to 2015. Well, 2015, OpenAI, the foundation, basically it's a non-profit organization, was co-founded by Elon Musk, guys. So Elon Musk is the billionaire entrepreneur person who's heading Tesla, who's heading SpaceX, SolarCity, and so much more. So he pretty much founded OpenAI as well. And the goal to OpenAI was to basically create a safe artificial intelligence platform that can actually benefit humanity, guys. See the highlighted words safe and benefit, because Mr. Elon Musk again has two views about artificial intelligence, and one of it is the negative aspect where he thinks that artificial intelligence might turn out to be bad at the end of it. But then hey, it's his opinion and we need to respect that. But again, I've covered all of this previously, guys. So this brings us to the perfect Go example that we just spoke about, guys, because again, when you think about it, in 2016, AlphaGo basically became the computer Go program which beat an unhandicapped professional human player. So this professional human player was the world champion multiple times, and it beat it like there is no tomorrow. I mean, to say it a little informally. But then this was done using basically a lot of machine learning techniques and a lot of tree searching techniques as well, guys. If you do not know what tree searching techniques is, you do not have to worry, guys, at this point of time, because again, when you come to think about it, AlphaGo actually went another step ahead, and it went to be generalized to the world of chess as well. And there's something called Alpha Zero now, which concentrates on many more two-player games where artificial intelligence brings its best and challenges the best human beings across the world, guys. So this brings us to the algorithms. What do you think is the need for something called as an algorithm? Well, consider this situation, right? So let's say you're either baking a cake or you're driving your car, you're even walking or singing. Well, your body is continuously executing the set of steps that you have already trained it to do, and then this is what we call as an algorithm. So basically, when you're driving your car, your brain is already programmed to do all the tasks that are required to pretty much help you to drive your car. And then when you're walking as well, how do you maintain balance? Well, as a kid, if you could realize that maintaining your balance as a toddler was very difficult, but then you trained yourself every day, and then now you can walk very easily, right? So this process, which involves learning and then this repetitive process, is again pretty much can be termed as an algorithm as well, guys. Well, if you've been wondering if algorithms are new concepts, well, they're not. Algorithms have been used for decades together. Well, back to this person on the screen called Alan Turing. This person, here's a good fact, this person was the reason probably why World War II ended. He was the one who decoded the very famous encrypted Enigma messages from Germany, and then this person decoded it, and then and all the code breakers and so much more, right? So the entire point here is to tell you that algorithms have been used, is an age-old tradition that's being used, and these days we've been pushing it to our computer science field as well, and then making sure that we make full use out of it, guys. And then again, why would we require it? Well, think of the huge amount of data that's being generated these days, and then think of the methods that we need to process it, to understand the data, to process the data, and then to pretty much clean up the data and work with it, right? So for all of these, we have something called as algorithms, guys. So on that note, what are algorithms? What is the formal definition of an algorithm? Well, guys, algorithms are as simple as this. They are just a set of rules, or you can call them as processes as well, to be followed in calculations or any other problem solving operations when done by a computer. Well, how simple is that? Well, this is exactly what an algorithm means. Well, you have a symbol on the left hand side. That is pretty much what a flowchart looks like as well. Don't worry, you'll just be checking out the flowchart sections in the next set of this slide. But then right now, I want to tell you guys that you guys are using algorithm as is. Well, step one, you're looking at your screen. Well, you've programmed yourself to look at the screen. That's an algorithm. And YouTube is running a recommendation algorithms where you just, let's say you search for something, Python tutorials or anything for that matter, right? Intellipaat's videos are up there. So how does YouTube know that, it should recommend Intellipaat's videos to its learners? Well, again, an algorithm is being set there. And every time you check your mails are filtered in your inbox, in your spam folder, and so much more. So how does Google or Gmail know what mail is a spam mail and what mail is not a spam mail, right? So that again is an algorithm right there. And no matter what operating system you're on, Windows right now, or let's say iOS, let's say Mac OS, Android, whatever, right? So all these operating systems are using algorithms right now. On that note, we need to check out what the types of machine learning are. So we have three main types of learning which happens when we talk about machine learning, guys. It's supervised learning, it's unsupervised learning, and it's reinforcement learning, guys. So if I were you guys, I would just suggest you guys just take a minute, pause on the slide to note these three types of machine learning, guys. So supervised learning, unsupervised learning, and reinforced learning. If you're already familiar with the concepts, or if you think that you got it in the bag, well, let's move ahead to check out what supervised learning actually means. Well, supervised learning, as the name suggests, requires some sort of supervision, right? Let us talk in terms of variables so we can understand it easily. Again, in supervised machine learning algorithms, let's say we have input variables and our output variables. These input variables are denoted by x and the output variables are denoted by y. So x is input, y is output. The goal of any supervised learning system is to understand how your output variable y changes with respect to the change made in terms of x, guys. So how does the output variable y vary when we go about playing with our input variable x is pretty much the goal of supervised learning system, guys. And then here we'll also be approximating the mapping function to a point where we'll have new input data coming in which we haven't seen, which the machine hasn't seen, and then we can predict new output variables y with respect to all the new data, the new x data that the machine just saw. So we've trained it for a particular amount of x's, and then it saw a new amount of data, a new amount of input variables, and then it trains itself to pretty much give us new y output values, guys. So how cool is that, right? And then we need to also know that we have dependent variables and the concept of independent variables, right? And our aim here is to pretty much understand how our dependent variable will change with respect to one independent variable. So we have a couple of dependent variable which goes hand in hand with the variable what we call as the independent variable. And then we need to understand what are the changes that goes into these dependent variables when they are mapped across and compared with respect to our independent variables, guys. Just to make sure that you guys are getting the concept out here, here's a very simple example showing you the same. So again, here our independent variable in a particular case is, let's say, our gender of the student. We have a girl and a boy here. The dependent variable can be the outcome of the educational qualification of the student. So let's say if the student either passed an examination or failed an examination, this becomes our dependent variable. So the independent variable is our gender. The dependent variable becomes the output of what the student is trying to do. And at the end of it, what we're trying to do is basically trying to determine whether the student would pass the exam or not based on the person's gender. Let's say we are doing a survey where we need to find out how many girls have passed or how many boys have passed. Here again, the gender becomes the independent variable, and all of that depending on it in our particular case is the outcome. The pass or the fail becomes dependent, right? So here again, we're trying to find out if the student would pass based on the gender or not. So the dependent variable would pretty much here be again, as I've already been mentioning, it's going to be the outcome, and the independent variable is going to be the gender, guys. So do we have anything more in terms of supervised learning? Well, yes, guys. Here is more classification with respect to supervised learning is we have something called as classification and something called as regression. Let us quickly check out what regression is, and then we can come talk about classification, guys. Well, regression is a type of supervised learning where the output variable is a continuous numeric value. So what do we mean by a continuous numeric value, right? So let me again take another quick example to make sure you guys understand this better. I have images of two apples for you guys. One apple costs $4, the other apple costs $3. Here the output variable is the cost of the apple. It is a numeric value, which is a continuous value. You can predict it, right? Is the apple ripe? If it's yes, then it's costly. If it's not yet ripe, then it's cheap. Well, is it a Shimla apple? Is it a Kashmiri apple? Is it a Washington apple? Well, you can pretty much go on adding so many factors around this apple and then come up with one particular outcome out of it, which would be the price, right? So the price depends on all of these factors. And in our case, the price is the output variable. So we're trying to predict the cost of the apple with respect to all these other factors, right? So again, doing this in a real world or in a mathematical situation, and in this situation, pretty much we call it as regression, guys. So with respect to regression, again, there is another type of regression, which what we call it as the logistic regression. And this is basically just a technique, where our dependent variable, instead of it being a continuous numerical value, it is a categorical value, guys. So again, what do we mean by this? Time for an example. If you can take a look at the example on your screen right now, what we're trying to do is we're trying to predict whether if it's going to rain on that particular day or not. And this is being done with respect to two independent variables, right? So how do we check rain? Again, pretty much it's usually done by checking the temperature, checking the humidity. And if all of this is good, we probably just go out, take a look at the sky to check for clouds and so much more, right? And here, coming back to logistic regression, the dependent variable is the categorical variable, right? So it can have only two values. A categorical variable can only have two values. It is mostly binary, guys. So it's going to be either 0 or it's going to be 1. And in this logistic regression model, what we call it, depending on all of these attributes, we get the probability our final answer is going to be either yes or no, right? So if you ask someone a question, is it going to rain, their answer might be either a yes or a no, right? So it's a binary answer. Again, here it's the same as well. To pretty much to graph out what it would look like, we have an S-shaped curve out of this model, what we call as the logistic regression, guys. So on the left, we have a linear relationship between our dependent variables and the independent variables. It is just a straight line. On the right, since it's a binary value, binary outcome that we're looking at, the curve looks like an S. So again, guys, take a moment, pretty much pause on this slide to understand what a linear regression graph looks like versus what a logistic regression graph looks like. So on that note, let us quickly come back to check out the next subdivision under supervised learning, which is called as classification, guys. You pretty much, as the name suggests, you might already know what classification means. In literal terms, well, again, classification, here the output variable is categorical in nature. So again, it's going to be a binary value. So you can just have a look at the picture on your screen, and then we can categorically analyze if that person is a male or a female, right? So here the binary outcome is again the gender of the person, if the person is either a man or a woman. And then again, the output variable is the gender of the person, which is a categorical value, and we're trying to classify this person into a specific gender, based on all the other factors as well. Well, how do we know it? Well, we could see the beard on the face, it looks like a man, so our brain pretty much told us it is a man, right? Simple as that. So on that note, we've pretty much checked out what supervised learning is. So what is unsupervised learning? Well, guys, in unsupervised learning, here all of the algorithms that we have, right? We have input data which has no labels. So when we mean that the data does not have any labels, then there is nothing that the machine can map to understand the data offhand very easily. So we can take a look at the raw data ourselves, right? So we can probably tell that there's a couple of fishes in there, there's a couple of birds in there. Well, we know it because we have trained ourselves for that. When the machine sees this, there's not going to be any label which is going to tell that this is a fish or this is a bird. So our unsupervised learning algorithm is pretty much going to run through this again, and at the end of it, with respect to clustering, what we call is the process of clustering, it's going to divide all the fishes for us, divide all the birds for us on its own. So here the input data has no input labels, has no class labels, and it doesn't know what's a fish and what's a bird, right? So again, building a supervised unsupervised model on top of this input data is again very interesting and very fun, guys. So here again, it's going to pretty much be giving out two clusters. First consists of all the fishes, and second consists of all the birds, guys. So coming to clustering, which is again a major part of unsupervised learning, the most important clustering algorithm, the most simple one, is the k-means clustering, guys. Well, k-means clustering again is an unsupervised machine learning algorithm where the aim is to pretty much go about grouping all the similar data points, just like fishes and birds, and making it into one cluster, guys. So again, there must be a very high intra-cluster similarity and low inter-cluster similarity out here, right? So what do we mean by that? Well, all the data points within a cluster should be as similar as possible, and all the data points in between two different clusters must be as different as possible. So all the data in one cluster is simple and similar. All the data when you compare two different clusters are very different to each other, right? So this is pretty much the k-means clustering in just a sentence, guys. Well, what does the k stand for in the k-means clustering, right? Well, k is the number of clusters that you just want the outcome to be. In our particular case, we have cluster A, cluster B, and cluster C. So the k value here is 3 because we have 3 different clusters, right? Very, very, very simple as that, guys. So on that note, the next type of learning that happens is what we call as the reinforcement learning, guys. Again, in reinforcement learning, there is something called as an agent. And this agent pretty much runs up and returns up most effective actions for us by mapping its state at every single moment, guys. So to give you a better clarity, I hope you guys have played Pac-Man in your olden days, guys. So in this particular video game, the space around the figures would what we call as the 2D game space. Again, you have something called as pack dots, you have enemies, you have walls, and so much more, right? So the action here is to again just pretty much move around and make sure you don't touch the bad guys and just finish your entire goal. Here, how do you know what the who the good guys are and where you need to move and how you're not supposed to get out every single time, right? So that particular thing, you've been playing this game for a while. Let's say you've been playing this game for a couple of hours, couple of days in your childhood, and then you realized how the game actually works. Well, that exactly is reinforcement learning, guys. Again, to give you another example, reinforcement learning is pretty much how a dog or a cat is trained in its real life as well. If the dog does something right, if the dog is given a handshake, let's say we're training a dog to give a handshake.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
And then if the dog is given a handshake, you might see that the trainer just feeds a biscuit that instant, right? So the dog knows that the outcome of giving a handshake is pretty much the right thing to do because there is a biscuit at the end of it. So the reward is being hunted by the animal, right? So again, to put it all in one single picture, this is what a reinforcement learning environment would look like, guys. So we have an agent who performs an action in an environment, and then here we can actually have two tracks where if the agent does it right, if the task is being performed right, there is a reward with respect to it and everyone's happy. Else, if you do not have that particular reward, then it means that something went wrong, and this will have a state. Because something went wrong, you're eventually not getting the reward. Let's say the dog did not give you a handshake, or if you pretty much give it a biscuit at that moment, it will not realize if it's doing the right thing or the wrong thing, right? So that we can have a state of, let's say the dog did not give a handshake, and that's pretty much what ST means, guys. Reward is RT, and this keeps on going in an iteration where you're just training your model better and better and better to hunt more rewards. The more the rewards, then the machine's doing the right thing. It's as simple as that, guys.
Let's talk about machine learning. We are going to cover only machine learning in the upcoming sessions also. What is machine learning? Okay, machine learning is simply nothing but theoretically ability of machine to behave in a certain way without being explicitly programmed. Fine. Okay, ability of a machine to behave in a certain way without being explicitly programmed. This is a theoretical definition of machine learning. But let's understand what is machine learning in simple terms. First, if I take any action in a computer, for an example, I'll right click on this desktop and it opens me a pop-up. It opens or throws me a pop-up. In this pop-up, I can take an action. Now, this is a programmed action, correct? If the programmer has not written the piece of code saying that, if the user says right clicks on the Windows Explorer, open this pop-up won't appear, correct? So everything within a machine, within an electronic device is a programmed action. But what machine learning does is, machine learning will simply take data as input. Okay, machine learning will simply take data as input. It will not take any programming language. It does not require any programming. It takes data, then it will supply a logic. The logic is machine learning algorithms. Based on that, the data will behave in a certain way. Okay, for an example, behavior is simply nothing but patterns. Okay, the data might be like this, but after applying the logic, the data will behave in a certain way. Here, for doing this, I don't want programming. I don't want to program a software to do this. I will just use programming language to implement the logic, but I'm not building a software. Okay, so for machine learning is simply the ability of our computer to behave in a certain way without being explicitly programmed. We don't have to create a software, as I said. We just need to implement the logic with the help of programming language. Actually, we don't even need programming language to implement it if we are using different tools. I use Alteryx for performing data analysis, predictive analysis. I also use Excel to perform predictive analysis. In those cases, programming language does not come into picture at all. Just because we are using Python, we don't have to get confused with programming language. As I was saying, we are not building softwares to achieve this. We will just be supplying different logics to expect the data to behave in a certain way. Let me plot a scatter plot. Now see here, this is exactly what machine learning does. This is how our raw data was looking like. Okay, this is how it was distributed, quantity and sales. Okay, Now I have supplied a simple logic, and when I supplied a simple logic, this particular data is now behaving in this particular way. I did not use any programming language. I did not use any software. I did not build any software to achieve this. I had data, and then I supplied a logic on top of the data, which helped us to generate a pattern. This is called as a behavior. This is what machine learning does. We will jump into each and every algorithm that we will be learning, and we will see how each and every algorithm behaves, what are the patterns that it follow, and how does it follow the pattern, and all those things step by step. But the point here is just to understand how ML works. ML simply works, as I said, it is just the ability of the program, ability of the machine to behave in a certain way without being explicitly programmed. Okay. Now there are two ways of learning. Okay, there are two ways for learning in machine learning. The first one is supervised learning, another one is unsupervised learning. There are two types of learning in machine learning. One is supervised, another one is unsupervised. There are other types also, but we are going to focus only on these two things. The machine learns in two different ways. One is supervised learning, another one is unsupervised learning. Okay, how do we differentiate between supervised and unsupervised learning? Supervised learning means if we know our target variable, I'll explain what is the target and independent variable, and works with labeled data, works with unlabeled data. X is independent variable and Y is our target variable. It's also called as dependent variable. Fine. Now, going forward, anytime I mention X means it's an independent variable, Y means it's a target variable. What's an independent variable? What's a target variable? Now see here, I want to predict sales. Machine learning is purely predictive. Okay, even data science is purely into predictive analysis only. It will only predict something based on something. Okay, now I wanted to predict sales, the value of sales based on quantity. Okay, because I cannot predict sales based on, sorry, I cannot predict quantity based on sales, right? But I can predict sales based on quantity. Here sales is actually my target variable. Okay, sales is my target variable because I'm going to predict sales based on quantity. Now whichever variable that I use for predicting my target is actually my independent variable. Why? Because quantity is not determined by sales, right? Various sales is determined by quantity, correct? Sales is an dependent attribute. If only I sell more quantity, sales value will increase. If I sell lesser quantity, the sales value will decrease. Okay, sales is dependent on quantity, whereas quantity is not dependent on sales. So quantity is the independent variable and sales is my target variable. So in a nutshell, the column that I wanted to predict becomes my target variable. The columns that I use to predict my target variable is called as independent variable. Independent variables are denoted by X, whereas target variable is denoted by Y. Throughout machine learning, we will be predicting only one value. Okay, so our target variable will always be only one. It can be either sales, profit, pass, fail, or anything, but we will be predicting only one outcome. But we can use multiple independent variables to predict that behavior. Okay, so X is independent variable and Y is target variable. Fine. So supervised and unsupervised. Okay. Now in this case of predicting sales by quantity, I know what I need to predict based on what. I know my target variable. My target variable is sales. So whenever I know my target variable, it becomes supervised learning. But in some cases, we will not know what is our target. In those cases, it becomes unsupervised learning. An example would be, let's assume we have a supermarket owner. The supermarket owner issued 1,000 coupons to 1,000 customers who visited the shop last month. Out of the 1,000 coupons that he issued, only 20% of the coupons was redeemed by the same customers next month. 80% of the people didn't turn up. 80% of the people did not use the coupon. What can be the reason? Okay, people did not turn back and redeem the coupons. 80% of the people did not even use a coupon. What can be the reason? So if I wanted to predict the reason, I do not know what will be my reason, right? So in those cases, I do not know my target variable. I do not know what I wanted to predict only. Okay. In those cases, if I wanted to perform an analysis and try to resolve the problem, they become unsupervised learning because we will not have any target variable. Okay. That becomes unsupervised. If I have a target variable, it becomes supervised. Now labeled and unlabeled data means, now I know this is sales data and these are the sales value. I may have the customer ID, customer name, mobile number, and all the information related to the sales column. Okay. If I have complete information about my sales, it becomes labeled data. Labeled data means you cannot confuse this with column headers. Even unlabeled data will have column headers, but it will have incomplete data like this. This is actually incomplete data because we do not know how these 67 quantities were sold, in which place it got sold, what are these 67 quantities, in which date it got sold, what is the price of the product, nothing. I don't have any information with regards to my quantity. Then it becomes unlabeled data. If it is labeled data, I will know everything about the data. Let me just open an example for you. Okay, if I don't have data, I cannot predict only, right? It is like I cannot predict the weather condition based on the number of samosas I sold today, correct? Weather has nothing to do with my business, but I can predict the number of ice creams that got sold if it rains today, or based on the weather condition, correct? So if I'm trying to predict something, I should use the variables that are useful to predict that variable. Okay, but if you see this data set, okay, look at this data set. This data set literally contains everything. This is the order ID, order date, shipment date, what is the shipment mode, which product, which place it got sold, what is the sales value, quantity, discount, profit, everything. I basically have literally every information about the particular sales value. So this is actually labeled data, but if I have incomplete information about the same table, it becomes unlabeled data. We will use supervised learning for labeled data and unsupervised learning for unsupervised learning.
Amazon is saying, identify and tell me what will be my sales in the fourth quarter. Now, in this case, what are we going to predict? We are going to predict sales. We know that very clearly, right? Because the target is predicting sales. We can use multiple independent variables to predict sales. I can use quantity. I can use the product name, product category. I can use the location of the product being sold. Basically, I can use a lot of independent variables to predict the sales of a business, sales that will happen in a business. In this case, since I know my target variable, this particular concept falls into supervised learning. If I have to solve this problem, I have to follow supervised learning to solve this. On the other hand, let's take a different example. Supermarket. Okay. The supermarket example is, assume you're an owner of a supermarket where you issued 1,000 coupons to all the customers, 1,000 customers that visited your shop last month. Okay, 1,000 coupons for 1,000 customers. Now, out of the 1,000 coupons that you issued, only 20% of the people redeemed the coupon. Rest 80% of the people did not even bother to use the coupon. What can be the reason here? The reason can be anything, right? People might have migrated from one place to another place. There might be heavy rain, so people don't want to go to supermarket. They might want to order everything in online. There might be a very fashion sale that happening in the online market where you will get everything for cheap. So there can be any reason. The point is, if I have to understand what went wrong in this business use case, there are a zillion reasons, right? But we need to find something in some information through the data that we have. We have just the purchase data of 1,000 customers. We just have their mobile numbers. That's it. Now, how can I actually extract useful information from this and take an action upon that? Since I do not know what needs to be predicted, I'll just go with unsupervised learning in this case, because there is no target. I don't even know what to predict, but I know some action I have to take. So I need to extract useful insights from this. Okay, these are two examples for supervised and unsupervised learning. Now I said in supervised learning, there are two techniques. One is regression, another one is classification. This is clustering, my bad. In unsupervised learning, it is called as clustering. Okay, it is not classification, it is clustering. What is regression? What is classification first? Now, regression in simple terms is a technique that will help us understand the relationship between two variables. Okay, this we have seen in Pearson's correlation coefficient, right? Pearson's correlation coefficient will simply tell us the relationship between two variables on the scale of -1 to +1. That's pretty much what it tells. But regression, it will help us understand the relationship between variables. Along with that, we will be able to predict a variable's particular value when my independent variable is at a certain value. For an example, let me give an example. I wanted to know what will be the amount of ice creams, okay, amount of ice creams that I'll be selling if it rains for 2 hours. Rains 2 hours. Okay, now my independent variable is rain data. My target variable is predicting the number of ice creams that are being sold. Okay, so in this case, regression techniques helps us to identify relationship between two variables. Both the variables must be quantitative. Okay, you cannot take a categorical variable and predict the relationship. Both the variables must be quantitative, the numbers basically. And also, if I wanted to know the behavior of my target variable upon a value of my independent variable, that is also doable with the help of regression techniques. That is another important reason that we will use regression. But when will I identify? When will I know? When will I know I should take regression? I should perform regression models. When will I know I should perform classification models? I'll explain them now. Let's take in supervised. I was talking about regression, so let's take regression first. Regression, classification, and clustering. Okay, regression, I said relationship between two variables, two quantitative variables. Okay. Now, in this case, when will I choose if a particular business problem is given to me? Will I choose a regression model or a classification model or a clustering model? When should I choose what type of models? So in supervised learning as well as in unsupervised learning, we are going to learn about different machine learning algorithms. Machine learning algorithms are also called as models. Okay, they're simply nothing but models. Each and every algorithm is simply nothing but set of logics that we will learn. Those logics, when applied on a data, will make the data to behave in a certain way. We are just going to learn about the behavior in different models. Okay. Now in regression, when will I choose a regression model? As if my target variable is continuous and infinite. Okay, target is infinite. Let's keep infinite. Target is having infinite possibilities. Now, what do I mean by infinite possibilities? Let's take the same Amazon example. I wanted to predict the sales for 4th quarter. Correct. Now, if I am predicting the sales value for 4th quarter, what can be the sales value? The sales value can be anything, right? It can be 350 million. It can be a loss of 110 million. It can be 1,125 million. Basically, the sales value can be anything. Okay, it has infinite possibilities. The outcome of my prediction has infinite possibilities. In those cases, we will go with regression problem. But in classification, we will try to predict the possibility of an outcome. Possibility of an outcome. Basically, probability. What we are going to do is we are going to identify the probability of a particular event to happen or not. Now, if in this case of classification, there are only limited or finite outcomes are possible, right? For an example, if I am writing an exam, what are the possibilities of the result? Either I can pass in the exam or I can fail in the exam. Okay, when I have limited or finite possibilities, then it becomes classification problem. Regression works in continuous data. Basically, it can have numbers which can be measured. Here in classification, it works with discrete data. It will work with countable numbers only. Okay. This is measurable data. This is countable data in simple terms. Okay. Now, in classification, I was talking about possibility of an outcome limited. Okay. If the possibility is only two, the example that I gave us, if I'm writing an exam, what are the possibilities? Either I can pass or fail in the exam. True or false, yes or no. Only two possibilities. If I have only two possibilities, that type of classification is called as binomial classification. Okay. It is called as binomial classification if the possibility of the outcome is only two. Yes, no, true, false, pass, fail. But if I have more than two, but still limited possibilities, then it becomes multinomial classification. For example, if Gautam passes the exam, what are the possible grades that he can score? A, B, C, D, S, O, something, right? But here the possibilities are more than two, but still limited only. It is not infinite. I have 4 or 5 possibilities here. Since it is more than two possibilities, it is called as a multinomial classification problem. So based on the problem statement given to you, problem statement is simply nothing but the client's requirement. The client will come to you, the client will ask, see, Prem, I want you to identify what is wrong in my business. I am trying to retain my employees but my employees are not getting retained. So in this case, it's a classification problem because we wanted to predict whether can we retain the employees or not. Only two possibilities. Either the employees can be retained or they cannot be retained. Only two possibilities, right? But on the other hand, the client is asking, see, I want to build a machine learning model, which will help me to predict the price of the cars that I'm going to sell in the market. Okay. I don't want to calculate the the price of the cars manually. I want the model to tell me what will be the optimal value for my car prices. Okay. Based on different features, based on the number of seats, based on the number of engines that the car has and all those things. Okay. But based on properties, ideally. In those cases, we will go with regression techniques because the car price can be anything, right? It can be the cars can be sold from 1 lakh till all the way till 1 crore, 10 crores also, right? So the point is it becomes a regression problem. These are pretty simple and straightforward because these are supervised learning. In majority of the problems that we will work with supervised learning only. In very few cases, we work with unsupervised data. In unsupervised learning, we will use there is only one type of mechanism that we have, which is clustering. What does clustering does is, now let's go back to the same supermarket example. In supermarket case, we gave coupons to 1,000 customers, but only 20% of the people redeemed it. So there is clearly some issue with the coupons that has been issued. Other which ways, more people might have used it. Now, what might be the issue? Since the issue can be anything, right? Increase in petrol price might made the people not to travel to a supermarket, might order everything in online. There is a better offer going on near store. There might be a heavy flood or heavy cyclone. So there can be both internal and external factors impacting people from not coming to the supermarket, right? We cannot control every factor, right? If it is rain or fuel prices, how can we control? As a business owner, we cannot control those external factors. So what is the right thing, or what is the only possibility that we have as business owners to make use of the data that we have? We have 1,000 customers, phone number, and the shopping purchase, right? Now you go to any shop, they'll give you a bill, right? They'll give you a bill of whatever that you have purchased, the total amount, and they'll also get your number, right? So these are the only two data that the supermarket owner has. So the owner has to utilize this data to take an action that will enhance the conversion from 20% to something else. How it can be done? It can be done by grouping the customers based on similarities. Now, as a business owner, what I did, I gave 1,000 coupons, but all the 1,000 coupons to 1,000 customers, but all the 1,000 customers received the same coupon only, generic coupon, like 10% flat offer. You purchase anything, 10% flat off. Every customer might have received the same coupon. Now, if you group the customers based on their shopping behavior, customers who are purchased between $0 to $100 will be group 1. $100 to $500 will be group 2. Anybody who purchased above greater than $500 will be another group. Once I group the customers, then I can specify different coupons, or I can produce different discounts based on the group. If you purchase less than $100, you will get $10 cash back. If you purchase anything between $100 to $500, 10% cash back. If you purchase anything greater than $500, 25% cash back. Now, if you target the customers based on the shopping behavior, the conversion will be increased, right? Rather than giving generic coupons, if you target the customers based on the shopping purchases and target them, obviously the conversion will increase, right? So clustering simply helps us to group the data based on similarities. Clustering can also help us to group the data based on dissimilarities, but the use cases for dissimilarities are extremely rare. So the general use case would be grouping the data based on similarities. That is done by the help of clustering. These are the 3 different mechanisms that we are going to learn in the coming sessions as well. And we will learn each and every model under different mechanisms, under regression, classification, and clustering. Let me just point out the models that we will be learning. We will be learning each and every model separately. Forgive my handwriting. Regression, classification, and clustering. There are multiple algorithms. We are going to come. There are at least thousands of algorithms, but we are going to learn the most critical and important ones. In regression, we are going to learn simple linear regression, multiple linear regression. These are algorithms. In classification, we are going to learn logistic regression. We are going to learn about naive Bayes, random forest, decision tree, k nearest neighbor. In clustering, we are going to learn about k-means clustering, hierarchical clustering, That's it. So these are the algorithms that we are going to learn. Simple linear regression, multiple linear regression, logistic regression, naive Bayes, random forest, decision tree, KNN, k-means clustering, and hierarchical clustering. Now, after learning all these algorithms, finally, we will be learning a new technique called as dimensionality reduction. Okay, where we will be learning about 2 algorithms, PCA and LDA. Sorry, we will also be learning about market basket analysis here. Market basket analysis over there. It's called as a priori algorithm. This list of algorithms and all those things are in your notes, so you don't have to worry about notes. You have to just remember or just know that what we are going to progress. It will be helpful just knowing that. No, we are not going to learn any nonlinear algorithms. There are actually nonlinear algorithms also, but we are not going to learn all those things. Okay, is it classification or clustering? It is clustering only, I think I rewrote it. Okay, perfect. Because we are done with the introduction to data science, we are going to jump into build models and implement them in Python. Okay. In the introduction to data science PPT, you will have all the detailed documentation of everything that I just explained. How will you, choose a data model? How will you have all those things? It is detailed as documentation. You can refer to the theoretical portion of it. But let's jump into the model building itself. Now, let's talk about linear regression. Okay. First, before understanding a linear regression, we must understand certain terminologies. Okay. I'll give you an overview of how everything works. In the process of explaining them, I'll also teach you certain terminologies. Now, at a very high level, what we will do is we will take data.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
We will say in this data, basically before saying, we will perform data cleansing, most important step. Once we perform data cleansing, we will normalize the data. Okay. Then we will split the data. Then we will build the model. Using the model, we will predict the values. Machine learning is purely predictive analysis only. Using past data, we are going to predict what will be the value for a new value, new data point, future data points, basically. Okay. Now, in this case, certain terminologies that we must keep in mind are, in splitting the data, when I say splitting the data, we will be splitting the data into X and Y. If I have multiple columns, I'll have to tell what is my Y variable and what are my X variables. Always remember, we can predict only one target variable. Okay, the target variable will always be only one, but independent variables can be multiple. Okay, this is a rule. Target variable is Y, independent variable is X. Okay, predicted variable. Now what we will do is, we will use independent variable and target variable from the past data to predict the target variable for the future data. Okay, so basically I'll have quantity and sales of my past data, and then I'll use new quantity value to predict the sales. Okay, the predicted data is called as Y hat. Okay, it is denoted as Y hat. The past data, the past independent variable is X, the past target variable is Y, the predicted target variable is called as Y hat. Okay, it is denoted by Y hat. Fine. Now, these are just different terminologies here. Here, in splitting the data, another thing that we will do is, we'll split the data into two important pieces: train data and test data. Okay. Now, if you see this entire model, the idea of this model building, it will be very similar to what we have learned in schools. In schools, the teacher will come and teach you different topics, correct? First, the teacher will teach you. Then the teacher will give you assignments or homeworks. Once you are done assignments or homeworks, you will be given tests, correct? You will be asked a question from the topics that the teacher asked, correct? Once you perform test, the test will be evaluated. Okay. If you are not performing well, you will be optimized. Optimized as in, you will be asked to retake the test again, give a different homework, and then the teacher will ensure you will give another test, and then the process continues, right? Unless and until you score good marks, they're not going to let you go. There's the same thing here. We'll take model, perform model building, predict the values. We'll also perform optimization. Optimization is tuning the model. Not every model will be giving you the correct results. So we will try to tune the behavior of the model and try to generate better results, but hyperparameter optimization. But in this case, all we are going to do is, we will supply data. In that data, there is some information. We are expecting the model to extract that useful information and hidden patterns and replicate the same pattern for the future data. That's all we are planning to do. Okay. Now, what is train data and what is test data in this case? Now, I have quantity and the sales. 10 quantities, $100. 20 quantities, $200. Okay. This is the data that I have. Using this data, I'll build a model. Okay, building a model is simply nothing but training the model. Training the model is simply nothing but telling the model that, see, for this data, for this particular independent variables value, the target variable is behaving like this. Try to understand what is happening behind. Try to understand what is the pattern behind. That is what training the model does. Now, the model says, see, I have learned the pattern. Okay, the model says I have learned the pattern, but we cannot believe the model, right? So what we'll have to do is we'll have to test the model, correct? If I have to test the model, I cannot supply the same questions, right? If I say, tell me what will be the sales for quantity is equal to 10. Model will simply tell 100 because we have already gave this question and answer, right? We said the question is 10, the answer is 100. If while you are conducting the test also, if you supply, tell me what will be the value for 10, it will obviously give me the correct answer. So what we will do is we'll introduce new values. We will ask what will be the sales value for the quantity 25. This 25 has not been used while we are training the model, correct? So this 25 is actually called as test data, and this 10 and 20 is actually our train data. Train data is simply nothing but the data that we use to build the model, and test data is simply nothing but the concept that we use to test the model after the model is built. Okay, the test data will not be used while we are training. It will be completely new data. Okay, we will be supplying new data to test the behavior of the model. That's called as test data. Okay, so in general cases, the client will not give you train data and test data. Okay, they'll give just only one data set. What we will do is we will split the data into two parts: train data and test data. We'll generally keep 70 to 80% of the overall table for training, and the remaining 20 to 30% for testing the model. Okay, so this is how we will structure the model building. When I'm explaining this in Python, it will make absolute sense, but I'm believing you have understood the theoretical idea behind train and test data. Please repeat target variable and independent variable. Okay. Now, let's take the same example. Through quantity, I wanted to predict sales, correct? Now, what am I supposed to predict? I wanted to predict sales. The variable that I am predicting is actually called as target variable. Now, how am I predicting sales? I cannot predict sales blindly, right? I need some information to predict sales. So that particular information is supplied by quantity. Okay. So the variables that we use to predict the target variable is called as independent variable. Okay. I can use multiple independent variables to predict my sales. Okay. Because sales is not just defined by quantity, correct? Sales is derived by product category, the product name, the quality of the product, the reviews, and multiple other things. Okay. So again, if you see it in a logical way, sales is actually dependent on quantity, correct? Because sales cannot be generated automatically, right? Only when I start selling quantities, the sales value gets registered. If there is no quantity sold, there is no sales. So basically, sales is dependent on quantity, whereas quantity is not dependent on sales, correct? So sales is called as dependent variable. Quantity is called as independent variable. Dependent variables are also called as target variables. Let's move on to the first model. Okay, the first model is linear regression. Okay, linear regression. What is linear regression? Now, before talking about the logic behind linear regression, let's understand the history behind linear regression. This particular algorithm is called as father of algorithms because this was the first man-made algorithm, and it was invented in somewhere around 1960s. This was actually formulated in the 1960s, but it was put into a machine in the early 1980s somewhere. But since this was the first man-made algorithm, we call this as father of all the algorithms. Almost all the algorithms that we have today will have some or the other resemblance to linear regression, to some or the other way, at least in assumptions or in the way it behaves or something. So understanding linear regression is extremely critical in almost all the interviews that you will give, okay, for the role of data scientist. The first question will start with linear regression, okay. Without linear regression, there will be no interviews. So knowing this algorithm is extremely critical. Now this is just the introduction to linear regression. Let's see what is linear regression in the first place. Linear regression is a regression analysis. It's a regression analysis, falls in the supervised learning category. Now, what does regression analysis does? It helps us in understanding the relationship between two continuous variables. Now, talking about the other property of linear regression, since it actually helps us in understanding the relationship between two continuous variables, in simple terms, this can be explained as change in variable 1. In simple terms, this can be explained as change in variable 2 explained by change in variable 1. Okay, what am I saying is, I have quantity and the sales. Okay, if my quantity is 1, my sales is 10. If my quantity becomes 2, my sales becomes 20, right? Now there is clearly a pattern in this. Sales is 10 times quantity, correct? This is the pattern that we can visibly understand. Now linear regression will simply help us understand whether there is any relationship between two numerical variables or not, and it will also explain us to what degree my sales variable will change if I change my quantity variable. To what degree sales can change when I change values in quantity column is what we are going to understand through linear regression. What we are going to see now is simple linear regression. Simple linear regression is simply nothing but using only one independent variable to predict one target variable. I'll not be using multiple independent variables. I'll just be using only one independent variable to predict one target variable. The same example, using quantity to predict sales. This is pretty simple, right? This is the idea behind linear regression. But what is what I would say, what is the technical explanation to this? How does linear regression work and identify whether there is any relationship between two continuous variables, and help us understand the change explained in variable 1, variable 2 by variable 1. Now, let me close all these things. Linear regression, any algorithm that we will see, okay, not just linear regression, any algorithm that we will see will follow a pattern, okay. Machine learning is all about building a pattern from the data, identifying a hidden pattern or trend. Now, what is the pattern that linear regression follows? It follows a straight line, okay. Straight line is nothing but linear, okay. That is the pattern that it follows. The straight line can be like this, the straight line can be like this, the straight line can be like this. It can be any in any direction, okay. It can be inclining, it can be declining, it can be constant, but it should be a straight line. Linear regression does not bother about different trends. It tries to it will try to explain the change in variable 2 with variable 1 in a straight line, okay. That's why it is called as linear regression. Now, what is the straight line? What is the straight line? This straight line is called as line of best fit, okay. I'll explain what is best fit with different examples, but for now understand line of best fit. What is the formula for line? In max, line is defined as y is equal to mx plus c. Now, this is what we are going to use as logic to predict the sales using quantity. Now, what are the variables that we are having here? Y, m, x, and c. What is y? Our target variable. What is m? Slope of the line. What is x? Independent variable. What is c? Intercept of the line. Now, whenever we are building the model, we have both X and Y. We have the data, right? So we don't have to don't have to create this, but we need to identify the slope and intercept for these two variables. Once we understand slope and intercept, what will happen? Let's assume the slope value is 10 and intercept value is 2. Okay, just assumption. Then how does my formula will look like? Y is equal to 10 times X plus 2. Okay, if this is the formula that we were able to generate, Y is my quantity, I need to, so Y is my sales, using quantity, I need to predict. Now I will ask for the quantity 25, tell me how much is my sales. Only if only I have my X variable, I'll be able to predict sales, right? 10 into 25 plus 2, 252. So my Y simply nothing but 252. My sales is 252 when I have the quantity 25. But we will see how to predict slope, how to identify intercept. But before that, we should also understand what is line of best fit. Okay, just giving you an overview of how linear regression works. All we need to identify is slope and intercept of a line. Linear regression does not bother about a lot of information that is underlying in the data. It just focuses on what is the slope of the data, what is the intercept of the data. Using the intercept and slope, it will try to identify a line which is the best fit of all the other possibilities that we will have. Now let me explain what is line of best fit using the same concept. If you lose me anywhere, please feel free to stop me. As I was saying, it is very important to understand linear regression thoroughly. Okay, I'll explain linear regression in detail with Excel. Step by step, I'll explain. Then I'll also explain the step-by-step implementation of same thing in Python. Okay, now this is how my data is distributed. My raw data is distributed like this. Let me draw some conclusions. X is my independent variable quantity through which I'm predicting sales. Sales by quantity. Sales by quantity. In this case, this is how my raw data is distributed. As I can see, there are not a lot of patterns here, because as the number of quantities increase, the sales is increasing here, but as the number of quantities increase, in some use cases, it is also decreasing. So there is no clear pattern here. What linear regression will try to do is, linear regression will try to create a pattern for the optimal fit. How? By drawing a line. It will draw a line anywhere. Assume here it is drawing a line. In this case, it is drawing a line like this. Here it is trying to draw a line like this. Now, assume it can draw a line anywhere. Okay. Once it draws the line, what it will do is, it will try to, drawing a line is simply nothing but maybe, okay, just understand it contextually. In Excel, I will explain this with data points. Now, once it draws the line, it will try to calculate the distance between the drawn line and the data points that we have. Okay? These are different data points. It will try to identify the distance between the line and the data points in the distribution, all the data points. It will calculate the distance. It is simply calculated by this, the blue line minus yellow points. Okay, let's assume this as yellow points for now. Once it calculates the distance between the data point and the line that it has drawn, it will calculate something called as RSS, residual sum of squares. Residual sum of square is nothing but, now what are residuals in the first place? Now this blue line that we are seeing is actually the predicted sales. Okay, it says, okay, let me predict the sales here. The blue line is actually the predicted sales. Yellow points are actually the actual data points, original data points. Okay. Now, the distance between, the difference between actual data and the predicted data is actually called as residual. Residual is also called as error. Okay. Actually, for if I sell one quantity, my sales is $10. If I sell two quantities, my sales is still 10. In this case, it is 20 in some cases, right? Actually, it says for one, if I sell one quantity, the sales value is 10. But the predicted line says, no, the predicted sales is 15, somewhere here, 15 or 18. Okay, let's keep 18. Okay, so the difference is 10 minus 18. 10 minus 18 is actually minus 8. My residual is minus 8 for one data point. Like this, it will calculate the error for each and every data point against the predicted value. Once it identifies the overall, once it calculates the individual errors, then it will square the errors and take the, it will give, for example, for the first model, it will say the residual sum of score is 50, and the second, for the second model, the residual sum of score is 80, and the third model, residual sum of score is 45. Then it will identify the model which has very less residual sum of score as line of best fit, because if I draw a line here in this particular distribution, the amount of error will be very minimal compared to drawing in any other possible use cases. That's why this line is called as line of best fit. Okay, I'll give you a very simple example also, but this is how technically it works. So let me give you a very simple example again. Let's take, I have given multiple interviews. Okay, I have cracked an interview. Now finally, after all the rounds, I'm negotiating salary with the HR. Now let's take this as a real example only and do this. Let me check my browser. LinkedIn salary. Now I have 7 years of experience. I am a data scientist. I worked as a data scientist. Let's see what is the median salary for a data scientist in real time. Now in India, it is in India, 6 to 14 years. Okay. Now let's take the actual data itself. The actual data, median salary is 17 lakhs. Okay, median salary is the middle salary, 17 lakhs. On an average, people are getting from 8 lakhs to 30 lakhs. The salary is distributed. Okay, people are getting 30 lakhs also. People are getting 8 lakhs also as salary for the experience bracket of 6 to 14 years. But the median salary is 17 lakhs. Now, I have seen this data. Okay, let's take a company itself. Okay, I have cracked the interview in Microsoft. The median salary is 20 lakhs, but the range of salary is from 9 lakhs to 30 lakhs. Okay, now as somebody who has already done the research, I am going to ask the HR for giving me the maximum salary, because for that particular experience, there is somebody who is already earning that money, right? 30 lakhs per annum. Okay, this is the salary that I am asking with Microsoft. But as a role of HR, every HR has this idea of providing you only the median salary. Nobody will give you the maximum salary in that particular range. So the HR is proposing me 20 lakhs. As we can see, the median salary is 20 lakhs only. See, the median is 20 lakhs. Okay. Now the HR says 20 lakhs. I am saying 30 lakhs. This is not helping anybody, right? Let's draw this data point. Let's draw this distribution. Okay, this is assume this is 20 lakhs and this is 30 lakhs. I am asking this, but the HR is saying this. Now, this is not, I am not satisfied, right? If I am asking 30 and if the HR says 20, this is not helping anybody, right? This is 10 lakhs differing from my what I'd say expected package. So the negotiation starts. Okay, in any company, anywhere, if you know that you have given good interviews, you must negotiate your salary. Okay. Now the negotiation will start. The HR I will say, no, 20 lakhs is way too much. Give me at least 28 lakhs. The HR will say, no, I'll give you 22 lakhs. Then the negotiation will happen. Finally, we will end up on 25 lakhs. Okay. We'll mutually agree on 25 lakhs. Okay. We will mutually agree on 25 lakhs. Now the line is drawn in this place. Now, what is the difference between the expected package and the given package? I was expecting 30 lakhs, but she gave me only 5 lakhs. So the difference is 5 here, minus 5. But the HR was initially proposing only 20. She has gone up or taken up her offer by another 5 lakhs. So this is plus 5. So the point here is the error between both the data points from 25 is 5 only. Okay, this is mutually beneficial for the HR as well as for me. I was expecting 30 lakhs, but since the HR proposed only 20 lakhs, but after negotiating, I was able to get another 5 lakhs. So it's a 5 lakh win for me. For HR, the candidate asked for 30 lakhs, but she was able to negotiate another 5 lakhs lesser from the expected salary. So there is a win of 5 lakhs for the HR also. So the error here, the error is I did not get what I want. HR also did not get what I want, what she wanted or he wanted. But we ended up in a mutual place where the error is mutual for both of us. Correct? But if the HR is going to finally say, okay, my stand is only, if the HR is going to draw a line here and says, I'll give you only 22 lakhs. Now the error for me is very large, right? I'll be losing 8 lakhs from expected package, where it will be biased towards HR, because HR has strongly reduced 8 lakhs for a company. On the other hand, if I negotiate very strongly and I end up getting 28 lakhs, the error in HR side is very large, right? Because she or he proposed only 20 lakhs. There is a upscale of 8 lakhs for her, an error of 8 lakhs for her. So the point is, when we are negotiating, the salary might end up anywhere, but the optimal line would be mutually beneficial for both the parties, right? This line, the blue line that we are seeing, is actually the line of best fit, because it is mutual for both the parties involved here. It is not hampering the HR, it is not hampering the candidate as well. This line of best fit is what we are going to identify using linear regression. I hope it is clear now. Now 0, 1. We spoke about the formula, the mathematical approach of linear regression. Linear regression simply follows a straight line. The pattern is straight line. Hence, the mathematical explanation is y is equal to mx plus c. Okay. Now we know y is target variable, x is independent variable. All we need to identify is slope and intercept. C is intercept. See here. Okay. What is intercept? It is pretty simple. It is simply nothing but point where x meets y. Okay. Point of intersection, basically. Okay, where x-axis meets my y-axis becomes my point of intersection. That is actually called as intercept. But what is the slope? Slope is simply nothing but the magnitude or direction in which the axes are present. Now the axis is present in x-axis and y-axis. Now that's why, see here, x-axis and y-axis. A slope can be present anywhere in the line, not necessarily here. It can be present anywhere in the line. But if I have to calculate the slope value, I need to know the distance in x-axis as well as in y-axis. In x-axis, it is from x1 to x3, correct? In y-axis, it is from y3 to y4. So if I have to calculate slope, it is pretty simple. It is x1 minus x3 into y1 minus y3 upon x1 minus x3 the whole square. But since slope can be present anywhere, we will not be considering only 1 and 3 here. We will try to generalize the formula by x minus x bar into y minus y bar divided by x minus x bar the whole square. Okay, so this is how we will actually calculate the slope. Okay, this is simply rewritten. Okay, the same formula is rewritten by striking out the numerator as y minus y bar upon x minus x bar. Theoretically this is correct, but practically what happens is you will have negative values in x minus x bar. You cannot override negative values with the square. So we cannot follow this when we are implementing it. We should follow the order of x minus x bar into y minus y bar divided by x minus x bar the whole square. But beware, you don't have to remember all these formulas or anything. You just need to know what is happening. But knowing the formula is always an advantage. Okay, it's not mandatory, but knowing it is very, very helpful, because you can understand what is exactly happening in the back end. So I can use this formula to calculate my slope. Once I calculate my slope, it will generate me a value. Assume 10. So my formula will look like y is equal to 10x plus c. Now I can easily calculate c, right? C is equal to 10x minus y. Okay. So intercept can be calculated once the slope is calculated. We already have the values of x and y. So it becomes very simple. Calculating slope is actually the main task in building or plotting a linear regression model. Okay, that's the technical part of it. So let me just close all these things. Enough of theory. Let's dive right into a data set and then see how it actually behaves. Then we will implement a lot of things along with linear regression while we are doing it in Python. First, in order to do this, let's create data. Let's do the same quantity sales example. Okay, let's take this because it's a good model only. I am just forcing the slope here, but just an exercise, right? We will take a random data set and do it also, so don't worry. Okay, this is my independent variable and this is my target variable. Let me do one thing. Let me highlight this in different colors. We are going to predict y with the help of x. Okay, that's what we are going to do in this exercise. Before plotting anything, we will first see the trend or the pattern in these two columns. Let's build a chart, a scatter plot. If you see the scatter plot, there is no straight line here. Okay, but we can in Excel also, we don't have to write any code. If I just click on trend line, it builds me a linear regression only. Okay, so see here, this line of best fit is around the data points very closely, which means there will be very, very less errors. If the line of best fit is very close to the data points, it means the errors will be very, very less. The model will be able to predict the values very accurately. But if the data points are far away from the line, it means there will be more error. But we will talk about the trend line after we manually create things step by step. We are just understanding the pattern.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Let me do one thing. Let me just keep the chart in the second sheet. So when we build a model, once we are done building the model, we can actually come back to this and then understand how it has changed. Okay, let's go back here. Now to build a linear regression model, we need the most important question. What is the value of slope and what is the value of intercept? Calculate this. I'll come back to calculating this. In order to calculate slope, we need to calculate x minus x bar, y minus y bar, and x minus x bar the whole square. So I'll say x minus x bar. Then it is y minus y bar. Bar is simply nothing but the mean value of that column. Then we will calculate x minus x bar the whole square. Once we have this information, then we will be able to calculate the slope value. Once we calculate the slope value, we can calculate intercept also. Once we calculate intercept, we can also calculate the predicted sales. This is the error. We'll talk about error later, but for now, let's calculate this one by one. In order to calculate these things, we need the mean value of these columns. So I'll simply calculate the average. Okay, the average of quantity is 54 and the average of sales is 492. Calculate x minus x bar. It is x value minus the mean value of it. So for all the data points, I'll calculate the x minus x bar. I'll do the same thing for y minus y bar also. I'll just substitute my sales value with the mean value of the column. Okay, see here, it is 755 minus 492, 575 minus 492, 176 minus 492, and so on. Then in this case, if I have to calculate x minus x bar the whole square, I'll just multiply this with the same number. It will give me x minus x bar the whole square. I also missed one thing. This is x minus x bar into y minus y bar. This is our numerator, right? So we didn't calculate the numerator. So just calculate the numerator. To calculate the numerator, it is x minus x bar into y minus y bar. This is my value. So we have a numerator. This is actually my numerator for calculating slope, and this is my denominator. Now this might look a little intimidating in the beginning, but I'll show you extremely simple ways to build a model in Excel as well as in Python. This is since this is a first algorithm, I'm following the detailed approach. Once you understand this algorithm in detail, the following algorithms becomes very, very easy. Okay. To calculate this, if I have to calculate slope, I need to know the average. I need to know the sum of x minus x bar and sum of y minus y bar. I need to calculate average, my bad. It's the average of this. Here also it is the average of it. Now, if I calculate x minus x bar upon y minus y bar, my slope value is generated. Okay, so this is my numerator and this is my denominator. Once I calculate them separately, I need to take the average of those columns. Once I take the average, I'll divide just that. Okay, numerator by denominator gives me my slope value 10.11347. 24147. I'll just copy this and paste the value here. What is my intercept? If I have found out my slope, my intercept becomes easy to calculate because my formula will look like y is equal to 10.11 into x plus c. Okay, but to calculate intercept, it is c is equal to mx minus y. Okay, mx minus y. So what I'll do is I'll just calculate intercept. Calculate intercept. What is m? The m value is this. What is x? X value is the mean value of x. Okay, mean value of x minus mean value of y. Okay, this is my intercept 54.12. Okay, this is my intercept. Just minimize a little. Okay, this is my intercept. So I have my slope value, I have my intercept value also. So my formula will now look like y is equal to m. Okay, my final formula looks like y is equal to 10.11x plus 54.1244. Now, if I supply only the quantity value, which is my x, I'll be able to predict sales, right? For an example, if I wanted to know what will be the quantity, what will be my sales if the quantity is 150. Here, if you see, we have not used anything greater than 100, right? So if I wanted to know what will be my sales value if my quantity is 150, in that case, all I have to do is supply 150 into the x position here, which will be my slope value multiplied by 150 plus my intercept value. So my sales will be 1571.11. Okay, so this is what we will do, but we will come to this a little later. First, we need to predict the salary for the existing quantity itself. So this is the sales value of actual data, but after building the model, we will have a very streamlined predicted value now, which is calculated by mx plus c, right? So what is m? M is simply my slope into x. X is the quantity value plus c. C is simply nothing but my intercept. Just apply the formula here. It says for quantity 13, the sales was 102, but the model says it is 185. For quantity 15, the sales says 126, but the model says 205. So the error is simply nothing but actual data minus predicted sales. Actual sales minus predicted sales. But we will come to error a little later. But here, the machine has found a pattern based upon the quantity and the sales of the past data. Now, let me do one thing. I'll plot the quantity and the predicted sales in the same scatter plot. See here, there is a straight line in the pattern now. The data is behaving in a certain way now. Let's just remove this chart and go back to the next sheet. Let's compare with the actual data and predicted sales. So in actual data, the data points were distributed like this, but linear regression says, no, for going forward, use this logic for predicting your sales. Just if I apply the trend line, it will plot a straight line for us. This is exactly the straight line that we were able to draw here. Now, I said we don't have to follow all this max manually. In Excel, if you have just quantity and sales column, you can plot a simple scatter plot. And then once you plot the trend line, you can say options. In options, you can say linear regression and ask the machine to show the equation on the chart. Okay. If you see the equation on the chart, where does I did not see here? The equation has been generated. It is 10.113x minus 54.124 mx plus c. It is. Why my intercept is positive then? Okay, it is y minus mx. Sorry, it is y minus mx, not mx minus c. It is y minus mx. Okay, understood. Okay, it's just the other way around, not c minus, not mx minus y. It is y minus mx. So it is minus 54 point something. Okay, now let's plot the trend. It was my manual error. The formula is c is equal to y minus mx. Now the predicted sales is just, now if you see the prediction remains the same. In our predicted value, if I just show the formula, it will exactly be the same. It is 10.113 into x minus 54.124. If we see what we have calculated manually, we have calculated exactly the same thing. 10.113 x minus 54.1244. That's exactly what machine also says. Machine did not calculate all those things manually like we did, but our manual calculation is correct to what the machine also have predicted. So if you see here, that line of best fit has been drawn here. So going forward, we'll have to follow this pattern if we have to predict sales via quantity. Okay, let me address cleared out. Save and share this Excel file. Yes, I will do that. Don't worry. We will take a break in 10 minutes. C is equal to y minus mx. Correct. You are right, Yogesh. I was just, when I was rewriting it, I got, I overlooked it. The correct logic is y c is equal to y minus mx only. Please explain intercept again. Intercept is simply nothing but where my point x meets point y, correct? Where x meets y, point of origin. For an example, the first interaction is happening somewhere here. Okay, the first interaction is, what's the data points? Okay, let's see the data points here. If you see the data label, it starts this particular label. It is somewhere around 102 or something. But this is the point of origin. Okay, this is where the point exists, like ends. Okay, this is the start point and end point. Now, where my x meets y is actually what intercept talks about. We can also set the intercept in the visual. Let's set that intercept and see where it is showing you. Set intercept. See here the intercept is here, somewhere here. We just cannot see it. Where point x meets y, it actually gives us between 40 to 50, somewhere here. As we can see, it is meeting x and y, right? So where the point x meets y is actually the intercept. Okay, where x-axis meets my y-axis. So in this case also I can just, I think you can leave this as it is. But that is the explanation to intercept. But why have you calculate average of numerator and denominator but not summation? I cannot calculate summation, right, Anish? What it will give me is the wrong information. I wanted to calculate x minus x bar into y minus y bar divided by x minus x bar the whole square, right? If that is the case, I cannot calculate it for individual data points. I wanted to know the slope of the data. I wanted to know the entire slope and entire what is this intercept. I don't want slope for each and every data point, right? If I have to calculate data slope for each and every data point, then I will take summation. But since I wanted to know for the entire data set, entire table that I have, then I have to take the average only. Perfect. So as we can see, we have built the model and we can see the data points. These are the predicted values. The dotted lines are the predicted values. Whereas the dotted points here are the actual data points. The difference between actual data points and predicted data points are actually the error. Okay, this is the predicted sales and this is the error. So actually, when I sell 13 quantities, my sales value gets generated to $102, but my model will predict it as $77. If I sell 15 quantities, I will be generating $126 as sales, but my model will predict it as $97. So there is error, but there will be error in all the models. There is no error-free model. Okay, every model will have some error. It is like students only. If the teacher is teaching a topic and conducting a test, not every student will score 100 out of 100, right? Every student will 99, 98, 97, 96. Some students will score 75, 76. It is exactly like this. Every model will have some sort of error in it. We will see how to handle error and how to understand error in models. But for now, all we have done is we have tried to build a model from data. So this is a past data. And using the past data, we have built a model and we will be able to predict the future data also. The future data here is, I wanted to know what will be my sales for 150 quantities. It will be $1,462. Okay. This is how simple it can be. Mathematical explanation is y minus x minus intercept is the value of y when x is 0. Okay. In this case, we predicted and we saw the error. Error is simply nothing but the difference between the actual data and the predicted data. Error is also called as residual. Okay, just a different name to it. Now, before even calculating the error, the first and foremost question that we need to ask is, Can I predict sales via quantity? That is the first question, right? If I cannot predict sales by quantity, then there is no point of building a model or calculating error, anything, right? So in order to understand this, what we will do, we will use the metric called as correlation. What is correlation that we learned in Pearson's correlation coefficient denoted by R? It simply tells us whether two numerical variables are, what I would say, related with each other or not, correct? It ranges from -1 to +1. If both the columns are not correlated, if my target variable, if it is not correlated with my independent variable, then there is no point of predicting the target based on independent variable, right? So we need to ensure that these two variables, my independent variable is correlated to my target variable or not. In order to do that, we can use R, which is correlation, but this will simply give us a correlation. We need to identify how much of my model has actually fit very well in the data with the help of R-square score. R-square score is also called as determinant of coefficient. Okay, determinant of coefficient. It is simply nothing but R-square score is very, very critical. Before even we calculate errors, the first thing that we need to know is what is the R-square score. The range of R-square score is between 0 to 1. It is simply, if you square the value of R, it will give you R-square score. Okay, but what it is, okay, why do I square it and what does it explain me? R-square score simply tells me how well the change in the response variable. Response variable is our target variable. Okay, how well the change in our target variable is explained by the independent variable. So it is the other way around. How well the change in independent variable is explained by the target variable. Yes, other way around. Basically, if I make a change in quantity, if I increase or decrease my quantity, how well my sales changes. Okay, how to what degree my sales changes. It can also be interpreted as, now I am using the M and C of the past data to predict the future data, right? M and C are the coefficients of the model. Coefficients are simply nothing but the learning parameters that we use to learn information from the data. In this case, it is M and C, intercept and slope. Now, how much of the information from the past data, how much of the information means, whenever I say information, I'm simply relating it to the pattern or the trend that is there in it. Okay, how much of the information in my past data is replicated in the future data. Okay, how well the model is fitting the data is what your R-square score explains. Anything greater than 0.5 or 0.6 or 0.7 is actually a good model, which means any change made in independent variable, 60 to 70%, if the value is 0.75, it means 75% of that change is explained by the independent variables. If my sales is increasing from 100 to 1000, why it is increasing? It's increasing because there is certain amount of value that got increased in my quantity. Okay, so the easiest explanation would be R-square score simply explains the change in my target variable based on the change happened in the independent variable. To what degree does it change? Now, to understand it better, it simply helps us understand how much of the information that is learned in the past data is replicated in the future data, is replicated in the test cases. So we need to calculate the R-square score through which we will be able to identify whether this is a good model or not. The model can be considered good if the R-square score is greater than 0.7. But in some cases, even 0.6 or 0.5 is also considered to be a good R-square score. It is purely subjective on the problem that we are currently working. Okay, based on the problem, the R-square score varies, but anything greater than 0.7, it's a good model. Okay, how can we calculate R-square score? R square score can be calculated by just squaring the correlation coefficient. Okay, if I calculate correlation, which is R, correlation is simply R. It is 0.988. If you simply square this value, it is the R square score. This is the R square score. But in Excel, we have the R square score function itself, RSQ. This directly will give me the R square score without even calculating correlation. See here, it gives me exactly the same value I have calculated manually, but the same thing, potato, potato, two different ways of achieving this. Okay. R square score is calculated like this. R square score is simply nothing but the determinant of your coefficients, which will help us to identify how well the model has learned information from the past and replicated it in the future. And okay, once we understand the R square score, then what we can do is we'll talk about errors. Talking about errors, how to calculate R, Jitesh explained that in our statistics module. To calculate R, it is simply standard deviation of X into slope divided by standard deviation of Y. Okay, that's the formula to calculate slope, calculate correlation. Okay, correlation coefficient, which is small r. It is not capital R, it is denoted in small r. And in this case, I just use the correlation function to calculate this. Okay, in Python also I'll show you how to do it. Don't worry. Am I missing anything? Okay, I have explained the basics everywhere. Now let's talk about error. Okay, I said every model will have error. Okay, there is a very famous proverb inside the machine learning community. There are there are no correct models. Okay, there are few models which are that might be helpful. Okay, so whenever a regression problem comes, now talking about error is also a residual. It is calculated by actual data minus predicted data. Now, how do I understand the errors? Now I have said the error is 24, it is 28, minus 103, 20. But how can I understand? Even if I calculate average, the average says minus 8.99 exponentiation to the power of minus 5. I cannot understand anything here, right? The problem here is we cannot interpret the error directly. So we'll have to use two different techniques to understand the errors. There are multiple techniques. The important ones are RMSE and MAPE. Okay. RMSE stands for root mean squared error. Okay. MAPE is simply nothing but mean absolute percent error. Okay. Now, what does root mean error squared error does is it simply takes the error, squares the error, and takes the mean value of it, and also takes the square root out of it. If you remember this syntax, if you remember this operation, this is exactly what we have done in terms of calculating standard deviation. How to calculate standard deviation? X minus x bar, the whole square, take the average of it and square root of it. RMSE is simply nothing but standard deviation of errors or standard deviation of the residuals. We can also say RMSE as square root of variance of residuals. Okay, it will simply tell us how far the predicted data points are present from the actual data points. Predicted data points are present from the actual data points. Okay, there is no range here, so it will become little tricky to interpret RMSE score. But the general idea is if the RMSE score is lesser, it means lesser error, which simply means if the RMSE score is less. Suppose this is my actual data point. The yellow data points are actual, and my red ones are the predicted data points. The predicted data points are actually closer to the actual data points, right? It means there will be less error. But if the RMSE score is far away from the actual data points, the errors are higher. Okay, the interpretation is If the RMS score is lesser, it means there are lesser errors. If the RMS score is higher, it means there are a lot of errors in the model that we have built. There are no scales to say what is a lesser RMS score and what is a higher RMS score. Based on the value of the target variable, we will only have to decide whether it is a lesser or larger RMS score. Okay, I'll explain this with the data points so it will make sense. But this is the concept of RMSE. It simply takes the squared error and calculates the average out of it, and finally takes the mean root out of it. We can also take MSE. MSE stands for mean squared error. Mean squared error is nothing but the variance of error. But understanding this is really tough, because this will be squared value of your error. Okay, if the data points are here, the squared values will be far away, so you cannot understand it easily. The easiest way to understand is using the RMSE score. Okay. Now talking about MAPE. MAPE is a very straightforward, simple way of understanding the errors in a regression model. Not only in linear regression, in any regression techniques, these are the error metrics that we must know: RMSE, MSE, and MAPE. Okay. In terms of MAPE, it actually does the same thing. It takes the error, calculates a percentage of the error, and then takes the absolute value. Absolute value is converts everything from negative to positive. Okay, real value. Then it will take the mean value out of it. Now MAPE is directly we can understand MAPE directly. It will give you the percentage of error that has been generated in the model. If it says 9.75, it means 9.75 of the predictions are incorrect. Rest 91.25% of the predictions are correct. Okay, it directly talks about the percentage of error that the model has created while building the model, whereas the remaining percentage are actually the correct predictions. Okay, MAPE is the easiest way to understand the overall volume of the error, the overall percentage of the error, whereas RMSE helps us understand how far the predicted data points are away from the actual data points. Okay, let me just clean this. Now let's execute all those things in Excel only. Then these are the topics that we must know for implementing things in Python. So we can directly jump there. So I'll calculate squared error. Then I'll calculate mean sum of squared and then percent error for calculating percent error, absolute percent error, and mean percent error. Okay. Squared error is simply multiplying the numbers error with itself. Then percentage error, sorry, let's first finish RMSE. So if I take MSE, RMSE, MSE is simply nothing but the average of squared error. RMSE is the square root of mean squared error. So this is the value RMSE has generated. What is our sales value? Our sales value average is 492. The RMSE score is 40, which means the RMSE score is very less. If the RMSE score is very less, it means there are very less errors in the predictions that we have made. The model will also have very less error. We will compare the RMSE score with the mean value of our actual target variable. If it is less, it means very less error. If it is high, the model has very large errors. Talking about percentage error is calculated by error divided by the actual data. This is the percent error. Once we calculate the percent error, we will calculate the absolute, because percentage cannot be negative. So using absolute, we will convert everything into positive. Then we will calculate mean absolute percentage error. Mean absolute percentage error is simply the average of absolute percentage error. It is this. If I convert this into percentage, 1.2% of the predictions contain error. The rest of the predictions are absolutely correct. It has very less error in the model that we have built in this particular use case. So this is a really good model. The R square score is really good. It is above 75. It is actually greater than 95. And the RMSE score as well as the MAPE score indicates that the model has errors, but it has lesser errors. Do we remove errors from the predicted values later on? No. How can you remove errors from predicted values? You cannot do that. Okay, you cannot, what I would say, remove errors at all. Errors are generated as a separate value only. You cannot remove them. We will try to optimize it in the lateral portion of the module. MSC, no problem. MSC is simply nothing but variance of the error. Okay, first I'll calculate what is variance. Mean sum of squared is actually variance. First I'm calculating error, then I'm calculating the mean squared error. Sorry, squared error. Squared error is just multiplying the error with itself. Then I'm taking the average out of it. Okay, this is the variance, but this will give you the squared error value. Okay, if I say the mean squared error value is 1658, it is far away from the mean value of the sales, right? Of our target variable. We cannot understand or interpret this easily. So that's why to normalize the mean square, normalize the error, we will take the square root. Because we are squaring the error here, to normalize it, we are taking a square root, which will give you a RMSE score. The RMSE score is compared then to the target variable, the mean value of the target variable. If the RMSE score is less, it means the model has lesser error. If the RMSE score is more, then the model has more error.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
The MAPE also says me that it has very, very less error. The formula for MAPE is pretty simple. First, we will calculate the percentage of error. Then we will calculate then we will generate absolute percent error. Then we will just take the mean out of it. It says 1%, 1.2% of the predictions contain error. Remaining 98.8% are correct. So what can we conclude is this is a good model. We can use this model and implement the model as a final model. Or if the model has produced very less R-square score, so for an example 0.54, and the RMSE score is very high, then what we'll have to do is we will reject the model, saying that this model is not good for this data set. So we cannot use this model for predictions. Okay, either accept or reject the model. How do we understand that the RMSE is high or low? That is what I was explaining, Rajendra. What we have to do is we'll have to compare the RMSE score with the mean value of the target variable. Okay, the RMSE score is 40 and the mean value of the sales is 492. 40 is far away from 492, right? Very less compared to 492. It means it is less. For example, if the RMSE score is 700, it is far away from the sales value, the mean of the sales value, then it is higher. Okay, so we will compare this with the mean value and say whether it is lower or higher. There is no range or scales in understanding RMSE. That's why we will compare it with the sales value of our target, the mean value of the target variable. We cannot actually rely on MAPE a lot. It directly tells us the percentage of error that we have made, but RMSE is very important than MAPE, because what RMSE does is RMSE will simply apply more penalty to larger errors. For an example, if you see, in this case, the error is, the deviation is 103. Instead of predicting 176, the model has predicted 279. The error is just 103, but when you square it, look at the value. It becomes 10,735. Basically, RMSE ensures that it will give more penalty to larger errors. So if your MSE score is very high, okay, it means there are larger errors in the model. It doesn't mean multiple errors. It means larger errors. RMSE simply tries to normalize it. MAPE percentage at the very high level simply tells me how much of my predictions are correct, how much of my predictions are not correct, how much percentage of my predictions are containing error, and how much can I rely on it. If I'm saying that tomorrow it will rain, if my MAPE is 1.2, you can believe the statement 98% of the cases. There are the fail proof is 1.2%. So it depends on what we are trying to explain. We'll have to use RMSE, MSE, or MAPE. If our focus is to understand whether we have smaller or larger errors, then we'll have to go with MSE. if I have to understand how far my data points are distributed from the center, from the actual data points, then I'll go with RMSE. If it is far away, if it is lesser, it means the model is good. If it is larger, the model is bad. If I just wanted to understand the error percentage of my predictions, I'll go with NIP. Again, everything is independent and different. So we'll have to go with use cases. In general use cases, it is MSE and RMSE only. Okay, perfect. So that brings us to the end of implementing all these things in Excel. Let me just save this, close it, implement this in Python. Let's come back to Python again. After a couple of classes, we are coming back to Python. Let's implement everything in. Now, we will be using a module called sklearn, okay, scikit learning. This scikit learn package contains all the machine learning related actions. It is a scientific package. It works only with machine learning related operations. It does not do anything else. So for the entire module, even including unsupervised learning, we will be using sklearn only from today till the end of your Python module. We will be learning sklearn only. Okay. So let me just launch this. Oh. Now we can take a data set and then build the model here. So before that, let me import all the required packages. So I'll be importing Pandas. I'll be importing Numpy. I'll be importing random for some exercises. I'll be importing matplot library. Import sklearn dot linear underscore. I'll be importing the linear regression function. I'll also be performing central imputation for you today. So I'll be using sklearn dot impute. I'll also be performing standardization. Sklearn dot, what is this? Pre-processing. Okay. I'll also show you min-max scaler, for example. Okay, these are the packages and functions that I want for building the model effectively. So just import them, let it get loaded. Perfect. It is done. Now I'll explain all these things one by one. First, let's load the table. Now in the current folder, supervised learning, I don't have, oh, I do have data. What is the data? Let's check. Years of experience versus salary. Too smaller data. Let's take a larger data set. Sales. The data frame is read underscore Excel files. I'll load the Excel, and then I'll show you the number of rows and columns that we have. It has 5,000 rows and it has 2 columns in it. Okay, fine. Now here I've loaded the table. So let's first see how the data is present. So first I'll say head. Just wanted to see the first 2 rows. I have order ID, order date, property ID, product ID, quantity, product name, price, sales, everything. Perfect. Now let's use quantity to predict sales. Okay. But if I have to use quantity to predict sales, I need to ensure whether the quantity is correlated to sales or not. So in order to do that, first let's build a simple heat map. Okay. I wanted to build a simple heat map to understand whether these 2 columns are correlated or not. I'll say this, and then I'll see this. I didn't define. Okay. Let me just enhance this to your size. Okay, perfect. So quantity and sales. Okay. If you see quantity and sales, it is only 32% correlated. Okay. Whenever you are building a model, especially a regression technique, we need to just ensure that the target variable is highly correlated against the independent variable. If I take in that case, price is very much correlated to sales. 88% price and sales are correlated. So let's predict the sales by the price of the products. Okay. In order to do that, this is actually my x variable and y variable, but let's not jump into conclusion directly. Let's not build the model directly. Let's follow all the processes that generally generally we will follow when we are building a model. First thing is, we need to ensure that there are no, let's first take a subset of the data. df is equal to df of location, all the rows. I want only price column and I want only sales column. Perfect. So we are going to predict sales based on price column. Now in this case, first let's try to understand whether there are any issues in these two columns. First and foremost is identify if there are any outliers in the table. Okay. Now your target variable can have outliers, but your independent variable cannot have outlier. So here it says in price there are outliers. In sales, this is a target variable, so it can have outliers. So let me just plot only price. Okay. Okay. There are definitely outliers above my upper whisker. So what we have to do is we have to handle outliers. Okay. So I'll simply say outlier treatment. If we don't treat the outliers, the output that we will be generating out of the model will be heavily influenced by the outliers, and we cannot rely on the prediction then. Okay. So how do I treat the outliers? Outliers are simply abnormal data points which causes influence in the which causes influence in any analysis that we will do. Okay. To calculate the outliers, to identify what are the outliers that are there. How many data points we have in total? 5,000 data points. Okay, let's use all 5,000. Then we will do the splitting. For now, what I'm going to do is I'll show you how to calculate the outliers and how to remove them. For that, first I need to know how the price column is distributed. df described. Okay, the minimum value is 3 and the maximum value is 300. Okay, perfect. Any value above 150 is an outlier. I can clearly see in my whisker here. Any value above my t here and any value below my inverted t are outliers. Okay. In this case, there are no outliers in the negative. There are no negative outliers. Anything less than the inverted t are negative outliers. Anything above the grade, this particular t that we are seeing is called as positive outliers. Okay. Now in this case, I have understood how the columns are distributed. This is 25th percentile, this is 50th percentile, and the 75th percentile. Okay, these are not percentages, these are percentiles. Okay. Now, if I have to calculate the range of the upper threshold value and lower threshold value, the upper threshold is called as upper whisker. Okay. And the lower threshold is called as lower whisker. The T that we are seeing is called as a whisker. Okay. But if I have to calculate this, then I need to know the most important point, IQR. Yesterday, I think we spoke about IQR. It is Q3 minus Q1. Q3 is simply 75th percentile. Q1 is 25th percentile, right? So I'll say 75 minus, what is my 25th percentile? 17. Okay, this is my IQR. Once we have our IQR, we can calculate upper whisker and lower whisker. Upper whisker is calculated by Q3 plus IQR. Okay. What is Q3? Q3 is 75. So 75 plus 1.5 times IQR. Lower whisker is calculated by Q1 minus 1.5 times IQR. Q1 is 25 percentile, 17. So 17 minus 1.5 times IQR. Okay, these are our thresholds. So let me print up. Okay, upper whisker is my 162 and lower whisker is minus 70, which means if there is any value in the price column, if it is less than minus 70, it's an outlier. And if there is any value in the price column, and if it is greater than 162, that is also an outlier. Okay, this is how we will be able to calculate the outliers. Just an alternative, I think I'll just pass on that. Fine. So here what I'm trying to do is I'm trying to calculate the upper whisker and lower whisker. Once I calculate the upper whisker and lower whisker, all I have to do is I will have to ensure what are the first I'll identify what are the outliers in the price column. Okay, I said any value greater than 162 is an outlier. What is the maximum value that we have in price? 300. So definitely there are outliers. First, let's extract those outliers. So in df of, if the price value is greater than 162, I wanted to know all those values from the price column in the data frame. 330 outliers are there. Oh my goodness. Out of 5,000 data points, 330 outliers are there. Okay. This 330, if I say 330 divided by 5,000, we will know the percentage of outliers. Okay. 0.06. If I convert this, it is actually 6%. 6% of my price column contains outliers. This is actually way too much. Okay. You cannot have 6% of outliers in any column. So we'll have to override this price column, override the outliers. We cannot eliminate outliers, okay? Because the outliers might contain some information and it may have a trend in the sales column. So we cannot eliminate outliers. If it is less number of outliers, we can eliminate. But here I have almost 6% of my column containing outliers. So I will replace the outliers with a particular value, okay? We can replace the outliers with the upper whisker value itself, or we can replace the outliers with the mean value of the column or the median value of the column. We can choose either one of these three and then replace the outliers. How can we do that? I'll say df dot index location in the location where if the price column, if it is greater than 162, okay, but in all the rows in the price column, I wanted it to be replaced with the, I will simply say, let's replace it with upper whisker only. Okay, it got replaced with upper whisker. Now there will be no outliers in this particular price column. See here, I have plotted box plot on price column. There are no outliers because all those outliers are replaced with the upper whisker value. It creates bias in the system. It creates bias in the table in this particular column. We will see how to handle bias later, but it definitely does create outliers. Sorry, bias. But what we have done is we have actually replaced those outliers with the help of upper whisker, so that no outliers are present in our independent variable. In our target variable, if there are outliers or any issues, we can leave it as it is. But in independent variables, these issues must not be there. Let's talk about missing values. Once you identify outliers and handle them, then the next thing that you will do is handling the missing values. Okay. To handle missing values, let's check if there are any nulls in both the columns. Is null dot sum. There are no nulls in the column in both price and sales. There are no nulls. The target variable should not contain null. Okay, irrespective of whatever happens, your target variable should not contain null, and it will not contain null. Any data set you take, your target will not contain null, but your independent variables can contain null. What I'll do is I'll intentionally create some nulls just so that I can show you how to perform handling missing values using sklearn. Okay, I have shown you how to do it using fill-in-a, right? The same thing can be done effectively on a table using fill-in-a. Using fill-in-a function, I can replace missing values for one column at a time. Okay, or else I can replace one constant for all the missing values across the table. But if I have multiple numerical columns, I wanted to replace all the numerical columns missing values with the mean value of that particular column. Then I'll have to use imputation techniques. So first, let me explain this. I'll say I actually wanted to the 148, 57, 43. Every value is present multiple times. Okay, the price value 13 is present 43 times. I'm going to replace all this 43 times into null. Okay, intentionally I'm going to do it just to show you how to handle nulls. I'll say df dot location the df of price column, if it is equals to 13, price column alone, I wanted it to be replaced with null. Okay. Now let's check for nulls. Df dot is null dot sum. So there are 43 nulls. I replaced wherever it was 13, I replaced it with null. So there were 43 13s. So we have 43 nulls now. How can I replace it? There is this concept called as central imputation. Central imputation is nothing but it's a technique that we will use to replace nulls in all the columns in the table. Okay. We will just use this to replace all the columns in all the nulls in the column. How does it work? Is if it is numerical column, it will use the mean value. Okay. It will choose the mean value. If it is categorical, we can choose mode. We can also choose median. While we are replacing it, we can decide what type of metric that we wanted to do. Okay, by default it will take mean if it is numerical. If it is categorical, by default it is mode, but we can change mean to mode also, median also. So I have already imported simple imputer while I'm loading the different packages. Simple imputer is the function which will do this imputation operation for me. So what I'll have to do is I'll say in the df column, in the table, in price column, I wanted to perform simple imputation. So I'll simply say fit underscore transform simple imputer dot fit underscore transform this particular column. Fit underscore transform is an application function. It applies the logic of simple imputer on top of the price column and changes the value. Okay, fit transform. It will apply, transform the values because we are trying to change the nulls into something, right? So basically, we are doing data transformation here. So fit underscore transform is used to apply a function and transform the values within it. Okay, here it is asking me fit underscore transform is missing one positional argument. Expect a 2D array, got 1D array instead. Okay, we have to reshape this. It expected 2D array. Okay, so this df of price is supplied as a one-dimensional array. It might have supplied as data as a series. To convert this into two-dimensional array, I'll just create two square brackets for price. That's it. Now see here, it got converted. So what I'll do is I'll again dump this into the price column of our data set equal to simple imputer creates an array. I wanted to convert this into a data frame. So I'll say pd dot data frame of whatever output that it will generate. So what will happen is the arrays will be generated. Those arrays will be converted into data frame, which then will modify the price column. Then we have in the price df table. I have executed this. Now let's check head column. Let's check if there are any nulls in the price column now. See here, there are 0 nulls. We actually had 43 nulls, but just by performing simple imputation, we were able to replace all those 40 nulls with mean value. Now see here, we can actually choose. If you see the simple imputer, the strategy is by default mean, okay, but we can change it into median or mode. Okay, by default it is mean. We can change it into mode. For mode it is most frequent. We can also replace it with a constant. Okay, so this is the easiest way to replace nulls across the table whenever we are dealing with nulls across multiple columns. Okay, if it is single column, we can use simple fill in a function. But for handling nulls across multiple columns, we will use simple imputer. Okay. Now let's again do one thing. Let's just ensure that both the columns are distributed properly. The minimum value in the price is 3. Sales is also 3. The maximum was 162. The maximum is 900 here. The scale of price and the scale of sales are in similar scales, right? It starts with 3 to 150. Basically, it is in hundreds only. My sales value also, it is in hundreds only. But if my sales value is in thousands and my price column is in hundreds or tens, then they are in different scales. Okay, in those cases we will perform normalization. Maybe when I'm teaching you multiple linear regression, I will teach you normalization. But for now, let's directly jump into splitting the data. Okay, so in this case, the data looks normal to me. I am blindly going to split the data and then build a model, then performing normalization. I'll explain normalization in a more complicated data set. Okay, fine. Now we have performed missing value. We have performed the outlier analysis. All we have to do now is just ensure that we will shuffle the data set before splitting the data into train test split. Okay, train test split, I'll come. Maybe first we'll have to split this into X and Y first of all. Even for splitting this into X and Y, I need to shuffle this. Okay, okay, for splitting, I don't want. I'll simply say, okay, maybe let's first shuffle this. For shuffling the data set, now let me show you the outcome. Then we will understand what will happen. Okay, 0, 1, 2, 3, 4, 85, 85, 85, 85, 150. These are the sales value. Now I will shuffle the entire 5,000 rows. df dot sample function. In sample, I'll say the fraction is 1. Fraction means it will take the values between 0 to 1. If I say 0.25, it will give me 25% of the 5,000 rows randomly. Okay, it will give me 25% of 5,000. 25% of 5,000 is 1250. Okay, but I want all the 100% of data to be shuffled. Okay, shuffled randomly, it should be shuffled. But if you see here, while it is shuffling, it is not resetting the index. It is giving me the same index position that was generated earlier. I don't want this. I wanted to create new indexes for the shuffled data points. So I'll say reset index is equal to true. Reset index true. Execute this. Index, there are too many indexes. Index has only one level, not two. What happened here? Okay, df is equal to, still throws there are too many levels. Index has only one level, not two. Here, so in place is equal to 2. My bad. I think this is not, in place is not what I believe. Let's see what happens. Okay, see here it has, okay. Okay, now I have to drop it. Since I'm saying reset index, it's giving me the old index and the new index. I don't want that. So I'll say drop is equal to true. Yep. What's not giving me the reset index arguments? Okay, drop reset. Yeah, this is weird for me also. How do I drop this using a drop index only? So reset index is equal to, okay, what did I do? Reset index. What's not dropping me the indexes? Fine, I think maybe I'm just, maybe because I have executed this before dropping, and because of that, this data frame is creating indexes, or it has created the index even before that. Okay, let me just quickly do this. Let me read. I think I'm writing the right syntax. Let me just reread the file, so it will give me new values. Then all I have to do is just ensure that I take only price and sales, and I will execute all the remaining codes one more time. Okay. Now I think it should not have the index. Okay, perfect. It was correct only. I just overwrote the data. So the syntax is correct. I'm just resetting the index so that I'll have new indexes. See here, the data got shuffled. Initially it was 85, 85, 85, 150. Now it is 24, 5, 10, 102 something. I'm ensuring that it is randomly shuffled. Now, before doing anything, let's see the original pattern of this data. Okay, before building the model, let's see the original pattern. The original pattern is df of price in x-axis, and then I wanted to also see df of sales in y-axis. Okay, I wanted this to be in red color. Perfect. I'm using the semicolon. Thanks, whoever said me this. But fine. Look at the trend here. The pattern is very weird because there were a lot of outliers, right? See, in 160 there were a lot of outliers. We replaced all those outliers with the upper whisker value. So here it is seeming fine because as the quantity price increases, the sales also increases. But since there are multiple outliers, this outliers will definitely impact the outcome of my output. But in this case, I'm just going to, as I said, it was just to show you the pattern. So directly let's jump into building the model. First, we'll have to say what is our X variable and what is our Y variable. My X variable is simply nothing but price. Okay. Again, I'll supply this in two square bracket just to ensure that it is in 2 dimensions. And my target is sales. So using price, I'm going to predict sales. I'll show you the head of X, the head of Y. Okay.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Now, what we can do is we can split this 5,000 rows into training and test data. Okay, in order to do that, I'll say train underscore X. We can actually split this using a function also. But let me just use this logic so you can visually understand what is happening. Then I'll show you how to do the same thing using a function also. So I'll say in X, I wanted to consider only the first 4,500 rows. Okay. All the columns, only 4,500 rows. In test X variable, I'll say the same thing. I'll say anything from 4,500 I want. Okay, that will be my test data. For training Y, I'll do the same thing. Testing Y also, I'll use the same thing. Just that I'll change X into Y, Y into X. Perfect. Now I have train data and test data. So train underscore X. Okay. Maybe I'll show you the shape of it. There will be 4,501 row and 1 column in it. In test, we will have 499 rows for testing. So this 499 data points, 500 data points will not be used for building the model. So once the model is built, we can supply this 500 data points and check whether the model is built correct or not. How can we check? We already have the Y values for these 500 data points, right? So we will compare this 500 data points from the actual data with the predicted data and see how well the model has learned the information from the data. Perfect. Everything is done. We have separated the data into X and Y. Now let's build the model. To build the model, I'll say model is equal to, the function is linear regression dot fit. Okay. This is fit is an application function. It will simply apply the logic on the data. It will not modify the data. It will simply apply the logic on the data. Where should we apply? On the X variable and Y variable, not on the entire X and Y, on the train X data and the train Y data. Okay, that's it. That's all model building is. I just use a fit function, fitting the function on the data. This particular operation will train the model on based on the data that is available here in these two data sets. I have built the model now. Okay. Model does not give me anything in this case. Fine. So I've built the model. Since I've built the model, I can check what is the intercept of the model. I'll say intercept. Intercept is this. If I wanted to know the slope, it is actually coefficient underscore. This is nothing but the slope of the model, intercept of the model. Okay, we have seen slope and intercept. Now we have these two information, right? So our final model will look like y is equal to, y is equal to So this is our final formula. Final formula is y is equal to 2.49x into x plus minus 14.96. This is the model's learning of intercept and slope from the given data. Since the model has learned this information, we can use this learned information to predict the model's behavior, to test the model's behavior on the test data. So I'll simply create y hat is equal to model dot predict test x. Okay, I'll supply the text s that I did not use to build the model and predict the model. It has created this. Now what I'll do is I will compare the y hat information. So it will be 500 rows here. Sorry, y hat is not a data frame. Okay, these are the 500 data points. Maybe I'll just show you the first 5 like this. But what we can now do is we can build a simple data frame for the first 10 or 20 data points and see how the model has built. So I'll simply say predicted sales is equal to td dot data frame actual sales plus test y predicted sales is y hat. Okay, if using all scalars, you must pass an index. Where am I passing a scalar? Okay, test y is a scalar value. What is that? Type of test underscore y. Okay, test underscore y dot dimensions. This 2, it is correct then. So my y hat. Okay, y hat is singular. Y hat also seems to be having 2 dimensions. It is having 2 dimensions, but then why it is passing me this information? Okay. Okay, we have this as an array. So I wanted this to be converted this into data frame only. Now it should work. Using all scalables, you must pass an index. Surprised, but no problem. We can always solve this. The range is 501 actually. Int object is not iterable. Emotions. Where do I not have an index? Okay. Okay. Let me just ensure how my test y is received. It's also a data frame. Oh, here it is the problem. Okay, okay, got it. Okay, a data frame is predicted test x. It's not being normalized into a. It is a data frame, but it is not getting normalized as a table directly. So, okay, let's check the shape of it. There are 500 rows, 1 column, perfect. This is exactly the shape that I want. My head function is head table is correct. Here just that, okay, let me just say y hat of predicted is equal to columns is equal to predicted. Still throws me the same error. First 500 rows. But it is doable. Y hat is a data frame. This is also a data frame. Test is also a data frame. It must work. Just surprised it's not working. Let me just check if any of my other codes are working like this. ML files. Sometimes the correct syntax also throws an error. I'm just trying to see if I have done anything wrong in terms of syntax. It is correct only, but I'm just checking and double ensuring that it is right. I didn't do it anyway. Fine. I think in the interest of time, I'm just going to leave it here. We will resume our session from this particular place only. Okay, just for now, understand we have built a model, and after building the model, we were able to predict the behavior of the model also with the help of the model that we have built. Okay, with the help of test data.
Now let's start off with deep learning. So deep learning is a subset of machine learning where it learns through data representations as opposed to task specific algorithms. So we saw that the drawback in machine learning models was that the models are specific to only one particular task. But this is not the case with deep learning models, as these deep learning models are based on the data representations, and these deep learning models are mostly built with something known as deep neural networks. So this is how a deep neural network looks like. So these deep neural networks completely learn the data which is fed to it. So this is the data. So let's say if this image of woman is fed as the data to the deep learning model, then it will completely extract all the features of this data by itself. Again, the difference between ML and deep learning over here is that the feature extraction in machine learning is manual. But when it comes to deep learning, the feature extraction is automatic. So the deep learning model automatically extracts all of the features associated with that image. And when new images are fed to it, it automatically is able to tell whether the image is same to this or not. So this over here we have a graph which tells us how does performance vary with respect to the amount of data. So what happens in machine learning is that as we keep on increasing the data, the performance increases only up to a particular threshold. After that, if we increase any more data, there is no increase in performance. So this is another problem when it comes to machine learning. But on the other hand, when it comes to deep learning, the more amount of data you give it, the better will be its performance. And that again is because deep learning is based on learning data interpretation. So the more data you give it, it will automatically learn all those features of the data by itself, and it will be keep on increasing its performance gradually. Now let's look at some applications of deep learning. So speech recognition is one application of deep learning. Now you need to understand that you cannot build speech recognition applications with machine learning. So this is where machine learning fails and deep learning comes in and helps you to build speech recognition applications. Also, another application of deep learning is self-driving cars. So we see over here that the person is just sitting. He is not even touching the steering wheel and the car is driving by itself. So just an amazing application of deep learning. And then we have language translation over here. So this again is a part of deep learning. So over here we are typing something in Spanish and it is being automatically converted into English. So we also have visual translation over here. So over here this text or this board is in some random language, and this app over here which uses deep learning automatically converts this visual into English. So those were some applications of deep learning. Now let's actually understand how does deep learning work. So most deep learning methods use neural network architectures, and that is why deep learning models are often referred to as deep neural networks. So a deep neural network basically has these three models: an input layer, the hidden layers, and the output layer. And the term deep usually refers to the number of hidden layers in the neural network. So traditionally, neural networks only contain 2 to 3 hidden layers, while deep networks can have as many as 150 hidden layers. Now that's a very huge amount, isn't it? So deep learning models are trained by using large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. So all of the input data is given to this input layer, and this input layer automatically extracts the features by itself. Now that data is sent to this hidden layer which performs all sorts of processing tasks, and then the final result is given out through the output layer. So now let's also understand what exactly is a neural network. So a neural network is a computing model whose layered structure resembles the network structure of neurons in the brain with layers of connected nodes. So it can learn from data which can be trained to recognize patterns, classify data, and forecast future events. So the neural network is based on the biological neural network of our brain. So that is why it is given the name neural network. So the layers are interconnected via nodes or neurons, with each layer using the output of the previous layer as its input. So its main function is to receive a set of inputs, perform calculations, and then use the output to solve the problem. Now, as I've already said, these artificial neural networks are based on something known as a biological neural network. So, our biological neural network has dendrites, cell body, and axon. So dendrites are where the input is taken, cell body is where the processing is done, and axon is where the message is transferred to other neurons. And the same thing happens in artificial neural network as well. So first we give in the data, that data is processed, and then the final processed result is given out as the output. So over here, let's say we train the data with images of cat, and the labels would be either cat or not cat. After that, we give in a new image of a cat, and then we basically try to predict whether the model correctly classifies this as cat or not cat. And since the model has learned the data properly, it correctly classifies this image as cat. Now, there are many ways of knitting the nodes of a neural network together, and each way results in a more or less complex behavior. Possibly the simplest of all topologies is the feed-forward network. So when feed-forward neural network, signals flow in one direction without any loop in the signal paths. And typically, artificial neural networks have a layered structure. The input layer picks up the input signals and passes them on to the next layer, known as the hidden layer. And there can be more than one hidden layer in a neural network. And at last comes the output layer that delivers the result. Now, the first question to pop into your head would be, what is the inspiration behind these artificial neural networks? Well, the answer to that is the biological neural network of our brain. So let us first understand the architecture of a biological neuron. So as you can see in the slide, our biological neuron has these three main components. So we have the dendrite, the cell body, and the axon. These dendrites receive the signals, and the cell body processes these signals, and the axon finally sends out these signals to other neurons. So just like the biological neuron, the artificial neuron has a number of input channels, a processing stage, and one output that can fan out to multiple other artificial neurons. So now let's understand these artificial neurons in detail. These artificial neurons are the most fundamental units of deep neural network. It takes an input, processes it, passes it through an activation function, and returns the output if the condition is met. Or else it will process it again until you get the correct output. And such type of artificial neurons is called as a perceptron. So they are basically like a linear model which is used for binary classification. So as the figure shows, we have x1, x2, x3 and going on till xn as inputs in the input layer. Now, to which we add the weights and the bytes that are randomly selected. So here we have w1, w2, w3 going on till wn as weights. So we multiply these weights with the corresponding inputs and add all the values together, and finally we add bias to that sum. So this final sum is passed through an activation function which finally gives us the output. So let us see this in detail. So here we have three arrows which correspond to the three inputs coming into the network. Now for these three inputs, we have corresponding weights associated with them. So input 1 is associated with a weight of 0.7, input 2 is associated with a weight of 0.6, and input 3 is associated with a weight of 1.4. Now, these inputs are multiplied with their respective weights and their sum is taken. So if the three inputs are x1, x2 and x3, the sum would be x1 into 0.7 plus x2 into 0.6 plus x3 into 1.4. And to the sum, we add an offset which is called as bias. So this bias is just a constant which is used for scaling purpose. Now let us understand the concept behind these weights. So these weights basically determine the relative importance of the inputs. So let's say we have two inputs, humidity and wearing a blue shirt. So here we can see that wearing a blue shirt has almost no correlation with the possibility of rainfall. So that is why the weight assigned to input x2 would be low in order to bring down its importance. Now let us see why do we need activation functions. So consider this scenario where you have two different classes. One class is represented with triangles and the other class is represented with circles. Now let's say I ask you guys to draw a linear decision boundary which can separate these two classes. So is that really possible? Can we draw a linear line which can segregate these two classes? Well, the answer is obviously no, isn't it? So let me tell you guys how can we do this. So we'll have to add a third dimension to create a linearly separable model which is easy to deal with. So the logic is when you're going from 2D to 3D, you're making your equation non-linear. So with the third dimension, I have introduced non-linearity in our data, which helps in creating a linearly separable model. And in real-world situations, you don't always get linear problems. So you should know how to deal with non-linear problems as well. And this is where activation functions help us to convert the linear equation to non-linear form. So these activation functions bring in non-linear functional mappings between the input and the response variable. Their main purpose is to convert an input signal of a node in an artificial neural network to an output signal. And if we do not apply an activation function, then the output signal would just be a simple linear function. Now there are many types of activation functions, and today we'll be discussing some of the widely used ones. So let's start with the identity function. So the identity function gives out the same output as the input. So no matter how many layers we have, if all the activations are identity functions, then the final output of the last layer would be the same as the input given to the first layer. And the range of the identity function goes from -infinity to +infinity. So after that, we have the binary step function. So this binary step function is usually denoted by h or theta, and it is a discontinuous function. So if the input is less than 0, then the output would be 0. And if the input is equal to or greater than 0, then the output would be 1. And this is why binary step function is used to solve a binary classification problem. So after that, we have the sigmoid function. So the formula for the sigmoid function is denoted by 1 upon 1 plus e power minus x. The sigmoid function basically scales the values between 0 and 1. So if the input is a large negative number, it is scaled towards 0. And similarly, if the input is a large positive number, it is scaled towards 1. Then we have the tan h function. It is a hyperbolic trigonometric function which scales the values between -1 and 1. So one advantage of tan h function over sigmoid is that it can deal more easily with negative numbers. And after that, we have the ReLU function, which stands for rectified linear unit. So this function will give out 0 if input is less than 0. And on the other hand, if input is equal to or greater than 0, then it will act as an identity function and give out the same value as the input. And this ReLU function is the most widely used activation function and is primarily implemented on the hidden layers of the neural network. Then we have the leaky ReLU, which is just a modified version of ReLU. So the leaky ReLU, instead of just completely removing the negative part, it just lowers the magnitude. And finally, we have the softmax function, which is ideally used in the output layer for classification problems. So the softmax function basically gives a set of probability values for each class of the output. And that particular class, which would have the maximum probability, will be our output class. So that was all about activation functions. Now let us learn more about perceptrons. So like we were taught how to behave in certain conditions, perceptrons also require training. So they have a learning algorithm through which they produce the output. By training a perceptron, we try to find a line, plane, or some hyperplane which can accurately separate these two classes by adjusting the weights and biases. So consider this image where we give the dogs and horses as input. So here after the first iteration, error value is 2 since the horse has been classified as dog and there is one dog which is placed in the horses class. And in the second iteration, the error value is reduced to 1 as it is just the dog which is classified as a horse. And finally, in the third iteration, we get the correct output as the perceptron has been trained well with no error. So all the dogs have been placed in one class and all the horses have been placed in one class. Now let's understand the perceptron training algorithm. So this perceptron over here receives multiple inputs and each input is initialized with a random weight. So after these, we multiply these weights with their corresponding inputs and then we get the sum. Now this input is passed through the activation function which would give us a non-linear output. So this process until here is known as feed forwarding. Now if the output which we get is not optimum, we calculate the error in prediction and then go back and then update the weights and bias. So this process where we go from output to the input layer is known as backpropagation. And we keep on backpropagating until we get the desired output. So that was the perceptron training algorithm. Now let's have a look at the benefits of using artificial neural networks. So the artificial neural networks can learn organically. This means an artificial neural network's outputs aren't limited entirely by inputs and results given to them initially by an expert system. So artificial neural networks have the ability to generalize their inputs. This ability is valuable for robotics and pattern recognition systems. Artificial neural networks also help in nonlinear data processing. So nonlinear systems have the capability of finding shortcuts to reach computationally expensive solutions. These systems can also infer connections between data points rather than waiting for records in a data source to be explicitly linked. This nonlinear shortcut mechanism is fed into artificial neural networking, which makes it valuable in commercial big data analysis. Artificial neural networks also have high potential for fault tolerance. When these networks are scaled across multiple machines and multiple servers, they are able to route around missing data or servers and nodes that can't communicate. And these artificial neural networks can also self-repair themselves. So if they're asked to find out specific data that is no longer communicating, these artificial neural networks can regenerate large amounts of data by inference and help in determining the node that is not working. This trait is useful for networks that require informing their users about the current state of the network and effectively results in a self-debugging and diagnosing network. Now, to implement these artificial neural networks, we would need the help of a deep learning framework. So the first question to pop into your head would be, what are the different deep learning frameworks available? So today we'll cover just that. So let's start with TensorFlow. So TensorFlow is arguably one of the best deep learning frameworks that we have today. It is an open source software library developed by the researchers and engineers from the Google Brain team for high performance numerical computation. One well-known use case of TensorFlow is Google Translate. So Google Translate is coupled with capabilities such as natural language processing, text classification, forecasting, and tagging. So TensorFlow basically comes with two tools, TensorBoard and TensorFlow Serving. So building massive deep neural networks could be complex and confusing. This is where we can use TensorBoard to visualize our TensorFlow graph and plot quantitative metrics. And then we have TensorFlow Serving, which is a flexible, high-performance serving system and can be used for rapid deployment of new algorithms while retaining the same server architecture and APIs. So now let's look at the next deep learning framework, which is Keras. So Keras is actually a high-level API which can run on top of other deep learning libraries such as TensorFlow, Theano, or CNTK. And with the help of Keras, we can implement both convolutional neural networks as well as recurrent neural networks. And the best thing about Keras is model building is extremely easy. It's like stacking layers on top of each other. So next, we have PyTorch, which is a scientific computing framework developed by Facebook. So we can get from the name itself that PyTorch is Pythonic in nature. That is, it can leverage all the services and functionalities offered by the Python environment and also smoothly integrates with the Python data science stack. Another great feature of PyTorch is that it offers dynamic computational graphs which can be changed during runtime. This is highly useful when we have no idea how much memory will be required for creating a neural network model. And the next deep learning framework is DL4J. So unlike deep learning frameworks which we saw till now,
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
which were all based on Python, Deep Learning 4J is a deep learning programming library which is written for Java and the Java virtual machine. And the biggest advantage of DL4J is it includes inbuilt integration with Apache Hadoop and Spark. So it helps in getting state-of-the-art results on image recognition tasks. So it shows matchless potential for image recognition, fraud detection, text mining, parts of speech tagging, and also natural language processing. And finally, we have MXNet. So MXNet is a deep learning framework developed by Apache Software Foundation specifically for the purpose of high efficiency, productivity, and flexibility. And the beauty of MXNet is that it gives users the ability to code in a variety of programming languages, such as Python, R, Julia, and Scala. This means that you can train your deep learning models with whichever language you're comfortable in without having to learn something new from scratch. And this deep learning framework is known for its capabilities in imaging, speech recognition, forecasting, and NLP. So when you hear the term TensorFlow, the first question to pop into your head would be, what exactly is a tensor? So in TensorFlow, data is represented in the form of tensors. Simply put, a tensor is a multi-dimensional array in which data is stored. So you can consider these tensors to be the building blocks in TensorFlow. Now, these very tensors are given as the input to the neural network. So as I've said, a tensor is nothing but an n-dimensional array. So the number of dimensions used to represent the data is known as its rank. So if a tensor has just one element, in other words, if it has just magnitude and no direction, then its rank will be 0. If a tensor has magnitude and direction in one plane, then its rank will be 1. Similarly, if a tensor has magnitude and direction in two planes, then its rank will be 2. And this goes on higher up the order. Now, TensorFlow, as the name states, is a combination of two words, tensor and flow. Here, the data is stored in tensors, but the execution is done in the form of a graph. So this is not like your traditional programming where you just write a bunch of lines and everything gets executed in sequence. So first, you'd have to prepare this computational graph, and then this computational graph is executed inside something known as a session. Now, in this computational graph, all the mathematical operations are depicted inside the nodes, and all the tensors are represented on the edges. So the entire computation process is done in two stages. In the first step, the code is depicted onto the computational graph, and in the second step, a new session environment is started and the graph is executed inside this session. So that was all about the computational graph. Now let's look at the program elements in TensorFlow. So we have three program elements: constant, placeholder, and variable. So let's start with constants. So constants are program elements whose value does not change, or in other words, the value is fixed. So let's head on to Jupyter Notebook and work with these constants. Right, so my first task would be to import the TensorFlow framework. So I'll type import TensorFlow as TF. I'll click run. So let me just wait till the import is done. Right, so we have successfully imported the TensorFlow framework. Now, as I've said, let's go ahead and start working with the constants. So let me just type in constants over here. So I'll create the first constant and name this constant as con1. Now this is how we can create constants in TensorFlow. So I will use this TF and then put in a dot and then type in constant. Now inside this I will give the value of the constant. So let's say the value is 10. So this is an integer type constant. Now similarly I'll also create a floating type constant and I'll store this in con2. So I'll type TF dot constant and the floating value would be 3.14. Now after this I'll create a string type constant. So again this would be TF dot constant and the string which I'd be giving would be this is Sparta. And finally we have a boolean type constant and I'll store this in con4. So this will be TF dot constant and let's say the value is false. Now I'll run. Now let me print all of these values. So I'll use the print function and then I'll go ahead and print all of these values, con3, con4. Right. So we see that this first constant is a tensor of type integer. The second constant is a tensor of type float. This third constant is a tensor of type string, and this fourth constant is a tensor of type boolean. Now we see that we only have the data types of all of these tensors, but we don't have their values. This is because, as I've already told you guys, we have to create a computational graph and then execute that computational graph inside a session. But till now, we have not started our session. So let's go ahead and start a session first. So I'll type ses equals tf dot session and I'll hit run. Now I will run all of these inside this session. So I will type ses dot run and let me go ahead and run all of these con1, con2, con3 and con4. So this time we have the values of all of these tensors. So the value of constant 1 is 10, the value of constant 2 is 3.14, the value of constant 3 is this is Sparta, and finally the value of constant 4 is false, right? So first we'd have to create all of the constants, then we'd have to create a session, and inside this session we'd have to run all of these constants. Now let me go ahead and perform some simple operations on all of these constants. So let me just type in operations over here. So I'll do a simple addition operation. So I'll type addition over here. And let's say the value of the first constant is 20. I'll put a plus symbol and then I'll take in the next constant and the value of the second constant would be 30. So I am basically adding two TensorFlow constants. The value of the first constant is 20, the value of the second constant is 30, and I'm storing that result in addition. Similarly, I will multiply these two constants now. So multiplication tf dot constant. So I'll give the value of 20. Now I'll put the asterisk symbol and then this would be tf dot constant of 30. So this time I'm multiplying these two values, right? So I'll hit on run. So now again, if I'd have to see the resultant addition and multiplication values, I'd have to run these two inside a session. So I'll type ses dot run and then put in these two values over here, addition and multiplication, right? So we see that 20 plus 30 gives us an addition value of 50. And similarly, when we multiply 20 with 30, we get a result of 600. Right. Now, so this was basic operation with scalars. And we already know that tensors can have higher dimensions. So let's go ahead and perform addition and multiplication with these higher dimension tensors. Right. So again, I'll just put in addition over here. And I will take in the first constant, and inside this I will give in a list of values. So let's say I will take in 1, 2, 3, 4 and 5, and I will add this list with the next constant. And this time the second constant has the values of 5, 4, 3, 2 and 1. Similarly, I'll also multiply. So multiplication equals tf dot constant, and this will have values, let's say the same values, 1, 2, 3, 4 and 5. Let me put a comma over here. Right, now I'll put the asterisk symbol. Again, I'll type tf dot constant, and I will give in the list of the values 5, 4, 3, 2 and 1. Now I'll hit run. Again, I need to run these two inside a session. So sys dot run. Let me put in addition over here. After that, I would also need the multiplication value. Right, so this is a result. So when we add 1 plus 5, we get 6. When we add 2 plus 4, we get 6. Similarly, when we add each of the corresponding elements with these elements inside the list, we get all of the 6s over here. Now let's take this multiplication result. So over here, when we multiply 1 with 5, we get 5. When we multiply 2 with 4, we get 8. 3 cross 3 gives us 9. 4 cross 2 gives us 8. And again, 5 cross 1 gives us a 5. So this was addition and multiplication with respect to lists. Now let me also do a simple operation on strings. So let me take in the first string and name it as str1. So this is a constant. So tf dot constant. And let's say I type over here, I love, and then I give a space. Now I will take in the second string, which would be str2. And inside this, and again, this would be a constant. So tf dot constant, and the value of this constant would be TensorFlow. Right. Now I will run this, and let me execute this inside a session. So sys dot run of str1 plus str2. So the result which you get is I love TensorFlow, right? So the first string is I love, and then there's a space, and the second string is TensorFlow. So when I add these two strings, the resultant is I love TensorFlow. Right, so that was all about constants. And then we have placeholders. So when it comes to placeholders, we don't have to provide an initial value and can specify it during the runtime. So this allows us to build our computational graph without needing the data. And this is how we can create placeholders. So tf.placeholder is the syntax, and inside that we just give the data type of the variable which we will substitute later on during execution. So let's head back to Jupyter and work with these placeholders. So let me just type in placeholder over here. So let me create my first placeholder. So I'll name that as A, and tf dot placeholder, and this would be of integer type. So tf dot int 32. Now I will create another variable which would be b, and the value of b would be actually a cross 2. So let me run this. Now I will run these two inside a session. So sys dot run, and I want to see the result of b. So I'll put in b over here. Now, since we know that a placeholder takes in a value during runtime, so this is when I'll feed the value to this placeholder a over here. Now to do that, I would have to create something known as a feed dictionary. So feed dict equals, let me create a dictionary over here. So it would be a, and the value which I'll be giving to a would be, let's say, 5. Now let me run this and let's see what do we get. Right. So during the execution time, I have assigned a value of 5 to a. And when we multiply this 5 with 2 over here, we get the value of b, which is 10. Right. So all of this is happening during runtime because with the help of a placeholder, we can assign it a value during execution. Now similarly, let me go ahead and give a list of values over here. So instead of 5, let me give the list of values 1, 2, 3, 4 and 5. Now I'll run this. So over here, 1 cross 2 gives us 2, 2 cross 2 gives us 4, 3 cross 2 is 6, 4 cross 2 is 8 and 5 cross 2 is 10. So you get an array of values during runtime. Now similarly, let me also create a placeholder for strings. So I'll type string placeholder over here. So now let me create this variable and name this as string name, and this would be your placeholder. So tf dot placeholder, and I am taking in a string. So tf dot string. Right. Now let me create another string over here. So the name of this string would be my name. And let's say the value of the string is I am. Alright. Now let me run this and I'll execute this inside a session. Ses.run, and I want the result of my name when I add it with respect to string name. Now let me also create a placeholder for strings. So I'll just type string placeholder, and let me create the first placeholder. So I'll name that as str1 name, and since this is a placeholder, tf dot placeholder, and I will be giving in a string during execution time. Now I'll also create another string value over here and name that to be my name, and the value of this string is I am, and then I'll give a space. Right, so now I'll hit run and let me execute this inside a session. Now let me also create a placeholder for strings. So this will be string placeholder. Right, so let me create this placeholder. I'll name this as str name, and since this is a placeholder, I need to use tf.placeholder, and I will be assigning a string to this during execution time. Now I will also create another string which would be my name, and this would be equal to I am, and there's a space, and I will be adding this with str name. So let me hit run. Right, now I'll execute this inside a session. So for that, I'll type ses.run, and I want the result of my name. So I'll just put in my name over here, and then I'll provide the feed dictionary. Feed dict equal to, let me put in the dictionary over here, and I will assign the values of str name over here. Right. So the values of str name would be Sam, Bob, and Charlie. Now let me hit run and let's see what do we get. Right. So what we are basically doing is we are adding this with the placeholder value over here, and we are giving the values during the execution time. So I am Sam, I am Bob, and I am Charlie. Now these three values are coming from this feed dictionary during the runtime. Right. So this is all about placeholders. And finally, we have variables. So a variable is just a program element which allows us to add new trainable parameters to the graph. And this is the syntax to create a variable. tf.variable, and then we give the value, or we initialize the value, and then we specify the data type of that variable. Right, so let's head back to Jupyter now. I'll just type in variables over here. Right, so let me create my first variable, and the name of that variable would be var1, and we can create a variable like this, tf.variable. So guys, you need to keep in mind that this v over here is actually capital. Right. So now after this, I would have to assign a value to it. So let's say I assign this variable a value of 20, and this is of integer type. So tf.int32. I'll run this. Now another thing to be kept in mind is whenever we are declaring values in TensorFlow, they have to be initialized. So this is how we can initialize all of the variables. So we have something known as global variable initializer. And when we invoke this function, all of the variables which we have declared would be initialized. I'll hit run. So now let me execute this inside a session. So says dot run of init, and I have initialized this variable over here. Now let me also go ahead and run that variable. Says dot run var1. Right. So we have the result of var1, which is 20. Now, since this is a variable, the value of a variable can be actually updated. So let me go ahead and update the value of this. So I will name this as updated var1, and the function would be tf.assign. And inside this, the first parameter would be the variable which I'd want to update. And after that, I need to give the value to which I'd want to update this. So I want to make this value of 20 to 25. Right. Now I will run this. So now this is actually a variable. We can actually update the values. So let me go ahead and do that. So the name of the updated variable would be, let's say, updated var1. And the function for that would be tf.assign. And this takes in two parameters. The first parameter would be the variable which we are supposed to update. And the second parameter would be the value to which we are updating it. So I want to make this 20 to 25. I'll hit run right now. Let me run this inside a session. Says dot run. And I need to pass in the variable which would be updated var1. Let me make it small v over here. I'll run this. Right. So initially the value of var1 was 20, but we have updated it and made its value to be 25. Now let's also go ahead and create a small linear model. So let me just type in linear model over here. And this is how our linear model would look like. wx plus b, where w and b would be variables and x would be a placeholder. Right. Right, so let me start off by creating w. So w is a variable. So w would be equal to tf dot variable. And I am initializing it with a value of, let's say, 10. And this is of integer type. So this would be tf dot int 32. Now, similarly, I will also assign the value for b. So b is also a variable and its initial value would be 5, and this is also of integer type. And finally, we have x, which is a placeholder. So x is equal to tf dot placeholder. And since placeholder does not actually take an initial value, it just takes a data type. So the data type is again tf dot int 32. So I'll run this, and now what I'll do is I will multiply w with x and add b to it. So the equation would be w cross x plus b, and I will store it in a variable and name that variable to be linear model. Right, so this is w cross x plus b. I'll run this. Now again, if I have to execute this, I have to run this inside a session. And since also I have created two new variables, I'd have to initialize them first. So init1 equals tf dot global variables initializer. I'll hit run. So now I will create a session. So says dot run, and I will execute init1 first. So I have successfully initialized these two variables w and x. Now I can go ahead and run this linear model. Says dot run. Now I would want the result of linear model. So linear model, and then I will use the feed dictionary. Now inside this feed dictionary, I would have to assign a value to this placeholder x. So x equal to, let's say I give a list of values over here, and the list of values would be 1, 2, 3, 4, and 5. Now I'll run this and let's see what do we get. Right. So if the value of x is 1, we get 15. So this basically means that 10 into 1 plus 5, which is 15. Now after that, if the value of x is 2, so this would mean 10 into 2 plus 5, which is 25. Similarly, if x is 3, that would mean 10 into 3, which is 30, plus 5 is 35, right? And same is the case for 4 and 5.
So let's go back in 1980s. There was this crazy guy called Geoffrey Hilton. He proposed that we could mimic somehow the mind, how a human mind works, and we can mimic the way it works, so that we can also try to make a thing out of it, so that whatever our mind is doing artificially, we can also do that thing. So he proposed a paper, and everybody said that, Hilton, listen, you are doing something wrong. This is not what is right. And everybody, didn't like uh, the way things were going on. But after 20 years, almost in late 90s, around 1999, he again came up with this paper. He brought in his paper, but this time with a proof, and he won a contest that is called ImageNet in 2004. This time he came back, and everybody had to listen. So we were at 2004 when he won the ImageNet. I have two people who I've already told that ImageNet is ImageNet is actually in a competition. It is held by a uh, joint vision of Stanford plus Princeton University. These guys come up, and they downloaded a corpus of images. Now they have a very large collection of images, around 1 million images, around covering 1,000 categories. They have. You can just click on explore, and you can see this tree around here. So what you have to do is that you have to make a model out of it, so that you can classify the images. So people used to make hand coded classifiers, and they were working, but at some stage they had to fail, because now let's say that fish, you are trying to detect a fish, but fish cannot every ways be in the same manner in which you are building the hard coded thing, right? Or let's say that you are trying to detect a cat, and then you say, okay, top right if it is a eye, top left it is a eye, and then it's a squishing mouth, then it's a cat, right? But now the cat face will not always be available to you in that particular fashion, right? It might be a top view, a side view, a bottom view, any view might come up, and at that time people used to fail. But in 2004, when Geoffrey Hilton came with his paper, the competition he won was with 94% accuracy, and that was never achieved, and it surpassed the human accuracy also. So that was where when people started listening to him and he came out, then he proposed slowly that, okay, that this is what I think, that artificial neural network is nothing, but that we are trying to mimic what is happening in our own mind, right? So if I say that, what is the theory, what Geoffrey said about neural network is that he said that artificial neural network is a computational model that is inspired by the way biological neural networks in our brain human information possesses, right? So I mean, most of you know this thing, that that our nervous system is made up of axons and okay, I'll show you the photo, that it is made up of axons and brains. I show you the photo, and you might be able to replicate. See, this is actually how a human nervous system is. Most basic diagram, and everybody of you might have seen this. So how this works is that there is a exact replicate copy of this. If I copy this, and you can attach it back here again. So these are the axon terminals that are connected to dendrites again, and this is how it flows. So let's imagine that your fingertips you can have your dendrites, and these are like small particles again of your pure neuron connected to your brain. So this is how there are like millions of these connected, and they're connected. If I take this, okay, one more feature of Jupyter Notebook that you already know, that you can add a markdown language. So what I do is I do escape M, and then I'll write HTML inside it. So I write img src is equal to, right? This is how you can write your, in this you can add that this is, right? Let's now look at it one by one, slowly, slowly. Okay, so these are called dendrites. These dendrites are the one who are like septicles. These are the one who are responsible for catching all the information and sending it forward to the nucleus. Now nucleus processes this thing and it sends to this axons and again throws it out to the axon terminals. Now imagine again that this is this copy, this is again replicated here, back here. So you can imagine that these dendrites are connected to these axons, right? And then they're flowing, 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 flowing. Now imagine, let's say that you touched a very small, a very hot glass, right? The moment you touch the hot glass, the dendrites at your fingertips, they sense that something is very hot there. So they send this information to your brain, okay, that this is hot. Now imagine this dendrite is processing the information, sending it to terminal, terminal to dendrite, and dendrite to terminal. It goes on, goes on, goes on until it goes to your brain. Now the brain says that this is very hot. You should remove your hand. Okay. Now this process is again flowing back to the dendrite, the original dendrite here. Let's say that this is the original dendrite here. Okay. And
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective as it is taught by IIT professors and industry experts.
your brain will say that this is really hot. You should remove the fingertips from the glass. And now when I'm saying that this information is going on, believe me, from your fingertip to your brain, there are like millions of these dendrites who are connecting and flowing this information. Now again, a process of reversal information flow is going on, and this time your brain is sending a signal that remove your hand from the glass. And this is again going back to the fingertip, and then you release your hand from the glass. But in real life, when you touch the glass and when you remove it, how much time do you take to remove this? It's just some nanoseconds, right? I mean, less than. Your reflexes are very strong. You just remove the hand out. But imagine what is happening when you do this. Your brain is not, your hand is not taking the decision of removing that. You might think that, okay, my hand is taking the decision to remove that. No. The hand is like a slave of brain. So every body part of ours is like a slave of a brain, right? Whatever we are doing, it is sent by the brain. The information is sent by the brain and then it's doing. This is how your body works, right? So it's a slave of your brain, and the brain sends the information, remove or attack, whatever it is, then it reacts. But it's really fast, right? Similarly to this way only, Joffrey said that, okay, this neural network, this is how even I will also build a neural net. Now I'll show you how a basic neuron looks like. Here it is. This is the image. Visualize it. Basic neural. It's not a network, it's just a neuron. But this is an artificial neuron. So Joffrey said that, okay, this is how I propose. Let's do the following. Let's say that your hand is not doing anything. Your dendrites or your nervous system is not, this basic neuron is not doing anything. Imagine that it's doing nothing. But it is reciprocating the information. But how it is reciprocating the information? By activating itself. So when you touch a hot glass or something, it activates itself and then only it's transmitting the thing, right? Now imagine if this would have not activated, it would have sent nothing, right? So this is also playing a very crucial role. See, brain is sitting somewhere like a million neurons far, right? He doesn't know what is happening to your hand until and unless this neuron is sending the information. So what information will the brain process if it doesn't have the information? So these guys are very much responsible for sending the information, and they send the information only when they're activated. So this dendroid will become, this nucleus will become activated, then only it will send the further information. And see, there is also a basic kind of a information processing is going on. It doesn't mean that these dendrites are just sending blank signals. See, I'll tell you more depth inside. See, these dendrites, they collect the information. These dendrites, they collect the information and they send it to the nucleus. Now, nucleus thinks that should I process this and send it forward, yes or no, depending on that, nucleus send it further. Right. Now, how is nucleus sending is, nucleus has a particular threshold value. After processing it, it says, okay, if I am activated by that processed value, it will send it further. If not, it will keep it to itself. So this is also how a basic artificial neuron, when I say artificial, it means that the one that we are building right now in deep learning, right? This is also built. Now what is happening is that imagine this round thing that you're seeing is the nucleus. This thing is a nucleus. But this is a nucleus, right? And these are the dendrites to it. This one, this x1 and x2. This is the way of thinking how we are intimating, and this is the tail, axon tail, and it is again connected to again a neural network. So it's a chain of multiple neurons going on. Now, if we go mathematically, what is happening inside this? It is nothing but a linear combination of all the inputs with a bias. I just went to the very human biological way and I just send a sentence. It's doing nothing. What it's doing is that it collects the input. Let's say that you have two inputs. Let's say that you have two inputs, x1 and x2. These are your two inputs. Now to every input, you will give some weightage to it. Let's say our weightage is here. This weightage is called W1 for x1 and W2 for x2. Correct? Now what I said, it is trying to build a linear regression, right? So what it does, it multiplies the weight of the corresponding input to itself. So W1 x1 plus W2 x2 plus it adds a bias to it. Now you will ask what is a bias? I'll say imagine that there is another input called x0. There is another input called x0 and the value of x0 is equal to 1. The value of x0 is equal to 1 and there is this weight associated to it that is called w0, right? So this bias is added to it and then you add this. That's it. You plus all these values, multiply plus all these values and you give this output to something called y. This is all a neuron does. Make sense? It's very important that you build the intuition that what is happening here. So this is the most basic, it's the smallest part of a neural network that you can pick. And the smallest part of a neural network is doing this. That it takes all the inputs that are coming to itself, give them some weightage, multiply the weightage to the corresponding input, and then sum all these, and then add a small bias to it also. That's it. Over. How is this weightage and bias being introduced? That who is okay, x1 and x0, x2 and x1, I can say okay, someone is giving to us the input that what is the temperature of the glass. Let's say it is coming from the outside environment, x1 and x2 is coming outside, but who is giving this w1 and w2? So okay, so the answer is that in a artificial neural network environment, at the very first instance, they are randomly allocated to it. So see, you all guys have learned ML, right? So how does ML work? ML says that I know the output and depending on the output, I have to give some weightage to these inputs so that they can give me the output. Now, you know that the output will be Y. You know that the output is going to be Y, right? Now, you want to make some equation where Y is equal to x1 plus x2. Okay, and now this is not the correct answer, right? X1 and x2 will never give you y1. So what you do, you add some w1 here, some random w1, and then here random w2. What it will do, it will not give you the answer. W1 and W2 will not give you the answer. You will do some corrections again in W1, W2, and ultimately it will give you Y. So this is what is happening. At the very first instance, you will take W1 and W2 as random. First is that does the process is reverse? Yes, it also reverses itself. The model will not only go from x1 x2 to y, but it can also come back from y to x1 x2. And second, let's say that he's asking Shivam, does it process recursively? Recursively, just imagine that there are like thousands of, now I'll draw it again to show you. This is just a very basic one, right? Now imagine what is going on here is that this is the small that you saw, right? X1, X2, and it is giving some Y. Now here it is again, there is a X1, X2, and then this is giving me Y. Now this Y and Y1 will become an input for some other cell. And then it is giving here. So are you imagining how will it look like? This becomes this, and this will become again an input for some other. So these are like connected. These are like throwing information from one to another, one to another, one to another, right? But this is how it works. This is how a small network looks like. And this is if I write down the theory, it says that the basic unit of computation in neural network is a neuron, or often called as a node, right? And came right it very right. This is called a node, or you can say it a unit also. So it receives input from some other node, from an external sources or external source, that I was saying right also, right? The x1 and x2 might be an input from another neuron, or it might be given to you directly from the external environment, right? Computes the object each input has an associated weight to it, which is assigned on the basis of its relative importance to other. The node applies a function f to the weighted sum of this input, right? Let me take an example that you're working on a machine learning problem where you are trying to find out the loan defaults, right? That in bank you have multiple people who take the loan. Now the bank wants to know how will this person repay the loan or not, right? Now you already have a historical data with you. The bank will give the data to you. Okay, let's say that this is the data with you. So in that data you already know that if this is the feature of a person, this is the credit history of the person. Based on that, they will also give you that, okay, he paid, he didn't paid, he paid, didn't paid, right? And based on that you adjust your model, right? So there also you have a x and y with you. You will have your x and y with you at that particular instance also. Okay, so everybody gets this this function thing, right? That's how this function is working. This function f is called the affine. So the f function that you see, this is called the affine thing, and it's doing nothing, right? You saw that this is it's doing a linear thing here, just multiplying the weights the corresponding x1 x2, and you might now consider x1 x2 as the importance feature. So the more important x1 is, the more higher the value of w1 will be, right? The more lower the value of w2 is, it means it doesn't make much sense to y. So everything that we will now talk will be with respect to y. So the x2 is not making much sense to y, so the value of w2 will be very less. Let's say y is dependent on x1, so this value of w1 will go more higher, right? And then your bias you already have, this is a static thing, right? Because the x not associated to it is equal to 1, right? Let's now go back at what further happens here. Now you get the y out of here, right? Now this y thing is a little, you have got the answer, and this might be greater than 1 or less than 1 also, right? So there is no measure of this answer. It might happen that w1 w2 is very small. Let's say w1 w2 are very small, then the value of y might be almost equal to 0, right? Or let's say that w1 value is very high, like very high, so the value of y might also get very high, right? So now this might bring some bias, this might bring some ambiguity to our model. This y might be sometimes, next to infinite, it might be equal to infinite, or it might also be equal to 0, right? Depending on the variables. And we don't want that. We want our y to be in some particular range, right? We want our y to be in some bonded weights, right? Then comes next guys whose names are activation functions. Activation functions. Now we got to know that how this y is made, right? How this y is ultimately achieved. Now to adjust the value or squeeze the value of y, we need some other thing, right? We need something that can control the value of y, and these are called activation functions. Now what activation functions does is that they will take the value of y and they will squeeze the value of y in some certain range. What they will do, they will squeeze the value of y in some certain range. So we have multiple, let's say we have a step function, we have a 10h function. So let's come back what this activation function is. So you understand that the value of y, how it is calculated, right? It is now totally dependent on w1 and w2. If the value of w1 and w2 is very less, I mean 0.0000, or let's say 10 to the power minus 23, then the y is going to be very less, right? Next to 0. Or let's say that the value of w1 and w2 is like 10 to the power positive 48 plus 48. So this might be very high. The value of y might be very high. There might be no standard to control this value of y, right? Mathematically, there is no this value can go from negative infinite to positive infinite, right? And this is not a very good range to get about a particular output, right? So what we do is we introduce something that is called activation functions. Now what this activation function will do is activation function will make sure that your output that you have got y should be in some particular range. What it should be? It should be in some particular range. Now how do you decide that who is going to be in what range, and how is that range called? See, the activation function, if I ask you mathematically, the mathematical purpose of introducing an activation function is to squeeze the value of y between some variable called 0 to 1, right? Majority times. So the purpose of activation function is to bound the y in some range, right? And this range might be -1, say 1, 0 to 1, or sometimes 0 to infinite. It might be different things, right? I was at this thing that mathematically the value is to be squeezed between 0 to 1, but if I talk to you about statistically why I am doing this is, now imagine till here, till this particular range, your model is a linear model. Everybody agrees with me, right? This is a linear model. Nothing non-linear have been done till now, right? All the things that we have done till this step in this circle, everything is linear. There is no non-linear thing, right? Now linear things are a little bad at classifying things if there are more than 3 classes, right? If I ask you, can you, if let's say there are 3 classes, one is like crosses, right? One is circles, right? And one is some triangles. Now can you make a single line and can divide these 3 data? No, right? If it would have been 2 classes, you might have drawn a single line and you might have divided the data into like 2 classes, right? But if it is a 3 class data, how will you divide this? You have to ultimately make a triangle kind of a shape, or this kind of a shape, right? Then only you can divide the divide this thing, right? So I'll show you a photo also. Let's say, let me give you an example, then I'll show you how this works. Okay, can any one of you, now this is this thing in front of you, everybody can see your data. There is this red dots and there is a blue triangle in the screen, right? Everybody can see this. Now can you make a linear model that can separate these two things? This can only do in a 2-dimension, right? But if I say you that, okay, see a magic, anybody wants to try this thing? How will you do? No? Okay, what I'll do is I'll remove this now. So what I did was I introduced a third dimension, and now I could easily separate by introducing a hyperplane here, and then I can say, okay, something that is above this hyperplane is red, something that is below this hyperplane is blue. Makes sense to everyone, right? So this is why we do activation function, to make sure that we want to classify things more better, to make things more clear. We do a activation function. So mathematically, why we are doing activation function? Because we want to squeeze the value of y somewhere. But if I talk statistically, what we are doing, we are introducing non-linearity in a linear model, because linear models are very much not capable of classifying things in when the number of classes increases. So now we saw that as soon as we increase the linearity, if we increase a dimension in the data, if we introduce non-linearity in the data, what it is doing? It increases the chances of making a linear separable model, right? Right. So if I say in three times, first mathematically squeezing the y. Second, if I say graphical thing, why we are doing this? Because we want to introduce a new dimension. And statistically saying why we are doing this, because we want to introduce non-linearity inside it. Now you might be asking what these functions do. It's a very good question. I have activation functions graphs. See, this is how a sigmoid looks like, a tanh looks like, a ReLU looks like, and see everybody is bounding. So see, sigmoid is bounding between 0 to 1, tanh is bounding between -1 say 1, ReLU is bounding from 0 to infinite. So it lets go everything that is going above. Yes, we have step function also. Step function says that you can go, if something can be only have two things, either 0 or 1. If something is negative, it goes 0. If something is positive, it goes 1. It's a step function, sigmoid, tanh, ReLU. So there are multiple things. These are doing the same thing that we want to do for a activation function. ReLU, you can understand that if something is negative, it says it's a 0. And if something is positive, it lets go whatever the value of this is, right? I write the variables in here. This is what brings in. Sigmoid is this, tanh is this, and ReLU is this, right? What is the maximum of 0 to 1? That ever value it will take, right? This is what activation functions is. Let's say that you have this thing called y1 and y2, right? And now the value of y1 and y2 is very large, right? So this y3 will become ultimately also very large, and this y4 will become also very large. And we know this is not the exact thing. We always expect our output to be in the form of 0 to 1 if it is a classification problem, and if it is regression problem, then it will always be in some range from 0 to 1, right? You all agree with me, right? In machine learning also, whenever you did a classification problem, you one hot encoded the problem. So you never said that the output is going to be a C80 cat or DOG dog, right? You always said that, okay, if 0 comes, this is cat, 1 comes, then it's a dog, right? You did the same thing, right? In machine learning also. Or if it was a regression problem, then you always regress a value from 0 to 1 with a multiplicative factor, right? So this is what is happening here also. The y3 and y4 value can never go up beyond a limit. To control that limit, we have to squeeze the value. And see, when I'm saying squeezing the value, that is in mathematical format. But if you see in statistically, what we are doing is that we have to introduce non-linearity into the data, right? Because linear data are not linear equations are not good in separating non-linear data, right? Right, this becomes separable. You see, now it is very much separable just by a simple hyperplane. Okay, so coming back to a feed forward neural network. So see, this was the input x1, this was input x2, and now what a feed forward neural network expects is that a hidden node should be connected to all the inputs. What does it expect? It should be connected to all the inputs that are in the previous layer. So this is, let's say this is called layer, input layer. Wherever your hidden neurons, this is called hidden layer. And your outputs are here. This is called a output layer. Now, when you are building this feed forward neural network, your responsibility is just one, that whichever neuron you're standing, let's say we are standing on this particular neuron, let's say this neuron, this neuron. Now, the only thing that okay, this is not a neuron exactly. Oh, sorry. Let's say we are standing on this neuron. Now, the responsibility is just this, that if you go to the previous layer is the input layer, all the neurons in this layer should be connected to this hidden node, right? Similarly, output 2 also expects the same. You go to the previous layer. So this is the output layer. What is the previous layer? Hidden layer. So all the neurons in the hidden layer should be connected to the output node 2. Make sense? Or if I make it more easily, let's say that whichever neuron you are standing, just go to the previous layer, and all the neurons in that previous layer should be connected to this particular neuron, right? So what you are doing is you have stacked all your neurons one by one in some format, right? So all your input neurons. So see, whatever you made in this above statement here, in this above thing here. So this x1 and x2, this is x1, x2. This might be x3, x4, x5, x10, right? So these x1 and x2s are what? Inputs, right? So what you do is you collect all these and you just put it inside a layer here. This becomes a hidden layer. now you will not only have one neuron, you will have multiple neurons, right? Also, what is happening is that what you have done is, rather than having just one neuron, what you have done is you have made multi-neuron system. So this is a feed-forward multi-neuron model here. So what you are seeing in the previous photo that was image that I showed you, that was just a multi-input single neuron, but now you have multiple neurons. So what you do is you stack these neurons in this layer, then you can have, so this is just an example. What you can do is you can have an image like this also. So now if you see Tarun here, so what is happening is these are your inputs x1, x2, x3, x4, right? This is your input layer. This is your hidden layer 1, where all your affines and activations are happening, right? This is your layer 2. Again, all the affines and your activations are happening. And this is your output layer. Hidden layer HL2. This is HL1. And this is input layer. So what is happening is that, let's say this is called neuron 1. That Y1 just marked. So let's say this is N1. This is called neuron 1. Now what is happening is that this neuron 1 is connected to X1 also, X2 also, X3 also, and some bias also. So what is happening here? This affine will be happening here. What will be happening? It will be here as a W1 X1 plus W2 X2 plus W3 X3 plus some bias B will give some output called Y. And here you will be having a very small activation function also residing here, right? Similarly for this N2 also, this N2 is connected to all the inputs, right? This N2 is connected to all the inputs. This N2 is connected now. It is connected to this, to this, to this, and this. Now N2 will also do some affine and then bring some activation, small activation function here, and it will also give some output called Y2. Similarly, Y3 will also be here. Now this Y1, Y2, Y3 will become input for these neurons. Let's say we call this neuron as N4. Now this N4 is connected to this, this, and this. Similarly, again affine, and let's say it gives the output called O1. Now O1 is here. Similarly, O2 is here. Now this O1, O2 will also become input for this. Let's say we call it O1 right here, right? This is O1. Y4. Let me remove this. Sorry. We were here that there is this some output called Y4, and there is some output called Y5, right? Now what is happening? Y4 and Y5 will become output for this O neuron, and they will give some output O1 and O2 similarly here, and then you will have outputs, right? This is how a multi-layer neural network works.
How will we know that how many layers?
Correct. This is one of the very good questions that first of all, how many layers do you want? This is the layers that you have, L1 and L2. Now you might have another question that, okay, in one layer, how many neurons can I fit? So there are currently 4. I can fit 5, 6, 10 also, right? I can fit 10 neurons also. So who is going to tell me that how many neurons and how many layers? This is what data science you are going to do here. I mean, everything is built for you. This neuron thing and this all thing this is already built for you. The only thing that you have to do is that you have to come up with the optimal number of neurons and optimal number of layers for each neural network. And now who is going to decide this? Very good question. This is you who is going to decide this. And how? Okay. So first answer is that hit and try, that everybody will tell you, and I am also telling that the first approach is hit and try. Let's say that you are doing a very new problem. I mean, you don't have any idea, you are just doing. So one thing is that you'll go with the hit and trial model. Second is that as soon as you become a little bit expert, now you start learning, okay, this is how my model is reacting to this particular neural network layer. So see, this is a very good question, but this is also an advanced question. Now see, when this let's say this is called neuron 1, when this neuron 1 is connected to x1, x2, x3, there is a weight called w1, w2 on this layer, and w3 here, right? So But when this N2 is connected, this is not W1, W2, W3. There is W4, W5, W6. So when this X1 is connected to this N2 here on this line, there is another weight, that is W4. So imagine how many weights are there. For 3 inputs, 3 neurons, there will be 9 weights, right? Now there are 9 weights. Now imagine here again that you have 3 inputs and 2 outputs, 3 to 6, then you have 6. So 9 plus 6. Then again here 2 to the 4. So you will have 2 plus 4. So 9 plus 6 plus 4 is 19. So 19 weights are there, and then you will have 3 biases here, right? So 19 plus 3 is what? 22. So for the small neural network, you have 22 values that you have to predict, right? Because y1, w1, w2 we have taken as random, right? And biases are also random. So you have to adjust them in a very optimal way so that you can get the output as y. So now imagine that you have 22 things that you have to train here. 22 things that you have to predict, not predict, but you have to optimize, right? And now let's say that you have a data only for like 10 rows. Now does this justify that you will have 22 things to adjust in the 10 rows of data? So this is called capacity building. So what you have to do is that you have to check your model if your model is even capable, if the data is even capable to adjust these values, right? Let's say that you are just doing a simple addition, right? If you give two numbers, your model has to give some output, right?
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Now let's say that you have 1,000 examples for it, but now you're building a like say 1,000 layer and 1,000 neuron per layer, 1,000 neurons, and then you have 1,000 layers. Now does the model require this much of data? No. The data will be lost in some third or fourth layer only, right? And see what I just said in just last 2-3 sentences, this will come slowly with the experience in you also. So what you'll do, so whenever a new problem comes to me, I first of all read the research paper through it. See, because we are not researchers. Let me be frank with you. We are not researchers who are going to make things. We are deep learning engineers here, right? We have to implement the engineer and we have to solve a business problem through it, right? So what you do is first of all you read some papers out of it, right? Then you get the intuition of how do you build a neural network around it. Then I do some hidden trial error. Okay, this is how you build, and this some changes, and then slowly you understand. Okay, when I change this thing is affected more. Then you reduce and more. Then you have some prior knowledge also, like that I told you. Keep capacity. That what is the capacity of the model? Let's say that you have a very large data, but you are just building one layer. Then the data is underfitted, right? Or let's say that you have very less data, but you have made a very big neural network for this. And this is called overfitting, right? You have a very over number of neurons for your model to be predictable, right? So slowly you will you will have intuitions, and this is I will tell you, with your when you will be doing your first problem in a neural network, you will understand slowly. See, you might be thinking that I'm not taking to you practical, right? I am not telling you about any real world example, but this theory is really important. I might directly jump to the code also, but that will make no sense to you after 2 or 3 weeks, right? Because code anybody can write. Until unless you don't know, okay, what will happen is the next after 2 or 3 months, when you will be making your own neural network, you will fail that. Okay, which activation function to use? Then this thing will occur. Okay, so see, this is what he is talking about to all the people. This is what he's talking about. Let's say that you want to add more layers. So currently there is only 2 hidden layers. You want to add more, add more, add more, right? If you want to increase per layer, you want to increase the neuron, you might go like this also. Okay, you might like, I'll reduce it to like, let's say 6. This I'll reduce it to 4. This and 2, and this is 1, right? This is how your neural network will look like. These are the 2 inputs. Now every input is connected to the every neuron in the first hidden layer, right? Then second, then third, and fourth similarly. And this is how the data is flowing inside it. You can see now slowly when we put every x into each neuron, does every neuron give same y? But no. See, Kim, if we come here it would have been the same if they would have same W, right? So if x1 is connected to n1 here at this layer, it has W11, right? But when x1 is connected to n2 here, it has something called W12, right? So there are different weights. So it is coming from x1, but because it is connected to different neurons, different input neurons, they will have different weights also. Understandable? So to other people, what Kame is asking is that, okay, that you are doing affine. I understand that you are doing affine, but let's say that, let's go back to affine equation. Because the value of x1 and x2 is constant, the output will always be constant, right? But no, because y1 is made up of this equation, and this equation is also driven by w1 and w2, and the w1 w2 values are different, the value of y will also be different in each case, right? Makes sense, right? And when you are asking about a real world problem, this is how a neuron will work. Okay, this is how it actually works. This is a intuitive GIF. Okay, so what that I took two words in overfitting and underfitting, and how do we address this problem? So what we do is that we divide our data into two parts, and I think you must have also done this in ML also, right? Training data and validation data, right? Not two, just three parts, right? Training, validation, and testing, right? So what you do is whenever you are training your model, you just make a slice, another slice of data, and this is called validation data. And you will never show this data to the model, right? So no, you are never going to train your model on this particular data. So what you're doing is you will never show this data to the model, so model will never come to know about it. So it will never learn about it also. Now once your model is made, what you will do is you will test it on this data. What you will do, you will test this on this data, and then the model will say, okay, this is how it looks like. Okay, this is what the predictions are, and then you'll see the predictions, and then you'll compare the predictions. Okay, this is not what I wanted, so the model is underfitting or overfitting. Now how will you do underfitting and overfitting? You'll do a confusion matrix, and then you'll see that if the model is just giving out you only one classes, let's say that your data had 10 classes, and if the model is just pushing towards one class, then this is overfitting. Your model is overfitted at a very lot level. Okay, now this dog image, when we expand this image mathematically, this will come out to be three things. One is called x1, x2, and x3, right? Now what we have to do is this x1, x2, x3 is done towards from our end. Now this x1, x2, x3 is connected to this neuron 1. Okay, now x1 is connected to n1, this is called w11. But when it is connected to n2, it will have some another random weight called w12. w12. Make sense? So number of neurons you can increase as much as you want, as much. You can have n3, n4, n5, n6, n7, doesn't matter. But you have to make sure that this w11 is not the same weight for all n1, n2, n3, right? Cool. Thank you. Thank you. So inside the matrix, you can see there are multiple values. The value ranges from 0 to 255. 255 is for like utter black, and 0 is for white, right? The value ranges from 0 to 255. You can see the more black it is, the more the value it has, right? So what is happening is that these are the multiple inputs that you will have inside your images, multiple inputs, and all these inputs will go in here. So in this particular example, you are seeing 3, but this time you will have more. So these all the zeros in first, all the values in second, third, fourth, fifth row till the 28th row. You will have all the numbers inside this input layer stacked one by one. So ultimately you will have 28 cross 28 is equal to 784. So you will have 784 inputs normally for this small image. And this is you guys were all asking about me how this will work in real world. So real world, let's say that you have an image of 500 cross 500. So that becomes around like 25,000,000. That means 2.5 million inputs you will have for single image, right? And let's say that you have 10,000 images, so this becomes multiplied by 10,000, right? So these are the number of inputs that will go inside one by one by one by one by one. So one image will go one time, two image will go two, second time, third time, and then based on this, the output is the model is going to do some calculations in the hidden layer, and then it's going to predict the output, and it will give you some output at y. Okay, so now we'll turn up the pages and we'll move to multi-layer perceptron. But now we might have multi-layer perceptron architecture. Now a multi-layer perceptron architecture simply means that you might have multiple hidden layers. Okay, so apart from having a input layer and output layer, you might have hidden layers in between of them also. Whereas a single perceptron was only a linear function, a multi-layer perceptron will have multiple linear and non-linear functions, a combination of them, right? I'll show you this again just to memorize things up. This is x1, this is what your input, x1, x2, these are your two inputs, right? Now you have a single hidden layer right now. Here you have this one neuron here. Now you already know that what is the calculation going on inside. There is the affine function. Affine function, what it does, it takes input from all the behind layer neurons, right? So if I say it takes input from all the behind layer neurons, and if this is a hidden layer h1, then it means that it will take inputs from all the neurons inside this input layer, right? So this is x1, then this is connected, this is x2, this is also connected. Now whenever a neuron is connected to another neuron, it is connected through some weightage corresponding to it, right? Let's say this is w1, this is w2, right? And then you might also have a x naught. Now the x naught is always equal to 1. So you might say this is just a bias as b. Now this b is like constant to this neuron also and to this also, right? I change this and it's not come to this. Okay, so now this is x1 and x2. For this, when they are connected to this neuron, the one that is downwards, and this neuron, they are connected again to some weightage, but this weightage might or might not be equal to the w1 that is the one that is described here. The one described here, this is never going to be equal to this one, right? So these are different weights associated with different. So you might, to make it more simplified, you might think that whenever there is a string connecting two neurons, it is connected through a weightage, and this weightage is different for each one, right? This weightage is different for each one. You might also see the equation here down here, w naught in plus 1 plus w1 x1 w2 x2. Now you know that w naught is equal to 1, so we have replaced w naught is equal to 1, sorry, x naught is equal to 1, so we have replaced x naught with 1, and w naught in itself, you can say w naught, or what people like to say is it's called as notation called b, and this is called the bias of the neural network. Okay, bias, and these w's are called the weightages, right? And then you do again a summation out here, and this time you do the final output, and then you give the output right here, right? You also remember that after every neuron there is also activation function which is sitting here, here, and here. They are also present on the outer section also. This and this, they're present here also. So they, and then you read that there are different types of activation functions. From step function to sigmoid, then to uh, softmax, we have different. I'll slowly go through each of them, and then you'll understand that how they interact, and how you might be also changing them according to your needs, right? So now once we are done with this perceptron layer, now okay, so this is called a feed forward neural network. Just one thing, feed forward neural network. Once you come from here, this neuron, you go till here, then there some calculations goes on, then you come to here, which is taking connections from this and this neuron, and then you give the output, right? Now let's say the output comes out to be some y1, whereas the actual output was, let's say, y, right? Now there is the error associated to it. So you say that you have an error, and what is the error? Y minus y1. This is the error, right? Y was the actual answer that should come, right? But you are saying the answer is y1. Then y minus y1 is actually the error. What it is? It is actually the error. This is actually the error y minus y1. Now your model, you say to your model that model, you have done some kind of mistakes. Now if you go back inside your session, if you go back to your session, you might see some errors inside it, and that error might be equal to y minus y1. So go and do the changes. Now if you see our function that we have done till now, the result through which we have come till now here at this point y1, it is all how much dynamic things you have taken, I mean non-static things you have taken. See, x1 is always going to be static, right? This no one is going to change this x1 and x2 because these are given by the data itself, right? So the data can never change itself. It is you who has to change, right? And then what is the thing that we have taken assumed? These are the values of w1 and w2. W1, W2, and W0. These are the similarly these W's here. I mean all the W's that are here, all the W's that are here, these values are something that you have assumed, right? So now what the model says, the model says that the value that you have assumed, W1 and W1, W0, W till Wn, these values might have some kind of a correction because the current values of W are present, are giving some error, that is y minus y1. So to reduce this error, you go back and check your values of W and switch the values of W to such an extent so that they minimize this error, right? Whatever I said just now statistically, right? Makes sense to everyone, right? What I just said here. Okay. Now this thing is called backpropagation. Now this thing is called backpropagation. Now backpropagation, if I take the copy of then how do can we use different activation functions also? Yes, it depends on the problem that uh, uh, what functions do you want to choose. So I'll tell you my particular example. So I was working on this library that is called DOLD5. Here what we are trying to do is that we are trying to restore colors into images that don't have color. So I mean if you talk about images that are like from that are before 1924. So we have some German artifacts. Those are before 1924, and those are totally black and white images to us, right? So what we have to do is that we have to fill images inside it. Now, filling images inside it is, I'll tell you, it's a complex process, but there is a form of images that comes out. That is called the LAB images. So if someone of you who has interest in photography uh, or if you understand what images are, then you might have heard this term called LAB. LAB images to convert. Now the range of LAB images is from minus 128 to 128. So here my task. So if generally if you see the activation function, if you remember from the previous class, all our activation function from ranging something from 0 to 1 or minus 1 to plus 1, right? Now I wanted something that has to go from minus 128 till plus 128, right? Then how will these things two go? So accordingly you can change your activation function and you make your own function out of it, right? Make sense? Now this is one of the most not used, but this is one of the most obvious things in backpropagation. This is in AI, and why this is famous, because this is the main backbone for AI. This is how AI learns itself, right? So people say that AI is learning from itself. No, it's not learning from itself. It's learning from the errors. Whatever error it is making, it goes back and it checks. So see, a human tendency of error checking is what? Let's say that you are doing some calculation and you do some error. What do? You go back again to the calculations and you check, okay, I did this mistake, and then you correct it, right? This is also the way how machine is also understanding. So what machine does, machine does some calculation, it calculates that there is some error, then based on the assumptions that it took, or based on the assumptions it took, it thinks, okay, these are the things I assumed and this is now the error. So what it does, it goes back and say, okay, I will change my assumptions, I'll tweak my assumptions, and then I'll see what is the error again. This is a iterative process. So again, let's say that in backpropagation, what will it do? It will try to change the values of W1 and W2, right? It will try to change these values of W1 and W2, and then it will again go in the forward direction, and it will again see, okay, again there will be some error, but this time the error will be less as corresponding to the previous error, right? Now again it will go back, then come forward, again go back, forward, go forward, invert, forward, backward, forward, backward. This will happen multiple times, and at one point the error will saturate. The error will look like this. The error graph will look almost like this. Here error is on the y-axis, right? And this is whatever you say, time on the number of epochs or steps, let's say, as of now. Steps means that how many times you have gone forward, backward, forward, backward. So you can easily see here that that the error was very high at this particular point, but then it slowly decreased. It decreased till here, but now it's almost saturating. So it's like almost saturating. And at one instance it will be like parallel to the x-axis. It will become parallel to your x-axis. This is how it looks, right? Let's move forward. So what happens is, I've already told you that all the edges that you are hit, that you see here, that all these lines that you see here, these lines, these are called edges. All the connecting things are called edges. Now for every corresponding edge you have a weightage, right? For every corresponding edge you have a weightage, and these weightages are by default randomly assigned to you, right? Now they are randomly assigned at the very first point. When the problem start at that particular instance, these are like randomly assigned to you. Now for every input in the training data, the ANN is activated and its output is observed. This is what I told you also, right? That once we'll do all the calculations, we'll do the first feed forward neural network. We'll check what the output is, and then the output is compared with the desired output that we already know. And the already know, this is also, you might have heard this term again and again. This is called ground truth, right? So see, deep learning may, you might have heard, this is not equal to what traditional technologies. In traditional programming, you have been given the input and people ask you output. But here it's not like that. Here they will give you the input also and the output also. And then you have to define some way to convert this input into output, right? This is how machine learning works, right? Because they give you input also and then they give you output also. So like say, let's first, on the first example, if someone tells you that you have to do some image classification problem, then this is not like they'll give you at the very first instant, this is the image, now tell me what it is. No, they'll give you a training data set where they will give you the output also. With the image, they will also tell you that, okay, 9 is written here, 5 is written here, 7 is written here, right? So you have the ground truths with you also. Now what you'll do, you'll compare your result with the ground output, and then the error is propagated back to the previous layer. If you read the line propagated previous layer, the error is noted and the weights are adjusted accordingly. This process is repeated till the output error is a predetermined threshold value, or where you think that it is being saturated. Right? This is what I also told you. Now, if I tell you that how it goes, okay, let's see one by one. Mathematically, I'll show you one by one also. Now, see, it's pure maths. Okay, just a little attention, and then we'll be here. Let's say this thing is called, okay, or otherwise, what I can do is I'll just pick up the smaller problem, and then I'll show you also how it is done. Just a second. Let me search for the image that I have. Let's go. Let's see that error is equal to, I'll write it down. Error is equal to, let's say, y actual minus y predicted, right? Let us write down error is equal to this. I'll write down. Okay. Now if you see that how is this y1 calculated, then let's say that we had an input called we had an input called I1, and let's say I2, write down, and let's say that we only have this one. Okay, let's make it more simple, right? I will take just this image. That will make you understand how things work, right? Let's copy this. Okay, I'll write it down. Okay, this is the example, right? So now we have input as x1 and x2, right? And we have an output called y. Let's say that the actual or the desired output be ya, right? This is what we require from them. This is how we have, and the value of y is equal to the value of y is equal to w1 into x1 plus w2 into x2, right? Everybody agrees to this, right? That how is this calculated, right? Now the okay, and let's then define error. Error is equal to y minus y a, right? Or whatever you want to say, y a minus y doesn't make much problem to us, right? This is how this is working. So now if I say E is equal to y minus y a, then I can say E is equal to, instead of y I can write w1 into x1 plus w2 into x2 minus ya, right? Now if you open up this, doesn't make much sense, but let me write it down. W1 into x1 plus w2 into x2 minus ya, right? Now sorry, okay, now the error is this, right? Now what do you want to do? Now the final equation of error is in front of you, right? If I write it down, the final equation is in front of you. You can now do, you have the final equation in front of you. Now you have to see that how to minimize this equation, right? How will you minimize this equation? This is the equation of error in front of you. Now what you can do is, now you might be thinking that okay, this error equation is just a simple linear equation, I can solve it linearly. Now imagine that instead of x1 x2 you have 1000 xn, right? Now this equation is not a 2D equation. Now this is a 1000 dimension equation. Now you cannot just simply do things and just check it around, right? You cannot just do it like that. You have to, you cannot just plot a graph and you can look into that, right? This is a little more complex than we thought of it, right? If I show you how the graph might look like, right? The graph will look like this. Don't just read this, just for the time being, forget this thing. Just don't read these things, okay? So what I can do is, I say okay, this is your error equation, or let's say error I can also say j of w. You might see this terminology j of w as error, okay? Okay, when you plot this thing here, now what you can see is, see, x1 is what? X1 is a constant, right? X2 is a constant and y is a constant. You all agree, right? That x1, I will put a star and say x1 comma x2 and ya are constants, right? You cannot change them. These are constants, right? They make no effect to e. The one that might change e is w1 or w2. Okay, for a fact, none of you told me, but we missed a bias also here. Bias b. We missed this bias b here, right? Say this b, but this b is, I mean, it's not going to make some effect to us, but still, just for the courtesy, let's put this, right? To anyone, any doubt is still here, please ask me questions, right? So now we can see that okay, what is happening is that e is only dependent on w's, right? E is only, the error is only dependent on w1 and w2 and b. None of the other people are changing this e. So what we'll do is, we'll try to plot this error with respect to the weight, and we'll see this is how the graph looks like. And what do we want to do with the error? If error is ya minus ya, what is our aim? Our aim is to make ya is equal to ya as equal to y, right? This is what our aim is, right? If ya is equal to, then we are saying that the error should be equal to 0, right? Error should be equal to 0 or tending towards 0, right? But if I say mathematically 0 is, I mean, if I say statistically, this error is never going to be 0, right? This is never ever tending to 0. So what our main focus is? Our main focus is that if e is here, our main motto is to minimize the current error. Whatever the error is, we have to minimize this error. Now the value of this error can be found here, right? You can simply see the graph and say okay, this is the value of e. Just take the value of w's and plot them, right? But as I told you, Now these errors are not just two inputs. We have like 1,000 inputs, so we might have 1,000 W1s and then one B also. So we cannot just plot it. So it will become a 1,001 dimensional graph. You cannot just plot it. So now we have to think mathematically that how can we minimize the error E. Now minimizing the error E, but we also have the like the equation of E also. We have the equation. Don't think that we have the graph, just think that we have a equation of E also, right? This is above, right? And equation of E is somewhat like this. If I copy this from here, this is somewhat like this, right? This is somewhat like this. This is what the equation of E is, and this is how we have to minimize. Now in mathematics, we have learned, in inferential mathematics, we have learned that if you want to minimize any curve, if you want to minimize any polynomial curve of the order greater than 2, what is the process? If you want to find out, if you want to know that where is, take the first derivative. That's very much correct. So as Omar said, that you have to take. So see what the first derivative tells you. The first derivative tells you that wherever there is a change in the slope of the graph. If I talk about what we learned in our higher education about differentiation, was that differentiation tells you that point coordinate where the graph changes its slope from positive to negative or negative to positive. So if you take the first derivative, it will tell you this place. See, it was in negative slope, then it came in positive slope. Now again here, when it was in positive slope, then it came into negative slope. Again positive, negative, positive, negative, positive, negative, positive, negative.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
So it will tell you all the places where it has uh, changed the slope from positive to negative or negative to positive. Vice versa, it's possible, right? So this was how we talk about inferential mathematics. But if you go in descriptive mathematics, it says that what is a derivative of a function? A derivative of a function when you have a tangent that is parallel to the x-axis, right? When it is parallel to the x-axis. So how where will be the tangent parallel to x-axis? Whenever there is a slope that is equal to 0. So if the slope was from positive to going to negative or negative to positive, so both the mathematical percept tells you that there is a change in the slope in that, right? So similarly, we can know that where are the positions, where are the places where we can get a change in the slope. Now, as Omar very he suggested that we will get all the points where it is maximum and minimum also, and we just want the point where it is minimum. I mean these points, we are interested in the one that are by dotted by green. Either this, either this, either this, right? But now again there's a problem is that these are very higher error. This one that I'm just marked as E1, this is a very higher level of error, right? We don't want a higher level of error, we want a lower level. This one we want the E3, we want E3 to be our error. So what we do, we take double differentiation. We first take differentiation, then we take double differentiation. Now double differentiation, then Omar, can you tell me what is the condition if it is less than equal to or equal to less than 2? Okay, I'll tell. Now with the first derivative you can know that where is the slope of change, but if you want to know that what it is, if it is a maxima or if it is a minima, how do you know it? You know by doing a double differentiation of that thing and then checking its dimension. So if the double derivative of any of your function is greater than 0, if the double derivation of a function is greater than 0, then it is a minima, right? And if the double derivation of any of your function is less than 0, then that is maxima. These are the conditions. Then you will check accordingly and you will go for minima. Now again the problem is that okay, now you will reject these points, you will reject all. Okay, so you might discard this, you might discard this, you might discard this, you might also discard this, right? So you will you will remove all these blue points. Now you will only have the green points with you, right? Now you want this E3 to be there, right? Now we don't have any mechanism through which we know that we have reached global minima or not. This is the dilemma in deep learning. And so slowly what we do is now understand this mechanism. This is called a this whole thing that I'm showing you right now is called gradient descent, or GD, right? You might have also heard this as SGD, stochastic gradient descent. When you do a gradient descent in batches, it is called stochastic gradient descent. Okay, so now you have seen this one thing, that now the E is dependent on either W1 or W2. So what you will do is you will take the derivative with respect to one time with respect to dW1. So what will happen? It will say x1 and then everything is equal to 0, right? Because these are all constants. Am I correct or wrong? What I'm doing is I'm trying to take a derivative with respect to W1. What will happen? X1, correct. X1 into 1, totally correct. Plus W2 is again a constant, plus constant plus constant. Makes no sense, right? That's there. And if you want dE by dW2, then what will happen? It will give you X2, right? X2 into 1. I'll put this picture around. So see, this was just for one, right? If you go from here till here, this was just for adjusting the new values. Now what will be the adjusting values of W1 and W2? So now we already have the older values of W1, W2. So the new value of W1, W2 will be dW is equal to W1 minus dE by dW1, and W2 will be equal to W2 minus dE by dW2, right? This will be equal to this, and but there is a special term that is called alpha that is associated here. It is multiplied here. I'll tell you what alpha is here. I don't know how to type alpha in like latex, but okay. So now you might ask that, okay, now we understand that this is the new value of W1 and W2, right? So now what will happen? This older value of W1 and W2 will be replaced by the new one, and then you again go forward, and then you again get the error, again come back, change the value, again go forward, backward, forward, backward. But there is one thing that you might ask me, that what is this A here? This A is called alpha. Sorry, this is not A, this is actually alpha, and this is also called as learning rate, or you might see people calling as LR. Right, now what learning rate is, now just pay a little attention towards here, right? So let's say the previous value of W1 and W2 will give you some error that would be here at this point, the one that I draw very small here, right? The next one will be here, then here, then here. So it might vary that how gradually you are moving your W. Let's say that you are making very small change in W, very small change in W. So your error, okay. So now let's say you have taken some initial value of W such that W1 such that the error is here, right? At this point, at this particular point. Now you make a very small change in your W1 and make it to W1 dash. So what will happen? The error will shift very slowly also, right? Your error is also going to shift very, very slowly because you have made a very small change in W1. Or otherwise, let's assume that you might, your W1 originally was here and you made a very big change in W. So your error might be here at this point. New error might be here, or it might also happen that it might come here also, right? It might change that how gradually you're moving your W. So there is this terminology that says that you should very slowly move your W so that you don't miss your minima. Let's assume that you slowly moved your hair till here. So you have come till here. Your W1 is here now. And now you suddenly you did a change in W1 so large that you came here. You came at this point. Now this is bad because you missed the global minima in here, right? So what people say that you should very slowly move the value of W, very slowly. You should do all the changes very slowly, and your DE by DW, your DE by DW should be controlled by some another external factor, and that factor is called alpha. Now, because if you go down the screen, if you see, I have multiplied this dE by dW term with a thing called alpha. Now this alpha is with you. This is a constant and this is in your hands. You can change it anytime that you want, right? So what you will do is, I'll move back up here. So what you will do is that you will select the value of alpha such that it is moving very slowly, right? But now there's a disadvantage also, because if you move very slowly, then let's say you are here, then you will come here at this point, then here, then here. So you might reach your global minima at a very larger time. It will take a lot of time to you. So you have to take a very critical value of alpha such that it moves very slowly. Okay, I'll take up a new Python and I'll just demonstrate you how images. Okay, so there are multiple libraries that you might want to use. These libraries for image reading, image processing, and I personally feel if you have passion for images, these are the best libraries that you should use. And see, one thing is that deep learning is doing wonders in all the dimensions, but especially in image, it is doing great. And deep learning started with images only, and that's why we are covering multiple use cases in images only and less in other domains. So that's why you need to also have first is OpenCV. Without any doubt, you should use OpenCV. Second one is, I remember, SK Image. That is again made by the people from sklearn only. So sklearn machine learning you might have learned it. Third is PIL. PIL is like very largely used. Then I want to write Keras also, but Keras is actually using backend is made up of PIL only. So it doesn't make much sense that we can use. It uses PIL and SK image both. So this is these are the like major library importing libraries, and now I show you how do you import a image inside your code. Before that, let me quickly check if I have some images. Okay, I have. Okay, let's say the test image is equal to, if I go back, I have a folder called data, then I have a folder called okay, I have a cat image as a test set with me. How do you read it? First, do you import the library, then you say image is equal to cv2.imread, and then you say test image. Now you read the image, and now image is no image to you. Image is actually C, is like this. It's a matrix to you. It's a Numpy matrix to you. If you see the shape, it says it's 499 in height, 403 in width, and 3-channel image. If you want to see the image, you have to import another library that is called matplotlib. Matplotlib will help you in visualizing things. plt.imshow, and then you can do image, right? So this is a cat image, a 3-channel cat image, right? Now what I can do is, okay, I can put a, okay, here it is. Okay, I just made sure that I'm not doing any kind of a changes by putting this tag. This will make sure that we're not doing changes. Now sometimes people confuse that, this is a single channel image, and people think that single channel image is a black and white image. No, black and white images when you will only have black and white, either 0 or 255. This is a grayscale image. Grayscale image means you will have everything in the tone of you will have pixel values ranging from 0 to 255 only, but you will have this in a single codec. So you won't have 3 codecs for RGB separately, right? If you see image 2, See, you will have values all ranging from these all values, right? And if I show you one more thing, just give me a second. Image one underscore image one is equal to image dot sum x is equal to 2 image one dot shape. Okay, this is not what it is, what I was thinking, but okay, this is the basic idea. Plt dot im show image one. So what I just did was that I took the sum. Okay, I should not take the sum, I should take the mean. Okay, now I should check that if image one is equal to image two. Correct. Okay, so see, these are different techniques that you can do. You can check with your you can do multi-processing images here. You can do convert into LAB to IAB. So there are multiple mode of images. You can go and check them. Check these different things out. Right? Image processing is very cool, and especially with the libraries like OpenCV, which are now using deep learning to do image processing. It's like a whole circle. So you do image processing because you want to do deep learning. You wanted to do deep learning, right? So this is like a circle like this. You want to do image processing because ultimately you want to do deep learning. But what people are doing, people are now using deep learning to do image processing. So it's like a circle that you go round and round and round. But image processing is very cool. And okay, one thing that I did forgot to tell you, that how do you install OpenCV? Installing OpenCV is a little pain. How do you install this? Installing install OpenCV is simple. You just say pip install OpenCV -python. It's not CV2, right? And then when you say Python, and then you will import it like import CV2. So there's a little confusion. So you install it by OpenCV Python, but you import it as CV2, right? Similarly for skimage, skimage is simple, pip install skimage. For PIL is again a problem. Install PIL name is pip install pillow actually. What you have to do, what you will generally do is from PIL import image. Okay, these are the one. Keras actually gives you images inside keras.preprocessing.images. I will write it down. I can like show you also. Okay, let me show you that only. That import keras. First of all, let me put everything inside the same thing. Okay, you say keras.preprocessing.image. Okay, from this import load image, then image to array, right? These are the two things that you want to do. Then you say image underscore 3 is equal to load image, then you say dot data, and then dot get small, let us do dog. Okay, and then you say plt dot im show, and then you say image 3. It won't work, it will give you error. Oh no, it plotted. Why? See, I'll tell you actually what this image is. Image 3 will give you a image context only. This is a problem with Keras will give you this image, right? Actually, otherwise what you have to do is, if you want to see the array of array context of this, it will say, you have to say image dot array, image to array, and then you say image 3. So now it will give you all the stuff, numpy stuff, right? So if I like cut paste this thing inside this, okay, it says, so see, what is this problem with this img2 array is that this, I don't know why it converts everything into a decimal. You can see, right? See, a float, right? Only. So what you have to do is, you have to say this is as type. I think int should work. Yes. Sometimes there are very small things that you need to focus. And I think if you can see the code here of load image, this is not a very, see, it's using PIL image, right? You can read everything that how is it using. It is using color mode as RGB, then it is grayscale, interpolation is nearest. These are different codes. It is how it is reading, right? And then it is returning the image dot resize, height width tuple. Height width tuple is taken from here, right? Target sizes, and then you can do these things. Make sense? This is how you read images. You do multiple things with them. You multiply some values and you come out grayscale. How do you do single channel images, right?
So, suppose you are a computer vision engineer and a client has approached you with a problem statement in which you have to detect the faces from a set of images that they will be providing, and you have taken up this project, and these are the following steps that you have to follow while building up this project. So, these are the images that they have provided to you. These are some of the images that have taken from their dataset, and here we'll be working on Python with OpenCV. In this project, we will be using the Har cascade classifier for detecting the faces from multiple images. So firstly, you have to perform the downloading part for the Har cascade system. So here I have written download Har cascade frontal face default.xml and this raw GitHub code. These are the raw datas for the Har cascade. You have to just simply save as, and you can save it as desktop, and you have the Har cascade classifier. So now next we will be just importing the CV2 and glob. So now we will be practicing it in the Jupyter notebook. So firstly you have to import the CV2 library and glob. So I want to tell you that glob is the function which returns us the array of those file name which we will write in the next line. Like we just have to perform face detection on those images which have .jpg extension. So for that I will be writing gimage equals to glob dot glob. So here I am calling the object glob and with the function glob, and here inside the function I will be writing the star dot jpg. So it will take up all the images that have extension .jpg. So after that we will detect, after getting the glob images, now we will create cascade classifier so that we can, so as it helps us in getting the face detection. It contains all the features of the images like nose, ears, face, object. These are some of the features of the image. So here we will be writing detect equals to cv2 dot cascade classifier. Then inside the braces we will be writing which classifier. We have downloaded the Har cascade frontal face default classifier, so we will be mentioning the same name, Har cascade. Okay, Har cascade frontal face default.xml. So now after creating the Har cascade frontal face default XML file, then what we will do, we will now traverse the glob images so that we can detect the faces. So for traversing we will be creating a for loop for traverse, or you can also write t image for traversing the image, t image in g image, the glob image. Okay, so now it will take one image at a time. Now in the for loop we will read the image, a particular image. So for just reading the image we will write like I have taken image equals to cv2 dot im read, and what is this reading? The t image. Okay, so after reading the particular image from the G image, now we will convert the images. These are the colored images. The image that it has read, it is the colored images. So in this face detection, we will first have to convert the colored image into the grayscale image. So it is easier for the classifier to handle the image and detect the faces from it. So for converting the image from converting the colored image to grayscale image, we will write gray image. I have written this gray image equals to cv2 dot cvt color color, and in the braces it will have this image that you have to convert it into grayscale. This image comma the we will write cv2 dot color and underscore bgr to gray gray. Okay, so after converting it into grayscale, now we will detect the faces from the images. So for detecting the faces, I will be writing the face equals to detect dot detect. I am calling this object here, and with the function detect multi-scale, and it has 3 parameters. So the first one is in which image you want to detect the face. So we will be writing this gray image here, and the next parameter is the scale factor. So we have to see the value of the scale factor, as the scale factor is that value which decreases the volume of the whole grayscale image by 5% until the face is detected. So it basically what does it decreases the value of the image so that it can find the face from the image. So I am writing 1.25. The smaller the value is, the greater will be the accuracy. So I am writing 1.25, and the next parameter is the minimum neighbor. So we don't have to bother this value. Now after that, after detecting the face, now we will be describing the rectangle shape for the face. So for that, create a for loop for. Now in this braces, we will be writing all the dimensions for the rectangle like x, comma, y, comma, w, comma, h, length, breadth, height and width. Okay, so after the parameter, now in face, we are actually we have detected the face, but now we have to define that face with a rectangle shape. So for that, we will be using the dot rectangle function. So here I am writing cv2 dot rectangle. Okay, rectangle. Now in this we have 4 parameters. The first one is the image that you have to detect the face image, this image that we have read it here. Okay, the second parameter is the RGB value. RGB value means the colored value. So here I am writing the x, comma, y, and then the other parameters for the rectangle. We are basically defining the parameters of the rectangle, how it will look on the image. So we will be writing x plus w, comma, y plus h. Okay, so after defining the parameters of the rectangle, now we will be look at the color of the rectangle. So here I am just taking the green color. So this is the code for green color. Okay, 0, 255, 0. Okay, so now after that the last parameter is the thickness of the rectangle. So I am giving 2. So now after defining the rectangle, now we will just show the image. So for displaying the image, cv2 dot imshow, in the parenthesis we will be writing detect. Any message you can write like detect images. Okay, and comma, which image? This image. So image. Okay, so after displaying the images, now we will be defining the wait key function. What does wait key does is we will define some intervals between the images. It's just a time period that what will be the intervals between the images. So cv2 dot wait key, and how many I am taking 200 milliseconds, sorry 2000 milliseconds, and we will be writing cv2 dot destroy all Windows. So destroy all windows will closes all the windows based on the wait for key parameter. So here I'm writing the 2000 milliseconds. So it will destroy it for that. So here, okay, so I'm running this code. So here you can see that all the faces have been detected.
Machine learning is the heart of artificial intelligence, and it consists of techniques that lay out the basic structure for constructing algorithms. These algorithms are used to build machine learning models that predict some outcome based on the input. So let's look at the first question. So the first question is, what are the types of machine learning? So there are three types of machine learning, that is supervised learning, unsupervised learning, and reinforcement learning. So let's see them in detail. So the first is supervised machine learning. In this type of machine learning technique, machine learns under the supervision of labeled data. There is a training data set on which the machine is trained, and it gives the output according to its training. So for example, if a patient is diagnosed for a disease of cancer, so the machine will predict the outcome based on the input or the symptoms as positive or negative.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.
Now the next is unsupervised learning. Unlike supervised learning, it has unlabeled data. So there is no supervision under which it works on the data. Basically, unsupervised learning tries to identify the patterns in the data and make clusters of similar entities. After that, when a new input data is fed into the model, it does not identify the entity, rather it puts the entity in a cluster of similar objects. So you can see over here, the robot tries to identify the object and makes the clusters of similar objects. And whenever a new data is fed into the machine, it tries to identify it according to the cluster identified by it. Now the next is reinforcement learning. So reinforcement learning includes model that learn and traverse to find the best possible move. The algorithm for reinforcement learning are constructed in a way that they try to find the best possible suit of action on the basis of the reward and punishment theory. So you can see in the example, the agent tries to learn from the environment, observes the environment, select action using policy, and it gets a reward or penalty according to its suitable action. So whenever it gets the reward or penalty, it tries to learn the right suitable action according to the environment. Now let's see the next question. So differentiate between classification and regression in machine learning. So in machine learning, there are various types of prediction problems based on supervised and unsupervised learning. There are classification, regression, clustering, and association problems. So here we'll discuss about classification and regression. So in classification, we try to create a machine learning model that assists us in differentiating data into separate categories. So the data is labeled and categorized based on the input parameters. For example, imagine that if we want to make predictions on the churning out of customers for a particular product based on some data recorded. So either the customer will churn out or they'll not. So the labels for this would be yes and no. So this lies under classification problem. Now the next is regression. So it is the process of creating a model for distinguishing data into continuous real values instead of using classes or discrete values. It can also identify the distribution movement depending on the historical data. So it is used for predicting the occurrence of an event depending on the degree of association of variables. For example, the prediction of weather condition depends on factors such as temperature, air pressure, solar radiation, elevation of the area, and distance from the sea. So the relation between these factors assist us in predicting the weather condition. So this was about classification and regression. So the next question is, what is linear regression? So linear regression is a supervised machine learning algorithm. It is used to find the linear relationship between the dependent and the independent variables for a predictive analysis. So you can see the equation over here, that is y equal to a plus bx, where x is the input or the independent variable, y is the output or the dependent variable, and a is the intercept and b is the coefficient of x. So let us see the graph for it. So this is the graph where it is having a best fit line that shows the data of weight, that is y or the dependent variable, and height, that is the independent variable, of 21 years old candidates scattered over the plot. So this straight line shows the best linear relationship that would help in predicting the weight of the candidates according to their height. So to this best fit line, we'll try to find the best values of A and B, and by adjusting the values of A and B, we try to reduce errors in the prediction of Y. So this is how linear regression helps in finding the linear relationship and predicting the output. Now let's head on to the next question. The question is, how will you determine the machine learning algorithm that is suitable for your problem? So for identifying the machine learning algorithm for our problem, we should follow these steps. So first is problem classification, second is checking the algorithm, and third is implementing the algorithm. So classification of the problem depends on the classification of input and output. So for classification of input, it depends on whether we have data labeled, that is supervised learning, or unlabeled, that is unsupervised learning, or whether we have to create a model that interacts with the environment and improves itself. For classifying the output, if we want the output of our model as a class, then we need to use some classification techniques. If it gives the output as a number, then we must use regression techniques. And if the output is a different cluster of inputs, then we should use clustering techniques. Now checking the algorithms in hand. After classifying the problem, we have to look for the available algorithms that can be deployed for solving the classified problems. Finally, we'll be implementing the algorithms. If there are multiple algorithms available, then we will implement each one of them one by one, and we'll check for the accuracy. And finally, we would select the algorithms that gives the best performance. Now the next question is, what are bias and variance? So bias is the difference between the average prediction of our model and the correct value. So if the bias value is high, then the prediction of the model is not accurate. Hence the bias value should be as low as possible to make the desired prediction. And the variance is the number that gives the difference of prediction over a training set and the anticipated value of other training sets. So high variance may lead to large fluctuation in the output. Therefore, the model's output should have low variance. Let's see the diagram for it. You can see in the diagram, the desired result is the blue circle at the center. And if we get off from the blue section, then the prediction goes wrong. So the model should have low bias and low variance. And if the model is having low bias, high variance, then very few of the points are lying close to the desired result. And if the model is having high bias and high variance, then the points are not lying close to the desired result. So the model should have low bias and low variance. Now the next question is, what is variance inflation factor? So the VIF is the estimate of the volume of multicollinearity in a collection of many regression variables. So it is calculated as variance of the model divided by variance of the model with a single independent variable. So the VIF quantifies the extent of correlation between one predictor and the other predictor in a model. It is used for diagnosing collinearity and multicollinearity. So higher value signifies that it is difficult and impossible to access accurately the contribution of predictors to a model. Now let's head on to the next question. So we have to explain false negative, false positive, true negative, and true positive. So let's start with true positive. When the machine learning model correctly predicts the condition, it is said to have a true positive value. Then true negative, when the machine learning model correctly predicts the negative condition or class, it is said to have a true negative value. Next is false positive. So when the machine learning model incorrectly predicts a negative class or condition, it is said to have a false positive value. Finally, when the machine learning model incorrectly predicts a positive class or condition, it is said to have a false negative value. Let's understand this with the help of an example. So if an alarm goes on in case of a fire, it is true positive in the sense that there is a fire. That is, the fire is positive and the prediction made by the system is true. Next is, if the alarm goes on and there is no fire, then system predicted fire to be positive, but it made a wrong prediction, hence the prediction is false and the condition is false positive. Next is, if the alarm does not go on but there was a fire, system predicts fire to be negative, which was false since there was a fire. So it is a false negative condition. Finally, if the alarm does not go on and there was no fire, the fire is negative and this prediction was true. So the condition is true negative. Now let's head on to the next question. So what is a confusion matrix? So confusion matrix is used to explain a model's performance and gives the summary of the prediction on the classification problems. So it assists us in identifying the uncertainty between classes. So this is the formula for calculating the accuracy from a confusion matrix. So it consists of true positive, true negative, false positive, and false negative values. So the accuracy is calculated as the sum of the true positive and true negative values divided by all the outcomes. So the accuracy is calculated as the sum of true positive and true negative values divided by true positive, true negative, false positive, and false negative. For example, consider this confusion matrix and it consists of values as true positive, true negative, false positive, and false negative for a classification model. Now the accuracy of the model can be calculated as below. So it is the sum of true positive and true negative value divided by the sum of true positive, false negative, true negative, and false positive values. So the accuracy comes to be 0.78. So the accuracy of the model is 78%. Now let's head on to the next question. So what do we understand by type 1 and type 2 error? So type 1 error is also called as false positive, and it is an error where the outcome of a test shows the non-acceptance of a true condition. For example, a cricket match is going on and when a batsman is not out and the umpire declares that he is out, this is a false positive condition. So here the test does not accept the true condition that the batsman is not out. Now type 2 error. So type 2 error is also called as false negative, and it is an error where the outcome of a test shows the acceptance of a false condition. For example, the CT scan of a person shows that he is not having a disease, but in reality he is having it. Here the test accepts the false condition that the person is not having the disease. So when should you use classification over regression? So both classification and regression are associated with prediction. So classification involves the identification of values that lie in a specific group, whereas the regression method entails a predicting a response from a consecutive set of outcomes. So the classification method is chosen over regression when the output of the model needs to yield the belongingness of the data points in a dataset to a particular category. For example, we have some names of bikes and cars. We would not be interested in finding how these names are correlated to bikes and cars. We would check whether each name belongs to the bike category or the car category. So that is why we use classification over regression. Now let's head on to the next question. So we have to explain logistic regression. So logistic regression is the proper regression analysis used when the dependent variable is categorical. Like all the regression analysis, logistic regression is a technique for predictive analysis. It gives the output as binary. So logistic regression is used to explain the data and the relationship between one dependent binary variable and the one or more independent variables. Also, it is employed to predict the probability of a categorical dependent variable. For example, if we have to predict whether a citizen is a senior or not, so the output will be in 0 or 1. So there are three types of logistic regression, that is binary logistic regression. So in this, there are only two outcomes possible. For example, to predict whether it will rain or not, it will give the values as 1 or 0. The next is multinomial logistic regression. So in this type of regression, the output consists of three or more unordered categories. For example, prediction on the regional languages like Marathi, Telugu. The next is ordinal logistic regression. So in ordinal logistic regression, the output consists of three or more ordered categories. So rating an Android application from 1 to 5 star, it comes in ordinal logistic regression. Now the next question is, imagine you are given a data set consisting of variables having more than 30% missing values. Let's say out of 50 variables, 8 variables have missing values which is higher than 30%. So how will you deal with them? So to deal with the missing values, we need to first identify the values, and for that we'll specify a different class for the missing values. After that, we'll check the distribution of values over the data set, and we would hold those missing values that are defining a pattern. Finally, we'll change these into yet another class while eliminating the others with the help of eliminating functions available in Python or R. Now, the next question is, how do we handle the missing or corrupted data in a data set? So in Python, there are two methods that are very useful. So we can use these two methods to locate the lost or corrupted data and discard those values. So the first is null method. So we can detect the missing values using isNull method. And after that, we can use drop NA for removing the columns and rows with null values. Also, we can use fill NA to fill the void values with a placeholder value. Now, let's head on to the next question. So we have to explain principal component analysis. Firstly, this is one of the most important machine learning interview question. So in the real world, we deal with multi-dimensional data. Thus the data visualization and computation becomes more challenging with the increase in dimensions. So in such a scenario, we might have to reduce the dimension to analyze and visualize the data easily. So we do this by removing the irrelevant dimensions, keeping only the most relevant dimensions. So this is where we use principal component analysis. So finding a fresh collection of uncorrelated dimensions and ranking them on the basis of variance are the goals of PCA. So here is the mechanism of PCA. So we have to compute the covariance matrix for data objects. Then we have to compute the eigenvectors and eigenvalues in a descending order. Next is to get the new dimensions and select the initial n eigenvectors. Finally, we'll change the initial n-dimensional data objects onto n dimensions. So here is an example for it. Here, the two graphs shows the data points and the two directions. One is green and the other is yellow. So we got the graph 2 by rotating the graph 1 so that the x-axis and y-axis represent the green and the yellow directions. So after the rotation of the data points, we can infer that the green direction gives us the line that best fits the data points. So here we are representing two-dimensional data, but in real life, the data would be multidimensional and complex. So after recognizing the importance of each direction, we can reduce the area of dimensional analysis by cutting off the less significant directions. Now we'll look into another important machine learning interview question. So why rotation is required in PCA? So what will happen if you don't rotate the components? So rotation is a significant step in PCA as it maximizes the separation between the variance obtained by the components. Due to this, the interpretation of the components become easier. So the motive behind doing PCA is to choose fewer components that can explain the greatest variance in a dataset. So when rotation is performed, the original coordinates of the points gets changed. So there is no change in the relative position of the components. So if the components are not rotated, then we need more extended components to describe the variance. Then the visualization and prediction becomes more difficult. So you can see over this graph, the data points, these blue dots represents the data points. And if we rotate the axis to these dimensions, then all the points will lie in this x-axis. So the previous one is x-axis and the new dimension is x-axis where all the data points lies. Now let's head on to the next question. So we know that one hot encoding increases the dimensionality of a dataset, but label encoding doesn't. So how? So when we use one hot encoding, there is an increase in the dimensionality of a dataset. So the reason for the increase in dimensionality is that for every class in the categorical variable, it forms a different variable. Suppose there is a variable called color. It has three sub-levels as yellow, purple, and orange. You can see over here. So one hot encoding color will create three different variable as color.yellow, color.purple, and color.orange. Now in label hot encoding, the subclasses of the certain variables get the values as 0 and 1. So we use label encoding only for binary variables. So this is the reason that one hot encoding increases the dimensionality of data and label encoding doesn't. So you can see over here that in this label encoding, the categorical variables or categorical values are given to the name of the food, and in one hot encoding the 0 and 1 values are given and the separate variables will be created for it. So it increases the complexity of the data. Now let's head on to the next question. How can you avoid overfitting? So overfitting happens when a machine has an inadequate data set and it tries to learn from it. So overfitting is inversely proportional to the amount of data. So for small database, we can bypass overfitting by the cross-validation method. So in this approach, we'll divide the dataset into two sections. So these two sections will comprise testing and training sets. So to train the model, we'll use the training dataset, and for testing the model, for new inputs, we'll use the testing dataset. This is how we can avoid overfitting. Now let's head on to the next question. Why do we need a validation set and a test set? So this question is similar to the previous one. So we split the data into three different categories while creating a model. The first is training set, the second is validation data set, and the third is testing data set. So let's see training data set. So we use the training set for building the model and adjusting the model's variables. But we cannot rely on the correctness of the model built on top of the training set. The model might give incorrect output on feeding new data. So we use validation set. So we use a validation set to look into the model's response on top of the sample that doesn't exist in the training data set. then we will tune hyperparameters on the basis of the estimated benchmark of the validation data. When we are evaluating the model's response using the validation set, we are indirectly training the model with the validation set. So this may lead to the overfitting of the model to the specific data. So this model won't be strong enough to give the desired response to the real world data. So for this, we use the test dataset. The test dataset is the subset of the actual dataset, which is not yet used to train the model. So the model is unaware of this dataset. By using the test dataset, we can compute the response of the created model on hidden data. So we evaluate the model's performance on the basis of test dataset. So we do not always expose the model to test dataset after tuning the hyperparameters on top of the validation set. As we know, the evaluation of the model on the basis of the validation set would not be enough. Thus, we use a test set for computing the efficiency of the model. Now, let's head on to the next question. So what is a decision tree? So a decision tree is used to explain the sequence of action that must be performed to get the desired output. So it is a hierarchical diagram that shows the actions. So you can see the diagram over here. So we can create an algorithm for a decision tree on the basis of the hierarchy of actions that we have set. So over here, you can see we are checking whether a person is fit or not. So the parameters are, the first one is, we'll check whether the person's age is greater than or less than 30. So if it is yes, then we check for eats a lot of pizzas. So if this condition is true, then the person is unfit. And similarly for this, if the person is greater than 30, it checks for exercises in the morning. And if it is yes, the person is fit. So this is the working mechanism of a decision tree. So let's head on to the next question. So we have to explain the difference between KNN and K-means clustering. So K nearest neighbor or KNN, it is a supervised machine learning algorithm. And in KNN, we give the identified or labeled data to the model. Then the model matches the points based on the distance from the closest point. So you can see over here, these are the matched points according to the centers. And for K-means clustering, it is an unsupervised machine learning algorithm. So in this, we give the unidentified or unlabeled data to the model. Then the algorithm tries to create the batches of points based on the average of the distances between the distinct points. So you can see over here, these clusters are formed. So this is the difference between KNN and K-means clustering. Now the next question is, what is dimensionality reduction? So in the real world, we build machine learning models on top of features and parameters. So these features can be multi-dimensional and large in number. Sometimes the features may be irrelevant and it becomes a difficult task to visualize them. So here we use the dimensionality reduction to cut down the irrelevant and redundant features with the help of principal variables. So these principal variables are the subgroup of the parent variable and it conserves the feature of the parent variable. Now let's move on to the next question. Both being tree-based algorithms, how is random forest different from gradient boosting algorithm? So the main difference between a random forest and GBM is the use of techniques. They both use different techniques for implementing. So random forest advances prediction using a technique called bagging, and GBM uses boosting to advance the predictions. So let's check each one of them. So in bagging, we apply arbitrary sampling and we divide the data set into n samples. After that, we build the model by employing a single training algorithm. Further, we combine the final predictions by pooling. So bagging helps to increase the efficiency of the model by decreasing the variance for overfitting. Now let's see boosting. So in boosting, the algorithm try to review and correct the inadmissible predictions at the initial iteration. After that, the algorithm's sequence of iteration for correction continues until we get the desired prediction. So boosting assists in reducing bias and variance both for making the weak learners as strong learners. Now let's move on to the next question. suppose you found that your model is suffering from high variance. So which algorithm do you think you could handle this situation and why? So for handling the issues of high variance, we should use bagging algorithm. So what it does is it splits the data into subgroups with replicated sampling of random data. And when the data is splitted into subgroups, we create rules using particular training algorithms. And finally, we use pooling for combining the predictions of the model. So you can see the diagram. The data is divided into subgroups as bootstrap 1, 2 till n, and the models are created as model 1, 2 according to the training algorithms, and finally they vote for the final prediction. Now the next question is, what is ROC curve and what does it represent? So ROC stands for receiver operating characteristic. So we use ROC curve to represent the trade-off between true and false positive rates. So in ROC, the area under curve gives us an idea about the accuracy of the model. So you can see the graph. So this graph shows an ROC curve. So the greater the area under the curve, better the performance of the model. So let's move on to the next question. So what is rescaling of data and how is it done? So in real world scenarios, the attributes present in the data will be in a varying pattern. So rescaling of the characteristic to a common scale gives benefit to algorithms to process the data efficiently. For example, if a student is gaining marks out of 100 as 60 in subject 1, out of 150, 120 in subject 2, and 180 out of 200 in subject 3. So after rescaling, the marks will be out of 10. So in subject 1, he'll get 6 out of 10. In subject 2, he'll get 8 out of 10. And in subject 3, he'll get 9 out of 10. So this is how rescaling gives us the benefit to rescale the data in a common scale. Now let's move on to the next question. So what is binarizing of data? So in most of the machine learning interviews, so this question is asked. So I'll give you an example. So first of all, converting data into binary values on the basis of threshold values is known as the binarizing of data. So the values that are less than the threshold are set to 0 and the values that are greater than the threshold are set to 1. So this process is useful when we have to perform feature engineering, and we can also use it for adding unique features. So here, if a student A in subject 1 gets 60 out of 100, in subject 2 he gets 20 out of 100, and in subject 3 he gets 70 out of 100. So if the threshold is set to 40, so if the marks are greater than 40, then the student is passed, or if it is less than 40, then the student is failed. So after binarizing, we'll get the output as 1 and 0, from which we can decide whether the student is failed or not. Now, let's move on to the next question. So, how to standardize data? So, standardization is the method that is used for rescaling data attributes. And the attributes would likely to have a value of mean as 0 and the value of standard deviation as 1. So, the main objective of standardization is to prompt the mean and standard deviation for the attributes. So, we'll implement standardization using Python. So let's move on to our Jupyter notebook. So this is our Python code for standardization. So we have imported the Numpy library and matplotlib.pyplot and pandas. So we'll be using the pre-processing in Python. So we'll be importing it from sklearn package. So basically, pre-processing is used. It is a package that provides several common utility functions and transformer classes to change raw feature vectors into a representation, and that will be more suitable for downstream estimators. So in general, learning algorithm benefit from the standardization of the data set. So this is the use of pre-processing. Then we'll load the data set. So I have loaded the data set using pd.readcsv. After that, we'll have a look at the original data. So the original data is over here. So it denotes the scientific values. So we have to do min-max scaling, or it is called rescaling of the data. So for this, we'll use min-max scaler. So we'll be storing it in min_max_ scaler. So pre-processing dot min-max scaler, and the range of the feature will be from 0 to 1. So values will be stuck in between 0 and 1. After that, we'll use this fit_transform to fit the value of the data and transform it into a format. So let's have a look at the values after min-max scaling. So you can see the values are between 0 and 1. So these are rescaled. Now we'll look at standardization. So we'll use standardization, and we'll use this object of standardization and store this standard scaler in it so that we can use it afterward in standardization. After that, for scaled feature, we'll use this object as x_ after standardization to store the values that are standardized. So after printing the values after standardization, the output would look like this. So the negative values are the values that are less than mean, and the values which are positive are greater than the mean. Now let's move on to the next question. So executing a binary classification tree algorithm is a simple task, but how does a tree splitting takes place? How does tree determine which variable to break at the root node and which at its child nodes? So Gini index and node entropy assist the binary classification tree to take decisions. So basically the tree algorithm determines the feasible feature that is used to distribute the data into the most genuine child nodes. And according to Gini index, if we arbitrarily pick a pair of objects from a group, then they should be of identical class and the possibility for this event should be 1. So to compute the Gini index, we should do the following. So we should compute the Gini for subnodes with the formula as the sum of the square of the probability for the success and failure. So that is p square plus q square. Then we have to compute Gini for split by weighted Gini rate of every node of the split. Now we'll see entropy. So entropy is the degree of indency that is given by the following. So this is the formula for entropy, where A and B are the possibilities of success and failure of the node. So when entropy is equal to 0, the node is homogeneous. And when the entropy is high, both groups are present at 50-50% in the node. Finally, to determine the suitability of the node as the root node, the entropy should be very low. Now let's move on to the next question. So what is support vector machines? So support vector machine is a machine learning algorithm that is majorly used for classification. So it is used on top of the high dimensionality of the characteristic vector. So we'll implement SVM using Python. So let's move on to our Jupyter notebook. So I've written this code. So first we'll import data sets from the sklearn package, then confusion matrix, as we will be calculating the accuracy of the model, and train test split from sklearn dot model selection, because we'll be splitting the data set into train and test set. So we'll use the iris data set for this. So I'll load the data set and I'll store it in iris.data and iris.target. Then we'll be splitting the data set into train and test set. So we have separated the data into data and target and stored it in A and B. So we'll be creating separate test and train data set for it. So we'll be using train test split function for this, and we'll give the argument as A, B, and random state will be 0. After that, we'll import svc from sklearn.svm to implement the model. So we'll build the svm linear model by using the svc function and store it in svm underscore model underscore linear, where kernel will be linear and will give the data as train dataset. After that, we'll predict the model's outcome using the predict function and give the argument as test. Finally, to calculate the accuracy, we'll be using the score function. So we'll be using this svm model linear dot score and give the argument as a underscore test and b underscore test. So after that, we'll get the confusion matrix. So we'll be using the confusion matrix function. So this will be our output. So this is our output that we get, and using this confusion matrix, we can calculate the accuracy of the model. Now let's move on to the last question of this machine learning interview questions tutorial. So we have to implement KNN classification algorithm. So the problem statement is classify the iris flower based on sepal and petal length and widths using KNN. So we already know that it is a supervised machine learning algorithm, and in it we give the identified or labeled data to the models, and then the model matches the points based on the distance from the closest point. So let's move on to our Jupyter notebook for implementing this. So this is our code for implementing the KNN classification algorithm. So we'll load the iris dataset from sklearn.datasets. Then we'll be importing k neighbors classifier, which will help us in implementing the KNN classification algorithm. We'll import Numpy and then train test split so that we can split the dataset into train and test dataset. Then we'll load the iris dataset and store it in iris underscore dataset. After that, we'll be splitting the dataset into train and test using the function of train underscore test underscore split. After that, we'll use k neighbors classifier and we'll store it in kn object. Then we'll fit the model on top of training dataset, that is a underscore train and b underscore train. After that, we'll be creating a new array and store the values of the characteristics of the flower in a underscore new. Then for predicting, we'll use this predict function to predict the outcome using the a underscore new dataset. After that, we'll be printing the predicted target value, predicted feature name, and the test score, which will give us the accuracy of the model. So the model has predicted that the feature name is Satosa and the test score is 0.97. That means the accuracy of the model is 97%.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.